Hello friends, welcome back to our channel. So today we'll start one more concept called design and analysis of algorithms. So in today's session we'll see what is an algorithm and the complete introduction to designing of algorithm and algorithm analysis. So and analysis of algorithms. So many of the viewers were requesting me to start this subject, design and analysis of algorithms, because this subject will be the most important subject for all the computer science students. So in order to get a higher package, the students have to focus on this particular design and analysis of algorithms. So mainly the data structures and algorithms concepts, right? So first we'll see what is an algorithm. So most of you know about this. What is the definition of an algorithm? So algorithm is defined as a set of instructions, okay, which are involved to solve the problem or a specific task. So if any problem is given, if any task is given, so what are the steps we have to follow in order to solve that, in order to achieve that, right? So it is a set of instructions, or we can also call them as a steps, okay, to solve problem, or we can call it as a task. So set of instructions or steps to solve the problem or task. And see, this algorithm is a most fundamental blocks for any programming to solve the problems. So this is the most major part while solving the problems. Here solving the problem means automation. In our language we can call it as an automation. So we'll consider one problem and we have to provide the solution by giving some sort of programming, right? So in order to give that, the main aim is to get the optimal solution. So for every problem there will be a lot of solutions, right? Solution 1, 2, 3 and so on, solution n. That means one problem can be solved in many ways, right? But we have to consider the optimal solution. Optimal, that means the best solution. So for this, to better understanding, I'll tell you a small example. If you want to go from one place to another place, so there will be a lot of paths, but we have to select the shortest path, okay, so that the time will be saved and also the fuel will be saved. So it depends upon the constraints, we have to select a proper solution. So among all these solutions we have to select a proper solution, right? So that's why this depends upon the methodology we are using to solve the problem. So there will be different methods to solve a problem, but we have to select a method which gives the best solution. So that we call it as a optimal solution. Based upon our requirement, we have to select the solution. So that's why the algorithm will be the most important fundamental block for all the problems to be get solved. So either it may be a simple problems or a complex problems. So both the problems can be solved by these algorithms. And there are many algorithm methodologies, right? So now we'll see the algorithm methodologies. So types or methodologies or methods are, the first one, searching techniques. So there will be a lot of searching algorithms, a linear search, binary search, etc. Similarly, sorting techniques. So we can use this sorting mechanism. So either, arranging the values in either increasing order or a decreasing order. So sorting algorithms will be there. A lot of algorithms: bubble sort, quick sort, merge sort, etc., etc. And similarly, brute force. Brute force methodology. So brute force methodology means checking all the possibilities. So we don't know the best one, so checking all the possibilities. So brute force method. Similarly, greedy method, dynamic programming, divide and conquer, method, recursive programming. Recursive programming. So these are all the different methodologies we can use to solve any kind of problem. But one important point is, one particular method will not be suitable for all the problems to be get solved with a better solution. So based upon the problem, we have to analyze which method will be suitable to get the perfect solution. So we have to learn all these things so that we can have an idea about all the methodologies, so that based upon the problem, we can select one among these methodologies to solve that particular problem. So this plays a very crucial role, right? So, and this is the first part, designing of algorithm in this subject. So which methodology we are going to use in order to solve the problem, whether we are using the brute force method or a dynamic programming method or a divide and conquer or a greedy method, etc., etc. And the next one is the analysis. So algorithm analysis, and this algorithm analysis is used to evaluate the performance of the algorithm. So if we use the performance of the algorithm, so used in evaluating performance of algorithm. So here the word performance will be in terms of two things. One is the space complexity. So another one is the time complexity. Time complexity, space complexity, and the time complexity. That means how much space it requires to solve the problem. That means a memory, right? So how much time it takes to give the response or to get the complete solution. That's also an optimal solution. So these are the two terminologies we have to consider in this algorithm analysis. So there are different categories of analysis, different types of analysis. So one is a best case analysis, best case, worst case, average case, and amortized case, right? So based upon these things, we have to evaluate the performance of algorithm, right, in terms of space and time complexities. So it should use a less space complexity and the less time complexity. Then that also with the help of the requirements, according to the requirements of the problem, right? So for example, let us consider if you want to travel from one place to another place. Okay, so from A to B. So there are two paths. One is a narrow road and another one is wide road. So if you are using a two-wheeler, automatically it suits this path to reach the destination within a short time. Okay, and if you are using the four-wheeler, okay, this path doesn't suit for this four-wheeler to reach the destination, right? So this four-wheeler have to choose in this path. So that means based upon the requirements, we have to get the optimal solution. Based upon the requirement, we have to choose the method to get the optimal solution, and also in terms of the performance, the space and time complexity, right? So from our next sessions, we'll see each and every methodology, and also the algorithm analysis concept. So this will be the most useful for the students of a computer science, particularly a computer science. Very important. Types of time complexity. So in our previous session, we have discussed about the introduction to analysis of algorithms. So in that we have seen the two parameters, that is a time complexity and the space complexity, are the two parameters to evaluate the performance of an algorithm. So time complexity means how much time it takes to execute the algorithm or a problem or a task. So there are different types of time complexities. Now we'll see one by one, right? So first I list out the types of time complexities, and then we'll go one by one. First one is a constant time complexity. Usually it is denoted as order of 1. Next, linear time complexity. It is denoted as order of n. So we will see this order. What is the order, right? So there will be different asymptotic notations. So that we will discuss in our further session. Just you can observe the denotations, just like a denotation. Order of n and order of n. Okay. Next, logarithmic time complexity, which is denoted as order of log n. Usually the base will be 2. Next, order of n log n. So there is no specific, so we can call it as a n log n time complexity. Time complexity. So in the name itself indicates, so then it will be denoted as order of n log n. So which will be similar with the logarithmic time complexity. And the next one is quadratic time complexity. Quadratic time complexity, so which will be denoted as order of n square. Order of n square. So these are the 5 different types of time complexities. So not every algorithm will have a single time complexity. Okay, so based upon the algorithm and based upon the inputs we are giving, the time complexity will be changed. So obviously the time complexity depends upon the input size. So the problem with a different input size will give a different time complexities. Right. So let us see one by one. First, coming with the constant time complexity. Constant time complexity. So just now we have said that time complexity means the time taken to execute the problem or to perform a particular task. So here, number of steps required to execute the problem is a constant. That means if the input size is increased, even though the number of steps required to execute the problem remains constant. So irrespective of the input size, the number of steps is constant. So the time doesn't affect with respect to the size of the input. So time doesn't affect or does not vary if the increase in input size. So if the input size is increased, then also the time taken to execute the problem will be remains same. Okay, so best example for this one is all the arithmetic operations. All arithmetic operations. So even though the number of the input increases, the performance of this operation will be same. The addition or subtraction or multiplication or division, the time doesn't changes. So such type of statements, we can say the time complexity will be order of 1 or 2 or 3 or 4. It's a constant. We simply say it as a constant, right? So next, coming to the second category, linear times complexity. Linear time complexity. So which is usually denoted as order of n. So here the number of steps required to execute the problem depends upon the number of size, the input size. So if the input size is increased, automatically the time taken to execute the problem will also be increased. So number of steps required to complete or to execute the problem depends on input size. That means if input size increases, then time taking to execute will also increase. So that means directly proportional. Okay, so directly proportional. So the time is directly proportional to the input size. So if the input size is small, automatically the time taken to execute the problem will be low. And if the input size is more, the time taken to execute the problem will be more. That means a direct proportional. So best example for this one is linear search. Linear search. So I think most of you are aware about these searching and sorting algorithms, because so if you are watching this design and analysis of algorithms, obviously you might be having a knowledge on searching and sorting techniques, right? So linear search means irrespective of the order of the elements, the search will be keeps on going from one element. That means every element will be compared. Okay, every element will be compared. For example, if you want to search some 100, okay, in 10 elements, okay, if you want to search one element in 10 elements, if the element is at the last position, what we have to do? So every element we are going to search until it gives the success. So it takes some 10 steps to complete its execution. For example, if we are having 100 elements, it will take 100 steps to complete its execution if the search element is at the last position. Okay, so similarly, linear search is the best example for this type linear time complexity. That means if the size increases, the time will also be increased. So, and obviously one more example, general example, if you are having a lock and you forgot the key and you are having a bunch of keys, what you will do to open the door? So you will try with each and every key. So if the correct key is the last key in the bunch, obviously you have to compare, you have to try for all the keys in the bunch. If the size of the keys, bunch of the keys increase, automatically the time taken to open the door will be also be increased. So such type of complexity, we call it as a linear type complexity. Hope you understood. Then coming to the third one, logarithmic time complexity. Logarithmic time complexity, and it is denoted as order of log n. Order of log n. And here the number of steps required to execute the problem will be reduced for every iteration. So the problem space will be reduced. So initially, if the problem space is n, after completion of the first iteration, the problem space will be reduced to n by 2. And obviously, again, the same problem will be divided into half, that means n by 4. So this process will be repeated until the problem has been solved. So such type of things, we call it as a logarithmic time complexity. Okay, here the problem will be divided into small bits or small parts, and after every division the problem space will be reduced to half. Right, see here, problem will be divided into small parts. So after each division, the space, the number of steps, or you can say number of steps, will be reduced to half. Okay, so such type of algorithms, the time complexity, we call it as a logarithmic time complexity, and it will be denoted as order of log n. Okay, now the best example for this one is a binary search. Binary search. So most of you know about this binary search. Again, I will say that one. So the first constraint is, if we want to implement this binary search, the elements should be in a sorted order. All the elements should be in a sorted order. If the elements are in sorted order, if you are searching for a particular element, so first it will find out the middle element, and it will compare the search element with the middle element, and if it is less than, so then the search position will be shifted towards the left part, and if it is greater than, the search position will be shifted towards the right part. For example, so 10, 20, 30, 40, 50. So if search element is some 10. So first it will find out the mid. In the first iteration it will find out the mid. So 10 is less than 30. So next search space will be this one. Next search space will be this one. So that means after every division, the complete steps are reduced to half. And in next iteration, again here we have to find out the mid and have to repeat the same process. So the same process will be repeated. That means the division of sub-problems will be done until it reaches or it completes its execution. So binary search will be the best example for this logarithmic time complexity. Okay, reducing the search space or reducing the steps to execute the problem. Coming to the next one, that's also similar to this logarithmic, which is order of n log n. So the same thing happens here also. So we are saying that order of n log n, you can see here also the problem will be divided into small parts. Small parts. Again, same. Each part, okay, after each division, number of steps required to solve the problem will be reduced to half. So this is nothing but our logarithmic time complexity. After that, collaborating all such small parts. So collaborating all small parts to complete the execution, right? For example, one problem is divided into n parts. Okay, one problem is divided into n parts. Sorry, 1, 2, 3 and so on. Okay, now you can see for each part again it is divided. Okay, so for this we'll say it as a log n. Again here it is a log n, here it is a log n. So like this, if we are having some n problems, so then we can say it as a n log n. That means after dividing the parts, after completion of this one, again we have to collaborate all the parts to complete its execution. Right? So the example for this one is merge sort. So merge sort. So in this merge sort, what we are doing? So we are dividing the complete elements into two halves. Again, from the right half and from the left half, again we are dividing it in two halves. Again we are dividing the left half and right half into two halves. Later we are applying the merging operation, and again we are starting collaborating the left and right halves to combine the complete sorted order. Right? So that is the best example for the merge sort. Okay, and this type of algorithm is more efficient if the size of input is large. So this algorithm is efficient and works good for large inputs. That means if the input size is more, this is more suitable. Okay, this type of algorithm will be suitable, and the time complexity we call it as an order of n log n. And the last one, quadratic time complexity. Quadratic time complexity, and usually we will denote it as n square. So here the number of steps required is more than the input size. So if the input size is n, the steps required to execute the problem will be n square. So double the steps, double the input size. Okay, so that's why we will represent it as an order of n square. So steps required to execute the problem is double the input size. So if n is an input size, then n square will be the steps required. And this algorithm is very slow if the size of input is more, because it takes a double of the steps, right? So this type of algorithm will be slow for large inputs. So if the input is large, the number of steps required will also be large. Right? The best example for this type of complexities we call it's a bubble sort. So the main logic of implementing the bubble sort is comparing the consecutive elements. So after first pass, the highest element will be residing at the last position. So in the first pass, we are going to compare consecutive elements. Okay, so in an array, if you want to compare the consecutive elements, first element and second element and third element and fourth element, so like that, if you want to compare the consecutive elements, then this complexity will be suited, and that will be the example for this particular complexity, quadratic time complexity. Right, so hope you understood this one. And apart from this, we are having a cubical time complexity, which is represented as n cube, and more time complexities are there. So these are the mostly we will see these type of complexities in different algorithms. And one thing I'm just repeating, so the time complexity may vary according to the input size. So the time complexity will be not same for all the input sizes. So if you change the input size, the time complexity will also be changed. So that's why this time complexity, there are different types of time complexities. So this is the one more way to calculate the performance of an algorithm, right? So usually this is used to evaluate the performance of algorithm based on input size. So according to our discussions in our previous session, depends upon the input, the algorithm execution time will be changed. So this evaluation, these asymptotic notations will evaluate the performance of the algorithm based upon this input size, right? So there are three categories of asymptotic notations. So the first one, big O notation, omega notation, and theta notation. Right? So first let us see this big O notation. So big O notation is used to represent upper bound of an algorithm. And coming to this omega notation is used to represent lower bound of an algorithm. And this is to represent average bound of an algorithm. So all the three depends upon the input size. So here upper bound of an algorithm means the maximum time the algorithm will take to complete its execution, and the lower bound means minimum time the algorithm will take to complete its execution. And the name itself indicates is an average bound, or some cases we call it as a tight bound. So that means in between the upper bound and the lower bound, that means an average time, right? The average time or the exact time the algorithm takes to complete its execution, that we call it as a theta notation. So this we can call it as maximum time algorithm takes to complete its execution, and here we can say minimum time an algorithm takes, and this is an average time an algorithm takes, right? So that we have to represent by using this big O. So the maximum time the algorithm takes to complete its execution is represented as a big O scenario. Similarly, the minimum time of algorithm which takes to complete its execution will be represented with omega scenario, and similarly the theta notation. And big O notation usually represented as, big O is represented as order of n. Okay, if n is a linear. So in our previous sessions we have seen different types of time complexities, right? So in that we have seen the constant time complexity, linear, logarithmic, okay, quadratic, etc., etc. So if we are representing with a big O notation, so in our previous session everything we have represented with an order, right? So order of n, that means worst case time complexity. Okay, so and it will be represented as big O, order of n. So this will be the worst case time complexity. Similarly, omega notation is represented as like this, omega of n. This is best case time complexity, because why we are calling it as a best case means the minimum time the algorithm requires to complete its execution. So that's what we require. So that will be the best case time complexity. So the best case time complexity will be represented with omega notation. So observe, if you are watching it as a big O of n, that will be the worst case. Okay, we are always calculating the worst case complexity, right? The maximum the algorithm can take. And omega, if you observe this symbol omega of n, that will be the best case time complexity. And similarly theta, it is represented as theta of n, which is a average case time complexity. Average case. So for every algorithm we can have these three different cases. So best case time complexity, worst case time complexity, and the average case time complexity. Okay, so the representation will be different, three different symbols. And here we are taking the n. N means nothing but our linear time complexity. Linear time complexity. Okay, for example, consider searching. Okay, consider searching. So if we are having some 5 elements, okay, so if the search key is 50, right? So how many iterations we have to done, how many comparisons we have to done? So the number of comparisons we have to done is total 5 comparisons. In the 5th comparison we will get the success, right? So that will be the worst case, that means maximum time. So if the search key is 60, then also the algorithm, the search key should be compared each and every element until it goes to the end. So that implies this will be the worst case time complexity. And if the search key is 10, what happens? So in the first iteration itself we will get the success. So the algorithm will be completed in the first case itself. So that will be the best case. So it requires only one iteration minimum, right? And when the search keys will be 10, okay, that means the first element. And if the search key is 30, what happens? So it will iterate till the third position, that means the average. So first, last and middle. So it have to iterate till the third element. So that means this will be the average case. So how much time the algorithm takes to complete its execution is called as a performance analysis or performance of algorithm, and that should be calculated with the help of these 3 notations, big O, omega and theta. So mainly this is used for calculating the growth rate, representing the growth rate of algorithm. Okay, so hope you understood this asymptotic notations. So big O, omega and theta. So growth rate is a rate at which the time complexity of the algorithm will be changing or increasing based upon the increase of input size. So it is a rate at which execution time of an algorithm increases on increase of input, and usually this complexity will be denoted with the help of asymptotic notations. So we have seen the asymptotic notations in our previous session. So I'll post the link in the description so you can go through that one. So the complexity is a time complexity, is represented using asymptotic notations. So we know that asymptotic notations, so big O, big omega and big theta, so which we call it as a worst case. Next, this is a best case scenario, and this one is a average case scenario. Now we have to see the order of growth rate. So also we have seen different types of functions, right? So different types of functions, the constant, logarithmic, okay, linear, quadratic, n log n, exponential, factorial. So like that we will be having a lot of functions, and we have to know the growth rate from smallest to the largest. That means which one will be the best and which one will be the worst. So based upon the execution time with increase of input. So that we call it as a growth rate, and in order to calculate the time complexity, we have to know the growth rate order. So if you know the order of growth rate, it will be simple while calculating the time complexity of any algorithm or any pseudocode. Now we will see the order of growth rate from smallest to largest. And always the time complexity will be represented using big O notation. That means a worst case notation, worst case scenario, right? So the order of growth rate of different functions, So from smallest to largest, I'll write here smallest to largest. So first one will be the constant. Okay, so order big O of 1. Big O of 1, it is a constant. And the next category, that means, and the next level we will be having a one more which is a log n, which is a logarithmic. And the next one is order of n, which is a linear. Next, which is a n log n. That's nothing but we can call it as a linear arithmetic. And then order of n square. N square is nothing but a quadratic. Next, order of n cube, which is a cubic. Next, order of 2 power n, which is an exponential. exponential, right? So example for this one is arithmetic operations, all arithmetic operations, okay, addition, subtraction, multiplication. And coming to the log n, it's a binary search where the search space will be reduced every time, and this is a linear search, that means searching the element in a sorted order, searching the element in unsorted order. And n log n, we can say it's a merge sort with divide and conquer. And quadratic, we can say it's a bubble sort where we are comparing two consecutive elements. And NQ, so matrix multiplication, so where we are using some three different for loops, okay, 3 for loops, right? So this is a towers of Hanoi, right? So towers of Hanoi problem. So towers of Hanoi problem comes with this exponential. Okay, so these are the functions, the names of the functions, and the example for these particular notations, right? And this is from smallest to largest. Okay, so the time taken for the constant will be less when compared to exponential, and exponential will be having more number of steps required to complete its execution when compared to the constant. So this will be from smallest to largest, and we can also call it as a best case to worst case. So already we have represented with an asymptotic notation order, that means a big O notation. That's a worst case scenario, right? So but here this will be the order, smallest to largest, and this table will be more important and will be more useful when you are trying to calculate the time complexity of any algorithm. Okay, so that's why I am writing the complete overview of all the functions, growth rate, order of growth rate, right? So hope you understood. In our further sessions we will see how to calculate the time complexities from simple code to complex code, how to calculate the time complexity of any algorithm or any pseudocode. So before going to calculate the time complexity, we'll see what are the steps we need to remember before calculating the time complexity. So the first step, we need to identify the number of blocks in algorithm or a pseudocode. So identify number of blocks in algorithm or pseudocode, right, or in a program also. So here the number of blocks means declaration can be considered as a one block, initialization statements may also be considered as one block. Similarly, iterations, the complete iterations, if it is a nested loops, then the complete nested loop should be considered as a one block. And similarly, conditional statements. So if the conditional statements used in the algorithm is if else, so both we have to consider as a single block. Okay, so first we have to identify the number of blocks, and for these two always the time complexity will be the constant. Okay, so time complexity will be constant. So constant means big O of 1. We can say constant as big O of 1. And for iterations and conditions, so here if it is a nested iterations, we have to use a multiplication for nested loops. Either it may be a for loop or a while loop. So if it is nested, then we have to use a multiplication. So we have to find out the time complexity for each and every loop and we have to multiply. Okay, so first we have to calculate the time complexity of the inner loop and the time complexity of the outer loop, and both we have to get multiplied. And if it is a conditional, then we have to choose either, because the conditional means only one block will be get executed, either if block or else block. So we have to consider only one case, either if case or else case. So we can write here, so maximum of if or else. So this is the time complexity of if block and time complexity of else block. So we have to consider only one thing. And if it is a nested if else, so calculate the time complexity of each and every block and find out the maximum among all those conditions. Right? So if our code is having some 2 conditions or 3 conditions, we have to calculate the time complexity of the 3 conditions and find out the maximum. So we have seen the growth rates from smallest to largest in our previous session. So select the maximum time complexity among this one if it is a conditional. So then what we have to do? Avoid the constants. So you can avoid all the constants. For example, if time complexity is 2n, you can avoid 2. If the time complexity is n by 2, avoid 2. Okay. If the time complexity is n plus 1, avoid 1. So like this, you can avoid all the constants in our time complexities. Okay. And simply add time complexity of all blocks. Time complexity of all the blocks. We have to add, for example, so add the time complexity of declaration, add the time complexity of initialization, add the time complexity of iterations if it is having, and add the time complexity of conditional statement if it is having, right? So add each and every block, the time complexity of all the blocks. And finally, the time complexity will be the highest order in equation. So if we apply all the addition of all the time complexity of all the blocks, the highest order will be the time complexity, final time complexity. Okay, so these are the points we have to remember before calculating the time complexity. So if you understand this one, and it will be very easy to calculate the time complexity for any type of algorithm and any type of code. And here one thing is we have to remember, so coming to the iterations, there might be a dependency or there might be an independent. So there you have to carefully find out the time complexities, right? So in the iterations we will be having the 2 categories, dependent, independent, right? So if they are independent, this process is final, right? So multiplication of nested loops. And if it is dependent, we have to trace out and we have to calculate the time complexity, right? So whatever the process we have we have explained here, the multiplication will be suitable if the iterations are independent, right? So hope you understood. the rules or the points we have to remember, so before calculating the time complexity. Now we'll see small examples, so how we can calculate the time complexity, right? So simple codes, I'll write the simple codes and I'll tell you the time complexity in this video. In our further video we'll go with the small complex, right? So the example 1, let us take for I is equal to 0, I less than or equal to n and I plus plus. So let it be some any statement is here. Now just check. So this is the block of statements need to be get executed. How many times it is going to be executed? So how many times it will be executed? So until I value starts with 0 and until I becomes less than or equal to n, that means I greater than n. Until I greater than n, this block will be get executed. For example, n plus 1 times. Okay, so n times it will be executed. If it is n plus 1, then it will be false and it will not be get executed. So it will be n plus 1 times, right? N plus 1 times. And what we have seen, so we have to avoid the constants. So avoid these constants. So the time complexity of this particular code will be order of n, big O of n. So always the time complexity will be represented using the worst case scenario, that means order of n, which gives the upper bound. So in the competitive questions, if you get this type of problems, so if you found any other time complexity like n square or order of log n log n, right, order of n cube, right, so everything will be correct for this particular thing. So because this is the worst case and it gives the upper bound of the time complexity, that means so n and greater than this order of n can be correct for this particular code. Okay, so this is the time complexity of this one, order of n. So let us take one more example. So for I is equal to 0, I less than or equal to n and I is equal to I into 2. So what happens here? How many times it will be executed? So now we have to trace. So when I is equal to 0, right? 0 less than or equal to n. If it is true, consider if it is true, I value will become, sorry, let us take 1. So I value become 2 less than or equal to n. If still it is true, I is equal to 3 less than, sorry, I becomes 2 into 2, 4, right? So 4 less than or equal to n. Now I becomes 8 less than or equal to n. I becomes 16 less than or equal to n. So like so on. So whenever I becomes k, then you can see that, see 2, this can be written as 2, this can be written as 2 power 2, this can be written as 2 power 3, this can be written as 2 power 4 and so on. So we can get it as, we can write it as 2 power k less than or equal to n. So this many times it will be repeated. So now what? So avoid this less than. So we can write it as 2k is equal to n. Now what is the k value? If you have this one, simply this is a formula logarithmic log n base 2. So the time complexity of this particular code will be log n base 2. So the time complexity is equal to, we can simply write it as order of log n. So always it will be base 2. Okay, you need not worry about that. Always it will be base 2. So log n base 2. So if it is 3, what happens? So I becomes 3 here and here it becomes 9, here it will becomes 27, and here it will becomes some 81. So here it will be 3 square, 3 cube, 3 power 4, and it will be 3 power k, and it will be log n base 3, and it will be base 3. Right? So like this we have to trace and we have to calculate the time complexity. So we'll see one more. So this is a order of n which we call it as a linear, and this is a log n which is called as a logarithmic. Now we'll check one more. For I is equal to 0, I less than or equal to n, excuse me. Again, for j is equal to 0, j less than or equal to n, j plus. And see, this is a code. Let us see. So we know that this is a nested loop. Nested loop. So not only with the for loop, we can also go with the while loop also, the same procedure. So coming with the inner loop. So how many times this inner loop will be get executed? So from 0 to n. So is there any dependency? There is no dependency because j will iterate from 0 to n, I will iterate from 0 to n. For example, if in between, n is replaced with I, okay, in the place of n if it is I, then it will be the dependency. So j should be depends on I, how much the I value, right? So that we will see in our further sessions. So now we will see only the simple things. So this is a independent, no, there is no dependency. So j will be iterating from 0 to n and I will be iterating from 0 to n. So there is no dependency. Now, so how many times if this inner loop will be executed? So n times. Then how many times the outer loop will be executed? Obviously n times. So in our first minutes we have discussed that if it is a nested loop and there is no dependency, we have to multiply the time complexity of each and every loop. So here we have to multiply, so time complexity will be order of n into n. We can call it as a n square. That's a quadratic, such type of complexities, right? So there is no dependency. And see, if the same thing happens with another for loop, for k is equal to 0, some k less than or equal to n, k plus plus, and see, for example, it is like this. The code is like this. Okay. So what happens? There is no dependency. 3 are independent. 3 loops are independent. So again calculate here, which is n times. So obviously the time complexity will be order of n into n into n, which is order of n cube, a cubic complexity, cubic function. Okay, and see, hope you understood this one. So if there is no dependency, simply we can multiply all the time complexity of each and every loop. And now consider this one and consider it is m and it is n. Then we can say the order will be m into n. The time complexity will be order of m into n. So simply we have to multiply the time complexities of each and every loop. Yes. Now, see. So we'll see. Write down some condition. If some I or any condition, write down any condition. No problem with the condition. Any condition. And inside we are writing some loop for I is equal to 0. I less than or equal to n, I plus plus. There is a code, and here again else part. Again here I am writing for j is equal to 0, j less than or equal to n, j is equal to j into 2, right? So what happened here? So this is a condition. So if it is a conditional statement, what we have done, so we have to find out the time complexity of each and every case. That means if block and else block, and we have to consider the maximum order. So what is the time complexity of this one? So only one loop is there. So this loop will be terminated till n, I value greater than n. That means n steps. So n times. What about the time complexity of this one? J is equal to 0, j less than or equal to n, j is equal to j into 2. So just now we have seen a similar example which gives the logarithmic, right? So that is the log n times, log n times. So what we have to consider? So this is not an iterative, so we should not multiply these two things, right? So this is a conditional statements. So we have to consider a maximum order, maximum order. So among these two, which one is the maximum, n or log n? So obviously we have to refer the growth rate from smallest to largest. So in that growth rate you can see n will be the largest among these two. So we have to consider this one, right? So now the time complexity of this type of problems, so which gives the time complexity order of n. So maximum of n and log n. N and log n. So which gives the this one order of n, right? So this is an iterative. This is an iterative. One more example. We will see one more example. Hope you are understood, right? So I am saying about all the different cases, right? So then you can practice on your own. See, for I is equal to 0, I less than or equal to n, I plus plus, and inside the for loop again I am writing for j is equal to 0, j less than or equal to n, j is equal to j into 2. So this is a code, right? So what happens? So both are independent, no dependency, right? Both are independent. So the time complexity of this loop will be log n. Just now we have seen, right? Log n. And the time complexity of this one will be n times. So here there is no dependency. Here these are not the conditional statements. So what we have to do, we have to multiply the time complexity of each and every loop. So the time complexity of such case, what is the time complexity? We'll get n log n. The order of big O of n log n. Big O of n log n. So this will be the time complexity. Okay, see. Last example, I'll close. So let us take void main int, let us take some I is equal to 0. For I is equal to 0, I less than or equal to n, I plus plus, and I'll write here printf welcome. Right, close. So this is a code I'm having. Now how to find the time complexity? See, this is the declaration. This will be the one block, and this is another block. So you can consider it as a block 1, block 2, and this completely comes under block 3. Okay, so this will be executed only one time. So one time, and this will be executed only one time, and this one, how many times it will be get executed? N plus 1 times, because if I becomes n plus 1, then only the loop will be terminated. So n plus 1 will also be executed. So it will be n plus 1 times. So what we have to do? So we have to add the time complexities of all the blocks. So we have to add the time complexities of 1 plus 1 plus n plus 1. So how much we get? N plus 3. And then we have to avoid the constants, right? So avoid these constants. So the time complexity will be order of n. So like this, we have to calculate the time complexity, right? So first we have to identify the number of blocks, and then we have to find out the time complexity for each and every block, and next we have to add the time complexities of all the blocks, and we'll get some equation. Avoid the constants in the equation and consider the highest degree among all the terms in the equation, so that will be the worst case time complexity. So usually we represent it as big O of n, right? So hope you understood this one. So in this session I have explained you about the complete basic problems. So in our next session we'll move on with a little bit complexity, right? The code with a little bit complexity. So we'll see some problems, and then you will be getting a complete idea about how to calculate the time complexity, and you have to keep on tracing the problems, and you have to solve the problems. Then you will be strong in finding the time complexity of any kind of algorithm or a problem. So in our previous session we have seen a few examples, so how to calculate the time complexity, and today also we'll see a few examples. And before going to the examples, let us recall the procedure. So first of all, we have to consider an algorithm or a pseudocode and find out all the blocks, how many blocks, the number of blocks available in that particular code. And once you find out the blocks and find out the time complexity for each and every block, and then add time complexity of every block, and then you will be getting one equation, and from that equation you have to consider only the highest degree based upon the growth rate, right? So by following the same procedure, we have seen a few examples in our previous session, and today we're going to see a few more examples. Yes, see, so the session will be again on time complexities. So let us take one code for I is equal to 1, I less than or equal to n, I plus plus, for j is equal to 1, j less than or equal to I, j plus plus, and let it be any sort of statements here. So you can see here there is a dependency. Okay, so how many times this will be repeated? How many times this will be repeated? So forget about this one, outer loop. How many times the outer loop is repeated? Obviously it will be repeated for n times. Obviously it will be repeated for n times, right? Because I is equal to 1 and 1 to n. Yes. Coming to the inner loop, how many times it will be repeated? So that depends upon I value. So in such case, we have to trace for a few iterations so that we can get an idea how many times it will be iterated. Now let us trace the problem. So when I is equal to 1, how many times j will be repeated? So j is equal to 1, so j will be repeated with, I'll write here. So j will be repeated one time. When I is equal to 2, that means second iteration, I is equal to 2, j will be repeated. You can see j less than or equal to 2, that means 1 and 2 times. When I is equal to 3, then j will be repeated. So 3, 1, 2 and 3 times. Okay, so you can say it here, how many times it will be repeated? 1 time plus 2 times plus 3 times plus and so on. Okay, how many times? 1 plus 1 time, 2 time, 3 time, 4 time. You can observe 1, 2, 3, and again if you trace the for I is equal to 4, it will j will be repeated for 4 times. 4 times. So this is nothing but our sum of n natural numbers. Sum of n natural numbers, 1 plus 2 plus 3 plus and so on. So obviously this will be repeated with n into n plus 1 divided by 2 times. So that will be n square plus n divided by 2. So obviously what happens? This will be removed, the highest order will be n square. N square. So like this we have to trace the problem if there is any dependency. If there is no dependency, obviously we can directly go with it. If there is a dependency, we have to trace it and we have to find out how many times the loop will be iterated. So you can observe here. So we'll go with a few more examples. Now, let us check with one more example. See, I is equal to 1, I less than or equal to n by 2, I plus plus. For j is equal to 1, j less than or equal to n by 4, j plus plus. So if you consider this type of code, so this how many times it will be repeated? Obviously there is no dependency. So I iterating from 1 to n by 2, j is iterating from 1 to n by 4. So there is no dependency. So if there is no dependency, we can simply multiply both the things. So this will be n by 2 times and this will be n by 4 times. And what we have to do? We have to multiply. So order of n by 2 into n by 4. So that will be the order of this particular problem. Okay, so hope you understood. If there is a dependency, so we should not multiply, but we have to trace the problem. We have to find out few iterations, and we can find the number of number of times the loop will be iterating, right? So just like in our previous example. So here there is no dependency. So obviously we can find out the time complexity of each and every loop and we can multiply. So in our previous example we are not multiplying that one, right? So because there is a dependency, so we should not multiply. Okay, so hope you understood. So if coming to the loops, nested loops, there are two things. One is dependency and no dependency. So if there is a dependency, trace and find. And if there is no dependency, multiply time complexity of each block or each loop. Okay, right? So here there is no dependency, we are just multiplying. So we'll see a few more examples with similar. So here I have taken two examples. So we'll see the time complexity for these two examples. So in the for loop we have taken the two initializations here, one condition and two updations, right? So let us trace and find out. So here in this case, okay, so when I is equal to n, then j will be 0 and condition n greater than 0 and the updation will be the next. Okay, here I'll write j is equal to 0 and j will become 1. J becomes 1 and I becomes n by 2. So n by 2 greater than 0. So observe. Next, I value will become n by 4. So n by 4 greater than 0. Next, I value n by 8. Okay, n by 8 greater than 0. So for every iteration, n will be reducing to half. N will be reducing to half. So what we can say, n by 2 power k greater than or equal to 0. Okay, greater than or equal to 0. So this we can simply write it as n is equal to 2 power k, okay, which we can call it as k is equal to log n base 2. So already we have discussed it, the same situation we got it, right? So the time complexity of this one will be, time complexity will be order of log n base 2. Okay, so like that we can trace it and we can find out the number of iterations that happens here. Okay, hope you understood this one. So n, and every time, so the comparison is on I greater than 0. Okay, so I value is keep on reducing to half. So while studying about the time complexity, different time complexities, we have studied the log n. That means if the search space or the space is reduced gradually to half for every iteration, that will be the logarithm n. So that will be the log n base 2, the order of log n, right? And coming to this example, let us take the same thing. Let us follow the same thing. So here I is equal to 0 and j is equal to n, and see n greater than 0. N greater than 0, true. Again, I becomes half, so I by 2. J becomes 1, so j becomes n plus 1, so n plus 1 greater than 0. And I becomes I by 4, and you can eliminate I because we are comparing the condition. We have to, so when the loop will be terminated, that depends upon the condition. So we have to consider the condition. So here the condition, the variable is j. So focus on the j. And in the above example, you can see the condition, the variable will be on I, right? So we have to focus on I. So you need not bother about j, whether it is incremented or decremented. So because whenever the I value becomes greater than 0, then only it will be iterating. Whenever the I value becomes less than 0, immediately it will be terminated. And I value will be decrementing with a half for every iteration. So similarly here also we are taking two variables, and one variable is decrementing by half and one variable is incrementing, and we are using only one variable in the condition, right? So we have to focus on the condition because based upon the condition only the loop will be terminated. So in the condition we are using j. So focus on j, not on I. So j is equal to n plus 1, n plus 1 greater than 0. So n plus 2 greater than 0, j is equal to n plus 2, n plus 3 greater than 0, so j is equal to n plus 3, and so on. So what happens? Always the j value will be keep on incrementing, and always the n value will be greater than 0, right? So the loop will not be terminated. So this will be the infinite loop. So if it is an infinite loop, the time complexity is undetermined. The time complexity of any infinite loop will be undetermined. So we can't determine, right? So we can't assume, or we can't calculate the time complexity because this is an infinite loop. Okay, so simply iterate a few steps and you can easily guess the number of iterations it will apply or it will follow. Okay, so we'll see a few more examples. So let us take one more example, and here also we are having two for loops, nested loop. So first we have to, so if it is a nested loop as we have discussed just now, so first we have to think about the dependency, whether there is any dependency to iterating the inner loop. So you can see the inner loop j will be varying from 1 to n, and outer loop I is varying from 1 to n. So there is no dependency. So we can calculate the time complexity of the inner loop and we can multiply it with the time complexity of the outer loop. So what is the time complexity of the outer loop? So in our previous sessions we can see the similarity, right? So the time complexity is log n. So if anyone missed about the previous session, so that will be available in the description playlist, so you can go through and you can easily understand how we are getting the log n base 2. And in this session itself we have taken this example and this came it as a n by 2. Okay, so that means we can avoid the constant, so n. So the time complexity of this one, the time complexity of this type of algorithm will be order of, multiply both one, n log n base 2. So this will be the time complexity. Okay, this is one example. So let us see the last example. See, let us see this example. I is equal to 1, k is equal to 1, and we have initialized two variables. We are checking the condition k less than or equal to n, and we are iterating the two statements here. And see, here the condition depends upon the k value and k value depends upon the I value. So there is a dependency. Hope you understood. So here the condition is k and n. So k value depends upon I because we are updating the k with I value, right? So I value will be keep on incrementing. Now we have to find out the time complexity. Trace here. So when I is equal to 1, then k will also be 1, and so 1 less than or equal to n. Then I becomes 2 and k becomes 3. So 3 less than or equal to n. Again, I is equal to 3. Okay. Now k is equal to k plus I. What is the key? 3. I is 3. 6. 6 less than or equal to n. Next, I is equal to 4 and k will be k plus I. K is 6 and I is 4. 10. So 10 less than or equal to n, and so on. So you can trace it. How we are getting this one? So you can see for I is equal to 1, okay, so 1, I is equal to 2, it is 3, I is equal to 3, it becomes 6, and I is equal to 4, it becomes 10. That implies sum of all the previous numbers. You can see when I is equal to 2, 2 plus 1, 3, I is equal to 3, 3 plus 2 plus 1, 6. You can observe here. So I. So that will be only 1, and here 2 plus 1, and here 3 plus 2 plus 1, and here 4 plus 3 plus 2 plus 1. You can observe. So 4, 3, 2, 1. So I values will be keep on adding. So that means sum of n natural numbers. So this can be written as I into I plus 1 divided by 2 less than or equal to n. Okay, so you can simply write it because this is nothing but sum of n natural numbers. So avoid the constants. So you can avoid the constants. So it becomes I square plus I less than or equal to n. I square plus I less than or equal to n. So simply you can consider the highest grade. So I square is equal to n and I becomes root en. So that implies the complexity of this one, the time complexity of this particular code will be order of root n. Right? So like this we have to trace and we have to find out how we are getting the condition, and from that we can get the time complexity. Right? So hope you understood this one. So previous examples, in our previous session we have seen all the simple examples, and in today's session we have gone with a few complex examples. So with this you might be knowing how to calculate the time complexities, and definitely by practicing more problems you will be getting strong with calculating the time complexity of any kind of algorithm or any kind of pseudocode. So in our previous session we have seen a few examples, so how to calculate the time complexity, and today also we'll see a few examples. And before going to the examples, let us recall the procedure. So first of all, we have to consider an algorithm or a pseudocode and find out all the blocks, how many blocks, the number of blocks available in that particular code. And once you find out the blocks and find out the time complexity for each and every block, and then add time complexity of every block, and then you will be getting one equation, and from that equation you have to consider only the highest degree based upon the growth rate, right? So by following the same procedure, we have seen a few examples in our previous session, and today we're going to see a few more examples. Yes, see, so the session will be again on time complexities. Time complexity. So let us take one code for I is equal to 1, I less than or equal to n, I plus plus, for j is equal to 1, j less than or equal to I, j plus plus, and let it be any sort of statements here. So you can see here there is a dependency. Okay, so how many times this will be repeated? How many times this will be repeated? So forget about this one, outer loop. How many times the outer loop is repeated? Obviously it will be repeated for n times. Obviously it will be repeated for n times, right? Because I is equal to 1 and 1 to n. Yes. Coming to the inner loop, how many times it will be repeated? So that depends upon I value. So that depends upon I value. So in such case, we have to trace for a few iterations so that we can get an idea how many times it will be iterated. Now let us trace the problem. So when I is equal to 1, how many times j will be repeated? So j is equal to 1, so j will be repeated with, I'll write here. So j will be repeated one time. When I is equal to 2, that means second iteration, I is equal to 2, j will be repeated, you can see j less than or equal to 2, that means 1 and 2, 2 times. When I is equal to 3, then j will be repeated, so 3, 1, 2 and 3 times. Okay, so you can say it here, how many times it will be repeated? 1 time plus 2 times plus 3 times plus and so on. Okay, how many times? 1 plus 1 time, 2 time, 3 time, 4 time. You can observe 1, 2, 3, and again if you trace the for I is equal to 4, j will be repeated for 4 times. 4 times. So this is nothing but our sum of n natural numbers. Sum of n natural numbers, 1 plus 2 plus 3 plus and so on. So obviously this will be repeated with n into n plus 1 divided by 2 times. So that will be n square plus n divided by 2. So obviously what happens? This will be removed, the highest order will be n square. So like this we have to trace the problem if there is any dependency. If there is no dependency, obviously we can directly go with that. If there is a dependency, we have to trace it and we have to find out how many times the loop will be iterated. So you can observe here. So we'll go with a few more examples. Now let us check with one more example. See, I is equal to 1, I less than or equal to n by 2 I plus plus. For j is equal to 1, j less than or equal to n by 4 j plus plus. So if you consider this type of code, so this how many times it will be repeated? Obviously there is no dependency. So I iterating from 1 to n by 2, j is iterating from 1 to n by 4. So there is no dependency. So if there is no dependency, we can simply multiply both the things. So this will be n by 2 times and this will be n by 4 times. And what we have to do? We have to multiply. So order of n by 2 into n by 4. So that will be the order of this particular problem. Okay, so hope you understood. If there is a dependency, so we should not multiply, but we have to trace the problem. We have to find out few iterations, and we can find the number of number of times the loop will be iterating, right? So just like in our previous example. So here there is no dependency. So obviously we can find out the time complexity of each and every loop and we can multiply. So in our previous example we are not multiplying that one, right? So because there is a dependency, so we should not multiply. Okay, so hope you understood. So if coming to the loops, nested loops, there are two things. One is dependency and no dependency. So if there is a dependency, trace and find. And if there is no dependency, multiply time complexity of each block or each loop. Okay, right? So here there is no dependency, we are just multiplying. So we'll see a few more examples with similar. So here I have taken two examples. So we'll see the time complexity for these two examples. So in the for loop we have taken the two initializations here, one condition and two updations, right? So let us trace and find out. So here in this case, okay, so when I is equal to n, then j will be 0 and condition n greater than 0 and the updation will be the next. Okay, here I'll write j is equal to 0 and j will become 1. J becomes 1 and I becomes n by 2. So n by 2 greater than 0. So observe. Next, I value will become n by 4. So n by 4 greater than 0. Next, I value n by 8. Okay, n by 8 greater than 0. So for every iteration, n will be reducing to half. N will be reducing to half. So what we can say, n by 2 power k greater than or equal to 0. Okay, greater than or equal to 0. So this we can simply write it as n is equal to 2 power k, okay, which we can call it as k is equal to log n base 2. So already we have discussed it, the same situation we got it, right? So the same, the time complexity of this one will be, time complexity will be order of log n base 2. Okay, so like that we can trace it and we can find out the number of iterations that happens here. Okay, hope you understood this one. So n and every time, so the comparison is on I greater than 0. Okay, so I value is keep on reducing to half. So while studying about the time complexity, different time complexities, we have studied the log n. That means if the search space or the space is reduced gradually to half for every iteration, that will be the logarithm. So that will be the log n base 2, the order of log n. right? And coming to this example, let us take the same, let us follow the same thing. So here I is equal to 0 and j is equal to n, and see n greater than 0, n greater than 0, true. Again I becomes half, so I by 2, j becomes 1, so j becomes n plus 1, so n plus 1 greater than 0, and I becomes I by 4, and you can eliminate I because we are comparing the condition. We have to, so when the loop will be terminated, that depends upon the condition, so we have to consider the condition. So here the condition, the variable is j, so focus on the j, and in the above example you can see the condition, the variable will be on I, right? So we have to focus on I. So you need not bother about j, whether it is incremented or decremented. So because whenever the I value becomes greater than 0, then only it will be iterating. Whenever the I value becomes less than 0, immediately it will be terminated, and I value will be decrementing with a half for every iteration. So similarly here also we are taking two variables, and one variable is decrementing by half and one variable is incrementing, and we are using only one variable in the condition, right? So we have to focus on the condition, because based upon the condition only the loop will be terminated. So in the condition we are using j, so focus on j, not on I. So j is equal to n plus 1, n plus 1 greater than 0, so n plus 2 greater than 0, j is equal to n plus 2, n plus 3 greater than 0, so j is equal to n plus 3, and so on. So what happens? Always the j value will be keep on incrementing, and always the n value will be greater than 0, right? So the loop will not be terminated. So this will be the infinite loop. So if it is an infinite loop, the time complexity is undetermined. The time complexity of any infinite loop will be undetermined. So we can't determine, right? So we can't assume, or we can't calculate the time complexity, because this is an infinite loop. Okay, so simply iterate a few steps and you can easily guess the number of iterations it will apply or it will follow. Okay, so we'll see a few more examples. So let us take one more example, and here also we are having two for loops, nested loop. So first we have to, so if it is a nested loop, as we have discussed just now, so first we have to think about the dependency, whether there is any dependency to iterating the inner loop. So you can see the inner loop j will be varying from 1 to n, and outer loop I is varying from 1 to n. So there is no dependency. So we can calculate the time complexity of the inner loop, and we can multiply it with the time complexity of the outer loop. So what is the time complexity of the outer loop? So in our previous sessions we can see the similarity, right? So the time complexity is log n. So if anyone missed about the previous session, so that will be available in the description playlist, so you can go through and you can easily understand how we are getting the log n base 2. And in this session itself we have taken this example, and this came it as a n by 2. Okay, so that means we can avoid the constant, so n. So the time complexity of this one, the time complexity of this type of algorithm will be order of, multiply both one, n log n base 2. So this will be the time complexity. Okay, this is one example. So let us see the last example. See, let us see this example. I is equal to 1, k is equal to 1, and we have initialized two variables. We are checking the condition k less than or equal to n, and we are iterating the two statements here. And see, here the condition depends upon the k value, and k value depends upon the I value. So there is a dependency. Hope you understood. So here the condition is k and n. So k value depends upon I, because we are updating the k with I value, right? So I values will be keep on incrementing. Now we have to find out the time complexity. Trace here. So when I is equal to 1, then k will also be 1, and so 1 less than or equal to n. Then I becomes 2 and k becomes 3. So 3 less than or equal to n. Again, I is equal to 3. Okay. Now k is equal to k plus I. What is a key? 3. I is 3. 6. 6 less than or equal to n. Next, I is equal to 4 and k will be k plus I. K is 6 and I is 4. 10. So 10 less than or equal to n, and so on. So you can trace it, how we are getting this one. So you can see for I is equal to 1, okay, so 1, I is equal to 2, it is 3, I is equal to 3, it becomes 6, and I is equal to 4, it becomes 10. That implies sum of all the previous numbers. You can see when I is equal to 2, 2 plus 1, 3, I is equal to 3, 3 plus 2 plus 1, 6. You can observe here. So I, so that will be only 1, and here 2 plus 1, and here 3 plus 2 plus 1, and here 4 plus 3 plus 2 plus 1. You can observe. So 4, 3, 2, 1. So I values will be keep on adding. So that means sum of n natural numbers. So this can be written as I into I plus 1 divided by 2 less than or equal to n. Okay, so you can simply write it because this is nothing but sum of n natural numbers. So avoid the constants. So you can avoid the constants. So it becomes I square plus I less than or equal to n. I square plus I less than or equal to n. So simply you can consider the highest grade. So I square is equal to n and I becomes root en. So that implies the complexity of this one, the time complexity of this particular code will be order of root n, right? So like this we have to trace and we have to find out how we are getting the condition, and from that we can get the time complexity, right? So hope you understood this one. So previous examples, in our previous session we have seen all the simple examples, and in today's session we have gone with a few complex examples. So with this you might be knowing how to calculate the time complexities, and definitely by practicing more problems you will be getting strong with calculating the time complexity of any kind of algorithm or any kind of pseudocode. So in our previous sessions we have seen how to find out the time complexity of any kind of algorithm, as well as the asymptotic notations, that is a big O, big theta and big omega notations, which will give the worst case, best case and the average case complexities. And coming to this amortized analysis, this is mainly used to analyze the average performance of the algorithm for a set of operations. Okay, so it is basically to find out the average time complexity. Okay, so that is also for a set of operations. So I'll write here, it is used to analyze average performance of an algorithm. This is most important. Next, for a set of operations. So that means it will calculate the average cost for all the set of operations. So calculates average cost of all operations. So for example, if an algorithm consists of 10 instructions, okay, or 10 operations, if some operations gives the worst case and some operations gives the best case, and we need to average the cost of all the operations, so that will give the amortized analysis. For example, so let us take a person who runs a family, and if he needs an amount, the monthly expenses, what is the monthly expenses, and how much amount he requires to run a family. Okay, so for example, in January, the monthly expenses, so I write here monthly expenses. So the monthly expenses are some 10,000 rupees, and in the month of February, let it be some 8,000 rupees. In the month of March, let it be some 6,000 rupees. So according to these statements, okay, according to this content, how much a man can run a family with a amount, right? So obviously we will say it will be 10,000. That will be the worst case. So here the amortized analysis means averaging the cost of each and every operation. So you can average all these things. So what is the average of all these things? So 10,000 plus 8,000 plus 6,000 divided by 3, because we are calculating for the 3 months. So it will be, so 10, 18, 24. So 24,000 by 3, which is nothing but 8,000. So a man can have an 8,000 rupees to run a family on an average of 8,000. So in the January, he might be having a few expenses, more expenses. In the month of March, there will be a little bit of expenses, right? So this average is 8,000, which is less than the worst case. So this type of thing, we call it as amortized analysis. So the same thing we have to do for algorithm. Okay, so based upon the operation, we should not consider the highest complexity. So we need to calculate the average cost of all the operations so that we can get the amortized time complexity or amortized analysis. Right? Now we'll take an actual example. We'll consider one data structure array and we'll see what is the complexity, worst case complexity to insert an element into a dynamic array. And the same thing will apply the amortized analysis and we'll compare the time complexities of both. Right? Yes. So let us see that one. So let us take an example as an array. See the worst case time complexity. So complexity of element insertion into an array. Obviously, it will be some order of n, right? So one element. If the same thing applies for multiple elements, so n elements insertion, so the time complexity will be n into some order of n, which will be order of n square, right? So this is the worst case time complexity for inserting n elements into an array. So this is the order of n square. I'll write here order of n square, right? So this is the worst case time complexity. Now calculating this amortized analysis. Okay, so that means we have to trace each and every operation and we have to find out the cost and then we have to average all the different costs. See what happens. So if I write here insertion, element insertion, and here I'll write the size of array, and here I'll write it as a cost. Okay, cost. So one thing we have to remember, the element can be easily inserted into an array, and if the array is full, what we have to do? We have to double the array and we have to copy all the elements into the array and then we have to insert it. So the complexity or the cost will be 1 if array is not full or overflow, we can simply say, right? So if it is full, what we have to do? So size should be double. Okay, size should be double plus copy all elements, because all the elements should be occupied in continuous memory locations, plus element insertion. So three things will be happen if the array is full. That means we have to increase the size of an array. So with the help of different functions, we know that in C we are having some dynamic memory allocations, so we can increase the memory, and in Java we can use a new keyword to increase the size. So like that, whatever it may be, so we have to double the size of the array, and next step we have to copy all the elements, because every element should be in the continuous memory location, and then only we have to insert the element. So this happens, see, I'll write here, don't get confused, and it will be 1 if array is not full. This should be happens if array is full, that means overflow. If array is full, size should be doubled, that is the first one. Copy all the elements, that the second one. Elements insertion will be the next one. Now, so what happens if you are inserting one element and if the array size is 1? Okay, so if the array size is 1, so simply we can insert and the cost will be 1. And if you want to insert 2, the array size is 1, there is no empty, I mean the array is full. Now it should be double. Double means 2. So here it is 1 and here it is 2. So then insertion of copy the element. First we need to copy the element. So 1 plus how many elements? So sorry. The first thing is double the size. So now the size of array 2. Next, copy all the elements. One element will be copied and element of insertion 1. So the cost will be this one. And coming to the third, insertion of the third one. So there is a blank. Okay, so the array is not full because, sorry. Yes, so array is full. So array is full means third element can't be inserted into the size of array 2. So then that should be increased. So 1, 2 and size should be increased. Size should be double. So 2, now it should be 4. Copy all the elements. How many elements? 2 elements. 2 elements should be copied plus element to be inserted 1. So here it is. Coming to the 4, element 4. So here the array is not full. So obviously we can simply insert the element. So 1, 2, 3, 4. So the cost is 1. Insertion of element. If array is not full, the cost is 1. Okay. And then fifth element. So there is no free space. So the array is completely full. What we have to do? Size should be doubled. So now the size of array will be 8. Right. So size should be doubled. So it will be 8 plus copy all the elements. How many elements? 4 elements. 4 elements will be copied. 1, 2, 3, 4. And 1 element should be inserted. 1. So 5. Okay, and then for 6, 7 and 8, you can observe the array is not full. So obviously 6, 7 and 8, the cost will be 1, 1, 1, right? Because full. And if it is again ninth element, the cost will be how much? So the array is full, so it will be 16. First size should be double. 16 plus, copy all the elements. 8 elements should be copied and plus 1. So if you want to insert the 9 elements, so that will be the cost. So like this, we have to analyze each and every step. And what we have to do next? We have to average the cost of all the operations. So this will be the first operation, second operation, third, 4, 5, 6, 7. Okay, so different operations, all are the different operations. So we have to apply the same thing for n elements, and we have to take the average. Because of this amortized analysis, this is the average performance of an algorithm. Now, let us consider. So we have find the cost of all the operations, and this will be keeps on moving, right? So I have to average. So average 1 plus, let us take 2 plus 1 plus 1 plus, you can apply 4 plus 2 plus 1 plus 1 plus 8 plus 4 plus 1 plus 1 plus 1 plus 1 plus 1. So like this and so on. It will be like, it will be keeps on moving and divided by n, because we have to average. So these are all the cost of n operations. So you can observe, we can replace this with, okay, we can replace this with, so 1 plus 2 plus 4 plus 8 plus and so on, and similarly plus see 1, 2, 4, 8, again 1, 2, 4 and so on, and again we will get 8 here, right? So again 1 plus 2 plus 4 plus 8 plus and so on, plus finally we will get all ones, right? And so on, plus we will get all ones divided by n. So this also keeps on moving. Okay, so we'll get only these type of iterations. So we'll get 1 plus 2 plus 4 plus 8, again 1 plus 2 plus 4 plus 8, again 1 plus 2 plus 4 plus 8, again so on, all ones. We can write like this. So we know the complexity for this particular series. Okay, see, if you want to get like this, simply you can analyze I is equal to 1, I less than or equal to n, I is equal to I into 2. So we have already seen such kind of time complexity, so which will be incremented with a 2 times, so that we call it as a log n base 2. So simply we can replace this with log n base 2, and this is also log n base 2, and this is total n terms. So n times 1 will be added, so n terms. So what we can write here, order of log n base 2 plus order of log n base 2 plus n divided by n. So what happens here? 2 log n base 2. So this becomes 2 log n base 2 plus n divided by divided by n. So you can see we have to consider the highest degree. So among log n and n, which will be having the highest degree? If we are having some function and we are trying to calculate the time complexity, we have to find out the highest degree. So what is the highest degree in this equation? So n, according to the growth rate. So just visit our previous sessions so that you will be understanding how we got this log n and how we are selecting this n, right? So calculating the time complexities and the growth rate. So these 2 sessions you just go through so that you will be getting a clarity about that one. So I'll share the complete playlist in the description box. Okay, right. So we have to consider this one, and this will becomes order of n divided by n, which is nothing but order of 1. See, order of 1. So the same problem, what's the worst case time complexity is of order of n square. And if you are using this amortized analysis, particularly the aggregate method, so this amortized analysis is also having a different methods, right? So counting method, then aggregate method, potential method, right? So this is an aggregate method. So here we have to calculate the cost of each and every operation, and then we have to perform the average so that we'll get the amortized time complexity, which we call it as an average performance of an algorithm over a set of operations. That's the most important. Okay, so order of n, and this is order of 1. This is amortized time complexity. Amortized time complexity. And this is a worst case time complexity. Worst case time complexity. Right? So there you can find the difference. So worst case time complexity of order of n square, and where amortized time complexity will be the order of n, inserting an element into a dynamic array. So this problem is for inserting an element into a dynamic array. So previously we are having some order of n square. So in our previous example we have seen, so if a person needs some monthly expenses to run a family, so how much he requires to run a family on an average, we have find out, we have calculated that average. So the same process we have to do the here, and that we call it as a amortized analysis, the average performance of an algorithm over a set of operations. Divide and conquer strategy. Divide and conquer. So in today's session we'll see the introduction, what is about this divided and conquer strategy, and what are the different applications which will follow this strategy, divide and conquer, in order to solve the problem. So in our first sessions we have seen there are different strategies like divide and conquer, dynamic programming, greedy method, etc., in order to solve any problem. So the main goal is to achieve the optimal solution, right? The better solution. So one of the strategies is divide and conquer, and so here there will be a 3 parts: divide, conquer and combine. So for the first part is a divide part, so where the complete problem can be decomposed into multiple sub-problems. So first the problem will be divided into multiple sub-problems. So that will be done in this divide part. Okay, so the problem is decomposed to multiple sub-problems. The second part is a conquer. So as the name itself indicates, it's a conquer. So conquer means applying some recursive calls or recursive procedure to solve each and every sub-problem, right? So the second part, conquer, so providing solution or finding the solution for every sub-problem. So finding solution for every sub-problem. And there is also a third part which is called a combine. So after finding the solution for all the sub-problems, the next part will be the combine. So we have to combine the solutions of all sub-problems to get the main solution. So the third part will be combine. So the name itself indicates, combines means so joining or integrating the solutions of all sub-problems. So combining solutions of all subproblems. Right? So these are the 3 steps involved in this divide and conquer. Usually some materials or some textbooks or some online information will be having as a D and C, right? So it will be represented as a D and C, divide and conquer, right? So, and the applications, what are the different applications that follows this particular divide and conquer? So the main applications which follows this divide and conquer are binary search, so where the complete element should be in a sorted order, so that we have to find the middle element and we are trying to compare the search element with the middle element, so that we are deciding whether the search element is available at the left part of the middle element or the right part of the middle element, right? So the search space in the second iteration, the search space will be reduced to half. So in the second iteration, we will follow the search space from either first to middle or middle to last. So that approach will follow this divide and conquer. So first we are dividing the problem, and again we are applying the same procedure, and we are, based upon the result, we are proceeding with the further division, or we are combining the solutions. So first one will be the binary search. Next, quick sort. So as we know that sort means arranging the elements in a ascending order or either descending order. Usually the elements will be arranged in a ascending order. So here also we will be having a lot of elements. So usually that will be stored in an array. So we have to consider a pivot element, and based upon the pivot element, all the elements that are less than the pivot should be arranged towards the left side, and all the elements greater than the pivot elements will be arranged towards the right side. Now the complete array is divided into 2 halves, left half and right half, and again from the left half again we have to select the pivot element, and again based upon the pivot we are arranging 2 sub-arrays. And coming to the rightmost array, again we are dividing the rightmost array based upon the pivot 2 sub-arrays. So this is again the process which follows the divide and conquer. So dividing the problem and providing the solution, finding the solution, and again combining all the solutions. So quicksort is also an application which follows this divide and conquer methodology. And merge sort. So this is also one sorting technique. So where here also the elements will be arranged in a sorted order. So here first of all we have to divide the complete array into 2 halves, and further again this left sub array and right sub array will be further divided into again 2 halves until it reaches to the two elements, right? So then again the process will be from bottom to top. So for every sub problem, for every sub array, we have to arrange the elements, we have to compare the elements, and we have to arrange the elements in a sorted order, and again we have to merge 2 arrays, and again we have to compare, and we have to apply the sorting technique, and again we have to apply we have to combine both the arrays. So merge sort means again first we are going to divide the complete array into sub arrays, and again we are just combining all the merged elements, all the sorted elements. So merge sort is also one application that follows this divide and conquer. So don't worry about it. So one by one we'll solve each and everything. So we'll see how we have to apply the divide and conquer. And one thing you have to remember, either you are using the binary search or a quick sort or a merge sort. So two things are common. So one is formula. So formula means at what point we have to divide the complete problem into sub problems. So according to which condition we have to divide it. Okay, so that is a formula, because in binary search we are finding the middle element, and based upon the middle element we are comparing with the search element, and then we are dividing. Coming to the quick sort, we are finding the pivot element, and based upon the pivot element we are dividing. And coming to the merge sort, this is also we are finding the middle element and we are dividing this complete array into sub-array. So we required some formula to divide the problem into sub-problems. And the next one, stop case. So stop case means how far we have to divide the problem into sub-problems. So at particular time we have to stop that division. So that is most important, stop case, right? So identifying the stop case or a base condition is somewhat difficult. So that may be one disadvantage of divide and conquer. And also not all applications will follow this divide and conquer, and this will be not suitable for all the applications to get the optimal solution. So right, so you can see these are the few applications. So I'll draw the simple diagrammatic representation about these three parts, right? So you can see first complete problem. So one advantage is complex problems can be easily solved by using this divide and conquer. So for example, this is a problem. This is a problem. So this is again divided into two subproblems. Right? So subproblem 1 and subproblem 2. This is a complete problem. Right? So based upon the formula and based upon the stop case, again this subproblem can be divided into further. Right? So for example, again this is divided. So problem 1, so problem 2, and again so problem 1. So this process will be keeps on moving, right? It keeps on moving. So once it was done, now finding the solution, and here also finding the solution, and here also we'll be having solution, and here also we'll be having solution. Now division is completed and conquer is completed, right? So up to here that is a divide part, and up to here this is a conquer part. That means finding the solutions, and after that we have to combine both the solutions. Right? So this is a combined part. So again here we have to combine both the solutions, and later again we have to combine complete solution, right? So this part is nothing but combine. So three parts: divide, conquer and combine. Dividing the problem into subproblems, right? So this is a part, and this is a conquer part, and this will be the combine part. Okay, this is completely the combined part. So identifying the problem, subproblem, and applying the same procedure in order to find the solution, finding the solution and combine the solution. So finally we'll get the complete solution for this particular problem. Okay, so the same approach will be applied for, we have seen the applications merge sort, quick sort, or towers of Hanai problem, and as well as the binary search. Okay, multiplication methods, finding the minimum and maximum elements. We can also use the same strategy in order to find the maximum and minimum elements. Alright, so hope you understood the complete introduction. What is this divide and conquer strategy? So to get the optimal solution. So let's stop here, and in our further sessions we'll see each and every application that follows this divide and conquer and how we can get the optimal solutions. Right? So in this session we'll see one application, that is finding the minimum and maximum element from a given array. using this divide and conquer methodology, right? So usually this is called as a min and max algorithm. Min and max algorithm. So the problem statement is to find the minimum element and a maximum element from the given array, right? So using this divide and conquer. So absence of this divide and conquer, so how can we find the minimum and maximum value? So for example, array is having some 5 elements, and let us assume these elements are not in a sorted order. Okay, so not in sorted order. So what happens? So in order to find the minimum element, how many comparisons we require? So we have to compare the first element with all the other elements, whether it is a minimum value or a maximum value. If it is a maximum value, we have to swap, right? So finally we require 4 comparisons. 4 comparisons, right? So similarly, in order to find the maximum also, it requires 4 comparisons. 4 comparisons. And if array is having some n elements, so in order to find the minimum value, it requires n minus 1 comparisons. And for finding the maximum value also requires some n minus 1 comparisons. So finally, if you want to find minimum and maximum in the same algorithm, it requires n minus 1 plus n minus 1. That implies 2n minus 2 comparisons are required. So if the elements are not in a sorted order, right? If the elements are not in a sorted order, so in order to find this minimum and maximum elements, we require some 2n minus 2 comparisons. So obviously the time complexity will be order of n, because we need to avoid the constants, right? So the time complexity will be order of n itself. But practically, how many comparisons were we required? So 2n minus 1 in the absence of divide and conquer. This is a normal method, right? So remember this one. So 2n minus 2 comparisons. Okay, conventional model, or we can call it as a linear model. Now we'll see how many comparisons we required if we solve the same problem by using a divide and conquer, right? So that means dividing the problem into subproblems and solving each subproblem using recursion, and then combining the solutions of all subproblems, right? Now let us see one by one. In this session, I'll mainly focus on example. First, we'll see the example how we can find the minimum and maximum element from the unsorted array using divide and conquer, and then we'll see the algorithm. We'll write the algorithm, okay, how we can based upon the example, and then we'll find the time complexity, right? So obviously the time complexity will be order of n, that's a no doubt, but we'll see how many comparisons it requires if we solve with the divide and conquer. Okay, so in linear we are having some 2n minus 2. Now we'll see the comparisons, right? So you will see in terms of comparisons how many comparisons it requires, right? So I'm going to cover all these 3 in today's session, right? Yeah, let's start with an example. So we'll take a few elements, so random elements, so the elements are not in a sorted order, right? So I'll take some 40, 60, 50, 30, 20, and let us take it 10. right? So there are a few elements. So usually 6 elements. We are considering the 6 elements. Now what we have to do? We have to divide it into sub-problems. For division, here we are taking the formula as a middle element, right? So 2 things we have to remember. In our previous session we have discussed about that one. 2 things, that is, which criteria we need to consider to divide the complete problem, and the second one, the stop condition. So at which position we have to stop the recursion. That means we have to stop the division, right? So the formula is a middle value. We need to find the middle value, right? So let us consider it as a low, and let us consider it as a high, and let us consider the index values 0, 1, 2, 3, 4 and 5. So this is an array. Okay, this is an array and these are the index values, and low is initialized to 0 and high is initialized to 5, right? That means n minus 1 if n is equal to 6. Now find out the middle value. So I'll write here middle is equal to, so middle value how we can get? Low plus high divided by 2. So here how much we get? 0 plus 5 divided by 2. How much we get? 5 divided by 2. So we need to consider only integer. So it will be 2. We need to consider only integer. So we need to divide the complete problem into 2 sub arrays. That means complete array into 2 sub arrays. So the first array will be from 0 to 2. That means low to mid. And the second array, what is the second array? Obviously the second array will be from 3 to 5. Usually we call it as a mid plus 1 to high. So based upon the middle value, we are going to divide the complete array into 2 sub arrays. Now consider, so let it be, so 40, 60, 50. So 40, 60 and 50. And here also the second array consists of 3 elements. So what are the 3 elements? 30, 20, 10. 30, 20, 10. So again we have to repeat the same process. That means recursion should be done. Recursively we have to solve each and every problem. So we are having the complete problem, and after first step we are having 2 sub problems. And now from these 2 sub problems, again each sub problem should be solved by using the same procedure. That means a recursion, right? That we call it as a conquer. So again here let it be 0, 1 and 2, and here also 0, 1 and 2, and let it be here a low value, and this is a high value, and again here is a low value, and this is a high value. So here mid is equal to low plus high by 2, 0 plus 2 by 2, and here also mid is equal to 0 plus 2 by 2. So how much we get? 2 by 2, it's 1, and here also we get 1. So we are applying the same procedure. And based upon this we are again dividing the same array into different parts. So again this will be divided from 0 to mid, that means low to mid, and mid plus 1 to high. See, so I am taking low to mid, that means 40 and 60, and mid plus 1 to high. So obviously mid plus 1 and high both are equal. So we are having only one element, 50. And here also the same procedure. So what happens? Again 2 elements, it was divided into 2 elements, 30 and 20, and again the same single element which is a 10. So complete problem, sub problem, and again sub problem. So we need to stop here, because if the total number of elements are equal to 2, then only one comparison is required. So we can compare 40 and 60 so that we can get the minimum and maximum value, right? So among these two values, we can simply say that with one comparison, we can say which one is the minimum value and which one will be the maximum value. And if the array consists of only one element, so then the minimum and maximum value will be the same. So we need to stop this recursion whenever the division, after division, if the count is equal to 2, okay, we can stop it. So stop procedure. So I will write here stop. When we have to stop condition. So whenever it becomes 2 power I is equal to 2. Okay, so or simply we can say it as a k. So anything we can represent simply 2 power k. Means here we have divided into n2. Okay, and further we have divided into 2. So that means here we can write it as n by 2 and here we can write it as n by 4, because n by 2 again we are dividing it into 2 halves. Okay, so we have to repeat the same process, n by 2, n by 4, n by 8, n by 16, and this process will be repeated until that equal to 2. Okay, this is a stop condition. Whenever it becomes 2, then we have to stop it. Now we are stopping here, right? Now directly we need to compare these two values. So compare these two values and we can find what is a minimum and what is a maximum. So here you can say minimum is equal to 40, maximum is equal to 60. And here we are having only one element, so the minimum value and maximum value will be the same. So a minimum is equal to 50, maximum is equal to 50. And apply the same process on the second half also. So here also the minimum value will be 20. So we need to compare. Okay, we need to compare whether 30 is greater or 20 is greater. So obviously 20 is greater, right? Only one comparison is required. And a maximum is equal to 30. And here only one element, so minimum is equal to 10 and maximum is equal to 10. Right? So two conditions we have done. If the number of elements are 1, then there is no comparison. So the minimum element and maximum element will be the same element. And the second condition, if the number of elements are 2, it requires one comparison. And based upon that one comparison, we can consider or we can assume what is the minimum value and what is the maximum value. Now we have to, we solved their subproblems. So this subproblem has been solved. So we got minimum value and maximum value. And this subproblem also solved. We got minimum and maximum. This subproblem we got a solution, minimum and maximum. This subproblem we got a solution, minimum and maximum. Now the third part should be started. So what is the third part? So third part is combining. Combining both the solutions, all the solutions. Okay. So first we have to combine these two solutions. So combining these two solutions, we have to compare this minimum with this minimum. So 40 and 50. So what is the minimum value here? So here minimum value from this one and this one, the minimum value will be 40. And similarly maximum should also be compared, 60 and 50. Which one will be the maximum? So obviously 60. So after combining these two solutions, we got a solution minimum 40 and maximum 60. And apply the same procedure for these two halves. So minimum 20 and minimum 10. When we compare these two things, the minimum value will be 10. And compare these two things, maximum 30 and maximum 10. So it will be a maximum 30. So after combining these two solutions, we got a solution min is equal to 10 and max is equal to 30. Now we have to compare these two things. Okay, these two things, and this one and this one. So when we compare this one, minimum 40 and minimum 10. So compare the minimum value from both the solutions. Compare the maximum value from both the solutions. So from these two solutions, the minimum value will be 40 and 10 10, and maximum value will be 60 and 30, 60. So this is the final solution. Final solution. So from the given elements, you can observe which one is the minimum element, that is a 10, and which one is the maximum element, that is 60. So we have applied the divide and conquer method. So we have divided the complete problem into subproblems, and then we have solved each subproblem, and then we have combined the solutions of all subproblems, right? So this is the procedure and this is the example. I think everyone understood this example. Now based upon this example, we will write the algorithm. Okay, so hope everyone understood this example, right? So we'll write the algorithm for this one. So I don't want to erase all these things because further we'll use the thing, right? See. See, algorithm or pseudocode, whatever it may be, we can write. So I'll give the name it as a min max. The algorithm name is min max. So it will take a few arguments like low, high, min and a max. So I take this one. Now what we have to do? So first we have to check whether the array elements are equal to 1 or 2. So if low is equal to high, so we have to initialize low with a 0 and high with n minus 1. Okay, if it is having some n elements, we have to initialize high with the n minus 1. So after that, if we get a low is equal to high, that means only one value is there. If the array consists of only one value, then obviously what happens here, we have seen both the min and maximum will be the same, right? So what we have to do, so the minimum is equal to some array of low or high, anything is common, right? Similarly, maximum is equal to a of high or low, whatever it may be. You can write anything because both are equal, right? Yes. Now the second condition, if it is having two elements, okay, the same thing which we happens here in the last step. Okay, so we got one array with two elements, one array with one element. So what happens here? Else if low is equal to high minus 1, that means if it is having a two elements, okay, if it is having two elements, what we have to do? We have to compare. So what we have to compare? If a of low is less than a of high, so we are comparing both the things. Okay, if only two elements, we are comparing both the elements. So if a is low is less than a of high, we can simply say minimum is equal to a of low and the maximum will be a of high, obviously. And else that means a of low is less than greater than a of high. That means if the first element is greater than the second element, obviously the minimum element will be a of high, maximum element will be a of low, right? So this is the first condition when the number of elements are 1, and this is the second condition when the number of elements are 2. Now when the elements are greater than 2, what happens? Again we have to divide. And we have to apply the same process. So else part, and what we have to do? We have to calculate the middle element. So middle element is equal to low plus high divided by 2. Low plus high divided by 2. And then we have to divide two arrays. What is the two arrays? The first one, the name is min max, and we have to apply the same procedure. So min max of low. What is the high value here? So obviously it will be mid, and we'll take it as a min 1 and max 1. And second array, this is the first array. Second array, min max, what we have to consider? Mid plus 1 to high, and from here we will going to get minimum 2 and maximum 2. So after completion of these things, we will get only minimum and maximum, both the cases, min 1, max 1, min 2 and max 2. Now we have to compare these two things. So after that we have to compare. If min 1 is less than min 2, so min 1 is less than min 2, so what we have to consider? Minimum value is equal to, okay, min 1. Else min 1 is equal to, min is equal to min 1, else min is equal to min 2. Okay, so if minimum 1 is less than minimum 2, so that means in the last step, if both we have to compare both the minimum values, right? And the same thing should be applied for maximum also. If max 1 is greater than max 2, what happens? So max will be max 1, else max will be max 2. So this is the algorithm for finding the minimum and maximum values, from the single array, unsorted array, by using the divide and conquer method. So hope you understood what we have done in the example. The same thing we have written in algorithm, right? So first condition, this is n is equal to 1 element, n is equal to 2 elements, and this part is n is greater than 2 elements. This is n is greater than 2 elements, right? So three conditions, we are writing these three conditions, and this part will be repeated until n by 2 power k is equal to 2, right? So hope you understood. Now we'll see how many comparisons we require if we apply this kind of algorithm, okay, divide and conquer algorithm. So by using the linear algorithm, so linear method, the time complexity or the number of comparisons will be 2n minus 2, and now we'll see the time complexity, that means the number of comparisons for this particular algorithm. See, if there are n elements, so we are dividing it to n by 2. N by 2 and n by 2. And again, this is divided into n by 2 and n by 2. This is divided by n by 2, n by 2. Further, it is divided by n by 2, n by 2. Okay, and this process will be repeated. And when we have to stop? We have to stop whenever n by 2 power k is equal to 2. That means after division, if the number of elements are 2, then we have to stop the division operation. Now, see the complexity or the comparisons, whatever it may be, we'll write here T of n is equal to 0. That means 0 comparisons if n is equal to 1. That means only one element is there, 0 comparisons will be there. Then it will be 1 if n is equal to 2 elements. If n is equal, if array is having 2 elements, only one comparison is required. And if it is, right. So if it is greater than 2, then what we are doing, we are dividing the complete array into two halves. So n by 2, okay, plus n by 2, right, plus 1 plus 1, and this is if n is greater than 2, and this is the time complexity of first half plus time complexity of second half, and this is for divide, and this is for combine the results. So if the number of elements are greater than 2, then it will be n by 2 plus n by 2, so plus 1 plus 1. So this we can write it as 2t n by 2 my plus 2. So like this we can write it. Okay, if n is, if the elements are greater than 2, then the complexity will be this one. So we have to divide the two halves, and again further we have to divide the two halves. Then we can see t of n by 2 will be, so apply the same, this is for t of n. Now t of n by 2, then it will be 2 into 2t of n by 2 divided by 2 plus 2, okay, so this is this one, plus 2, okay, we are just substituting n by 2 here, okay. Now this happens with, so 4t, and this will be n by 4, n by 4 plus 2 2s are 4 plus 2. Similarly, again divide it into n by 2. Again divide it into n by 2. So again we'll apply the n by 2 here itself. Okay, or simply we can go with the n by 4 also. Okay, if it is n by 4, apply the same thing. Okay, so let us take further, it is divided. So 4 into 2t of n by 4 divided by 2. So further we are dividing. Okay, so plus 2, and write down all those things. 4 plus 2. So if you solve this one, it will be 8t into n by 8 plus 8 plus 4 plus 2. Right? So, and if you go with the next one, right? So t of, again further division. So 8 into 2t of n by 8 divided by 2 plus 2 plus 8 plus 4 plus 2. So which will be 16t n by 16 plus 8 plus 4 plus 2. So you can use a generic formula. So if it is 8, obviously we are getting, see, third division we are getting here like this. Okay, so this can be written as 2 power k of t n by 2 power k plus, so this can be written as 2 power k plus 2 power k minus 1 plus and so on plus 2. Okay, so if it is 4, it will be 2 power 4, and here it will be 2 power 4, 2 power 4, 2 power 3, 2 power 2, 2 power 1. So like this we can write it. And see from here, so when we are applying the stop condition, this is a stop condition. From here we can consider n is equal to 2 power k plus 1. Okay, so simply we can write it as 2 power k into 2, so which can be written as 2 power k plus 1, or simply we can write 2 power k is equal to n by 2. So remember these two formulas. Remember these two formulas. Now what we have to do? So you can observe this particular pattern, which is a geometric progression, a formula of geometric progression. So geometric progression formula is, so A into r power n minus 1 by r minus 1, where A is a first term and r is the second term divided by first term, right? And if it is like 2 plus 2 square plus 2 cube plus and so on 2 power n, if the series is in this way, the formula will be A into r power n minus 1 by r minus 1. Just remember this one, right? So here A is the first term, so here A will be first term, that is a 2 into r is the second term by first term. What is the second term? 4 by 2, again it is 2, and here n, so here we are representing that as a k. Okay, here it is n, but here we are representing it as a k. So 2k minus 1 divided by 2 minus 1. So this can be considered in the place of this one. Okay, so hope you understood. So forget about this term, 2 power k into t of n by 2 power k, right? So forget about this one, just remember about this series. So this is like in the same way, 2 power 1, 2 power 2. So you can observe here 2 power 1, 2 square, 2 cube, 2 square, 2 cube, 2 power 4. So it will be keep on moving until 2 power k, right, from 2. So that will be in the form of this series. Now what we have done? We have applied the direct progression formula, A into r power n minus 1 by r minus 1, where A will be the first term and r will be the second term by first term. So it will be this one. Now apply the same thing in the place of this one. So I'll erase this one, right? So hope you understood. I'll erase these calculations. I'll apply the same thing here. So 2 power k into t of n by 2 power k plus, instead of this series we can write this one. So 2 into 2 power k minus 1 by 2 minus 1. So this can be written as 2 power k into t of n by 2 power k plus, it will be, so denominator will be 1, so it becomes 2 power k plus 1 minus 2. Okay, so 2 power k plus 1 minus 2, and here you can see so 2 power k t into, in the place of n we can write it as 2 power k plus 1. So 2 power k plus 1 divided by 2 power k plus 2 power k plus 1 minus 2. Okay, so I'll erase this one also. So what happens here? So 2 power k into t, what happens? This we can write it as 2 power k into 2 by 2 power k plus 2 power k plus 1 minus 2. So you can remove these two things. So now the formula will be 2 power k into t of 2 plus 2 power k plus 1 minus 2. Right? Now you can observe 2 power k. So what is the value of 2 power k? N by 2. So n divided by 2 into t of 2. That means we are having 2 elements. Okay, in the n we are having 2 elements. If it is 2 elements, see, if n is equal to 2, the result will be 1, complexity will be 1, the comparisons will be 1. So we can simply substitute it as 1 plus 2 power k plus 1. 2 power k plus 1, it is n. So n minus 2. Okay. So from this we can write it as n by 2 plus n minus 2, which will be treated as 3n by 2 minus 2. So this is the number of comparisons we required in order to find the minimum and maximum elements using divide and conquer. So here also, if you observe, the worst case complexity will be order of n. Because the highest degree is n, the complexity will be, here also the complexity will be order of n. Okay. In the linear model also, that the highest degree is n, the complexity will be order of n. Now you can check. So if you are having a 10 elements, okay, so we need to find the minimum and maximum from the 10 elements. If you apply the linear approach, how many comparisons will be required? So the comparisons will be 2n minus 2. 2n minus 2. That implies 2 into 10, 20 minus 2. 18 comparisons are required. 18 comparisons. And if you go with the divide and conquer, then the same comparisons, the comparisons will be 3n by 2 minus 2, which will be 30 divided by 2. Okay, 3 into 10, 30 divided by 2, 15 minus 2, 13 comparisons. So now you can observe, so if it is a linear approach, it requires 18 comparisons, and if you go with the divide and conquer, the comparison has been reduced to 13, which is an optimal solution. So you can feel the difference. So without using the divide and conquer, and after applying the divide and conquer, so obviously the number of comparisons will be reduced if you use a divide and conquer strategy. So final goal for every problem is to find the optimal solution in terms of complexity or time complexity or space complexity, whatever it may be. But the final goal is to get the optimal solutions. Now we can see clearly by using the divide and conquer method, we will be having the optimal solution. So it requires a minimum comparisons, less comparisons when compared to the conventional model or a linear approach. Right? So hope you understood. So this is the stop condition. First we have to start dividing the complete problem into sub-problems, and we have to continue the same process until the division results to 2 elements. So then we have to apply the algorithm. An example for the binary search, and then the algorithm, and finally we'll see the time complexity. Right? So today's concept is a binary search. So search means searching or finding an element, whether it is present in the given list of elements or not. So if it is there, automatically will return that element or a position, or we can say that element is found in the list. Otherwise we will say it is not found. And in order to solve this one, we are going to use this divide and conquer. That means we are going to divide the complete list into 2 halves, and we are going to solve the problem by selecting either one of the half. Right? So every time we are going to reduce the search space. For example, if a list contains some 5 elements or 6 elements, in the second, after first iteration, after dividing the list, so then the search space will be reduced to around 3 elements or 2 elements. So like this, we are going to reduce the search space after every iteration until it gets only one element. Okay, so let us consider an example first. First, let us see the procedure, how we are going to solve that one, and then we will move on with the algorithm and then a time complexity. Now, consider a list of elements, and one first thing, very important, if you want to perform this binary search, make sure that the element should be in a sorted order. That is a one important constraint before starting this binary search procedure, right? So very important. So elements should be in sorted order. So this is important for binary search, and if you are moving with another one, linear search, so there will be no constraints. The elements can be of any order, so that we can find the element, that we can perform the linear search. But coming to the binary search, make sure that the element should be in a sorted order before starting the binary search. Now consider an example. So we are going to take some sorted elements. So I take it 10, 15, 35, 42, 58. So I'll take a small elements, okay, only 5 elements. So here I am considering 5 elements. So now consider this one as a low, this one as a high. Okay, low and high. First we need to find out the middle element. Okay, middle. So consider the index values 0, 1, 2, 3, 4, and this is the 5 elements. These are the 5 elements. And now we need to know the key value, that means the search key. So which element we are going to find. Let it be the search value is 10. Search value is 10. Now in the first step, find out the middle value. So mid is equal to, so low plus high divided by 2. So which gives, so 0 plus 4 divided by 2 is equal to 2. So middle is a 2. Okay, middle is 2. So what we have to check, see, the low is a starting element and high is the last element. Okay, low is the starting element, high is the last element. So always we know that low will be less than high. We know the process, right? So always low will be less than or equal to high, because if the elements are only one element, the same element will be pointing towards the low and high. So low is less than or equal to high. And if low is greater than high, then such is not possible. Or we can say that element is not found. Okay, if low is greater than high, then such will be not possible, right? So we need to repeat the same process. Okay, we need to repeat the middle, calculating the mid value until the low becomes greater than high. Now see, middle. Now what is the element of a middle, right? This one is a mid. This one is the mid. Okay, so now compare the middle element with the search element. Compare middle element with the search element. So I need to compare search element, and let it be, the name of array is capital A. So A of mid. So we need to compare this one, right? So what happens, k is a 10 is equal to 35. Is it true or not? If it is true, that implies our search value is equal to the low of mid, I mean A of mid. So obviously we can say that the element is found in the list. So if it is false, check 10 is less than 5 or 10 is greater than 5. First let us take the greater than, because it's a false condition. So 10 is a greater than 35. That means we are comparing the search with middle element. This is the middle element, right? So 10 is greater than 35. So it is false. Next, 10 is less than 35. So if you want to compare two values, only these three are possible. Whether either both are equal, either the first element is less than the second element, or either first element will be greater than the second element. Only the three possibilities. Now check 10 is less than 35. Yes, this is true. What happens, that what says this one means search element is less than 35, and the constraint is elements should be in a sorted order, and from this point 10 is less than 35. Obviously that implies the search element may be less than the middle element, less than the portion of middle element. Okay, hope you understood. So here from low to high we are finding the middle value, and in the middle value we are checking and comparison. So we are comparing the middle element, and based upon this one we are selecting either we have to choose the left portion of the middle or right portion of the middle. And here 10 less than high, okay, 10 less than 35, it is true. Then we have to select the left portion, because all the elements which are less than 35 will be towards the left side of the elements. Now what we have to do? We have to change the search space, and here the search space is low to high, and now the search space will be low to, and already we have compared this middle element, right? Here we have compared the middle element. So the search space will be reduced to mid minus 1. Mid minus 1. Okay, mid minus 1. For example, if the search element, if the key is some 42, what happens? So up to this one, the same procedure. So 42 is equal to 35. Wrong. 42 greater than 35. True. That means whatever the element we are going to search, that is on right side portion because of this sorted order. So what happens? So the portion, that search space will be reduced towards the right side portion. What is the right side portion? Already the middle element has been compared. So we need to change the low value. So low value, so the search space will be mid plus 1 to high. Mid plus 1 to high. So we need to search only this portion. If it is less than this portion. Okay. So like this we have to repeat, and we have to check, and we have to stop this procedure whenever the low is greater than high. If the element is not found, automatically we will get the low greater than high. So then we have to stop this procedure and see. So we are performing the division operation and one comparison. Division operation and one comparison. Right. See, we'll check. Now you can see 10 less than 35, then it is low to mid minus 1, and now the elements are so 10 and 15, and we should not consider 35. Mid minus 1 means here low 0, mid minus 1, 2 minus 1 is 1. So the search space is reduced to index values from 0 to 1, and here also 0 to 1, and you can see this one will be 0, this one will be 1, and we need to find out again a mid value. So this will be a low value, and repeat the same process which we have done is the same, right? So again calculate a mid is equal to low plus high divided by 2, which gives 0 plus 1 divided by 2 is equal to 0. So compare key value and 10. Sorry. Key value and A of mid. A of mid. So, which gives key value is 10, middle value and A of 0, that means A of 0. A of 0 is 10. 10 is equal to 10. So, obviously we found the element. If it is not found, again we have to repeat the same process. Okay. So, hope you understood. So, first the search space will be from low to high, and if after the first iteration, that means after finding the first middle element, we are based upon the middle element comparison, we are reducing the search space from either left portion or the right portion. If it is a left portion, the range will be from 0 to mid minus 1, and if it is the right portion, the range the search space will be from mid plus 1 to high, and we have to repeat the same process. Okay, now we'll write the algorithm. Recursive algorithm, right? We can write the recursive algorithm. So I'll write here. It's a very simple algorithm. Binary search. So we can take a lot of parameters, like array. We can pass the array, low, high, and key. So I will take it as some array, low, high, key. So we need to follow this order. First one is an array, second one is a low, third one is a high, and fourth one is a key. Now first we have to find whether low is less than or equal to high, and if it is low is greater than high, then simply we can say it is not possible. So if low greater than high, so we can simply return false. We can write return false or element not found, whatever it may be, based upon our logic, based upon our presentation, we can write it. And else, that means if low is not less than, low is not greater than high, next we have to find out the procedure. What we have to do? First we have to calculate the middle value. So middle value is equal to, so the same thing, low plus high divided by 2. So after getting the mid value, this is an index, right? Now we have to compare middle the key with the middle element. So here, if mid is equal to some array of, if key is equal to array of mid, then write down return true, or you can write it, yes, the element found at the position mid is the position, right? Else, again we have to check the condition, else if key is less than array of mid, what happens? If the search element is less than the middle element, obviously the search space will be left hand side. So what we have to do? On the left hand side means the search space will be reduced. So low will be remain same and high becomes mid minus 1. So you can write it the recursive call. So we can simply call the same thing. So binary search. What we have to do? So first one is array, low value is same, and the high value will be mid minus 1 and a key. Okay. Then else, if both the cases are false, that implies the key is greater than array of mid. So again we can write binary search, and now also array, the search space will be now reduced to right half. Right half means low value will be changed to mid plus 1. So mid plus 1 to high key. So this is a simple and very easy algorithm. So everything is the complete problem will be divided, and based upon the division, based upon the comparison, we have to change the search space. Search space means from where to where, either low is changed or high is changed. So we have to repeat the same process until the low value is greater than high. So if this problem came low greater than high, that implies the element is not found in the array. Okay, so now we will see the time complexity. Hope this is very simple. So hope you understood this one. Now we will go with the time complexity. What is the time complexity? So the best case time complexity is order of 1, because if you are searching the search element is the middle element. For example, if key is equal to 35, how many comparisons you require? So here in this case, that is the middle element. Obviously, in the first comparison itself, we will get the search. Okay, so it will be order of 1. It's a best case, and always we have to consider the worst case, right? So consider the worst case. So T of n is equal to, what we are doing? We are dividing and we are doing the comparison. So what we have to do? T of n divided by 2 plus 1. So we are not solving two portions. Okay, we are solving only one portion, either left half or right half. So that's why I am writing only one time, T of n by 2. And after that, we are comparing, one comparison. And see, we need to find out the n, what is n, and see, in the first step, we are finding n divided by 2. Okay, so in the next step, we are finding n divided by 4. See, now we are checking n divided by 2, that becomes n divided by 4 plus 1 plus 1. And again we are performing the same thing in the next half. So n by 4 half, that means n by 8 plus 1 plus 1 plus 1. And similarly, T of n by 16 plus 1 plus 1 plus 1 plus 1. So what happens? Every time we are dividing the search space into half. So first we are having some 5 elements. From that we are dividing the 5 to 2, and then we are dividing the 2 to 1. Okay, so we are keep on repeating the same process until we get the element, only one element. So you can simply say that this is T of n by 2 power k plus k terms. Okay, now when we have to stop, so that is also most important here, stop condition. So when we are going to stop this division, so n by 2 power k is equal to 1 element. So we are keep on repeatedly dividing the complete list, and we are stopping whenever n divided by 2k becomes 1 element. Okay, so from this equation we can say n is equal to 2 power k. So substitute the same thing here. So what happens here? So the same process will be repeated, and T of n by 2k is n plus, from this one, what is the k value? So log n base 2. So we can represent it as log n base 2. Okay, now what happens is equal to T of 1 plus log n base 2. So if there is only one element, then automatically it will be 1. So 1 plus log n base 2. So the time complexity, we can say the time complexity is equal to order of log n base 2. So this is the time complexity for binary search. Okay, using divide and conquer. So here we are not combining all the solutions. So just we are dividing the complete problem into sub problems, and we are considering only one portion, not the two portions. And we are repeating the same process until it reaches to one element, and we are comparing, and if it is not found, we are saying that element is not available. So the only one constraint here is elements, all the elements should be in a sorted order. So that is the most important constraints we have to follow while starting this binary search process. So the sorting is arranging the elements either in ascending order or descending order. So by default we'll go with the ascending order, right? That means a lower to higher. So one type of that process is a merge sort. So by using this merge sort also we can sort the elements, and this will follow the divide and conquer strategy, right? So we know about the divide and conquer. So it will be having some three stages. One is dividing the problem into sub problems, and second one is a conquer. So that means providing the solution or finding the solution for each sub problem recursively, and the last one will be the combine. So we need to combine the solutions of all the sub problems to get the main solution. So the same process will be applied for this particular merge sort, right? So here in this session we'll see, first we'll see an example so that we'll be getting an idea how the merge sort will be implemented, and then we'll go with an algorithm or a pseudocode. So based upon the procedure which we have known in this example, so we'll write the algorithm and we'll check, and finally we'll see what is the time complexity, the worst case time complexity of a merge sort, right? So we'll see one by one. So first let us start with the example. So let us take a few elements, unordered elements, and then we're going to use the divide and conquer method. So 50, 60, 10, 70, 30 and 40. So let us take these elements. Now we know that these elements are not in a sorted order. So we have to arrange them in the sorted order. So initially we'll write the index values 0, 1, 2, 3, 4 and 5, and we know, so this is the low, we will represent this one as a low and this one as a high. This one as a high. So the first step is divide. So we need to divide the complete problem into sub problems. So formula. So by which formula or by which criteria we need to divide the complete elements into two halves. So that is based upon the middle value. So mid value. So we need to calculate the mid. So mid is equal to, so low plus high divided by 2. So we need to consider only the integral part. So that will be low plus high by 2. That means 0 plus high 5 divided by 2. So which is 5 divided by 2, which is 2.5, and we need to consider only integer. So that will be 2. So mid is 2. Mid value is 2. So here I write mid is equal to 2. Now what happens? We need to divide the complete problem into two halves based upon this mid. Okay, so what's the mid value? 2. So this is a mid. Okay, so where we have to divide? So one part is from low to mid, and the second part is from mid plus 1 to high. So based upon this one, we need to divide the complete elements into two halves. So here we will write So 50, 60, 10, 70, 30, 40. So this is one part and this will be the another part. So again we need to divide the elements further based upon the middle. So we have to solve these two parts individually and recursively. So what happens here? This is 0, 1 and 2 and we need to calculate the mid. Mid is equal to 0 plus 2 by 2. 0 plus 2 by 2. So which will be 1. Which will be 1, right? So we need to divide this one into two halves. So 50 and 60, that means low and mid plus 1 and mid plus 1. Mid plus 1, right? So here also we need to apply the same process. So mid is equal to 0 plus 1, sorry, 0 plus 2 by 2, so which is 1, right? So this is 1, 2. So now here also the same process. It was divided into 70 and 30 and again 40. So two parts. So complete data is divided into two parts and each part is again further divided into two parts. And similarly here also it is 0, 1 and it is 0, 0, 1 and it is 0. So here again we need to divide. So mid is equal to 0 plus 1 by 2 which is equal to 0. So we need to consider 50, we need to consider 60 and here is only one part, that is 10 and here also the same. So mid is equal to 0 plus 1 by 2 because this is a L, this is a high, low and high, low and high. So low plus high by 2. So here also we need to use the same thing. So 70, 30, 40. So right, this is the process. This is the process. Right? This is a process. Now we got a complete elements here. Now what we have to do? We have to compare each and every element and we need to arrange the elements in a sorted order. What we have to do? So we need to compare this 50 and 60. Okay. So 50 and 60, obviously both are in the same, right? And this is 10. And apply the same process here also. So 30 is greater than 70, so 30 is less than 70. So we can see 30 and 70 both comes in the same thing. And now it will be the 40. See what we have to do. So let us assume this one as I and this one as J and this one as I, this one as J. So we need to compare I and J. Here also you can see this is I and this is J. This is I and this is J. So we need to compare the I value and a J value, and if the element whichever it is lower, that should be loaded in the new array. So this is the new array. You can observe this is a new array, right? So compare 50 and 10. Which is the highest? So which is the lowest? 10. So obviously 10 will be placed here first. And this value will be incremented. That means it will be moved to the next one, next element. And here also, now there is no element in J. If in such cases, whatever the elements remaining in this particular subarray, so that will be loaded into the new array. So 50 and 60. See, 50 and 60. So after combining this one, so we got these elements. Similarly, here also, let us assume the new array. See, 30 is compared with 40. So which is lower? 30. So 30 will be stored in new array, 30. And immediately I value will be incremented. So now I value is pointing towards 70. Again repeat the same process. 70 and 40. So 40 is a lower. So now place 40 here and J is incremented. So there is no other value in this particular array. So whatever the elements remaining in this sub array, that will be loaded into the new one. So 70 will be copied here. So you can observe after every step we are getting the elements in a sorted order. So here you can see 10, 50, 60. These elements are in sorted order. 30, 40, 70. These elements are in sorted order. Now what we have to do? So we have to combine these two arrays. So after first division you can see 50, 60, 10, and now it is 10, 50, 60. After division 70, 30, 40, here you can see 30, 40, 70. So we have to compare each and every element of both the arrays, and we have to create a new array, and if whatever the element which is lesser, that element should be copied into the new array, and that index should be incremented towards next one. So if there is no other element in the array, then automatically whatever the elements remained in the next array or the another array should be copied into this one. Now if you are still having any doubts, so let us solve this one so that you will be understanding, right? So here we are having 3 elements and here we are having 3 elements. Now we will solve this one. So I will erase this one. Right. So let us consider 10, 50, 60. So 3 elements, and here also we are having 3 elements, 30, 40 and 70. See, now what we have to do? So we have to compare each and every element, right? See, so let us consider this as I, this as J. Okay, this as I and this as J. Now what we have to do? So we have to compare 10 and 30. We have to compare 10 and 30. So this is a new array. Okay, this is a new array. So 10 and 30. So which one is less? 10 is less. So obviously 10 will be stored in the new array. So 10 will be stored in new array, and I will be incremented this to the next one, because 10 is already here, right? So I will be incremented to the next one. J remains same. Okay, J remains same. Now 50 is compared with 30. So which one is low? 30. So 30 will be copied into the new array. Right? 30 will be copied to the new array. Now J will be incremented. J will be incremented. Again compare 50 and 40. Which one is low? 40. So 40 will be stored here, and again J will be incremented towards here. And again 50 and 70. So 50 is less. So 50 will be copied here, and I will be incremented towards here. So 60 and 70. 60 is less. So 60 will be copied here, and I will be incremented, and there is no element in the array. So it goes beyond the index. So then immediately what we have to do? So we have to go with the next another array, and whatever the elements remaining in that array will be directly copied to the new array. So only one element is there. So already 10 we have copied, then 30 is copied, then 40 is copied, 50 is copied, 60 is copied. So only one element is remains here. So we will simply write 70 in this place. Okay. Now we have taken the elements here, 6 elements, 50, 60, 10, 70, 30, 40, and now we are getting the elements in a sorted order. So 10, 30, 40, 50, 60 and 70. Right. So here we have done the division. So where we have divided the complete problem into 2 halves based on middle value, and then conquer. So recursively we are keep on solving by comparisons, and then combine. So we are merging or combining all the different sub-problems so that we are getting the final solution, right? So hope you understood this one. So based upon this explanation, we will write the algorithm, right? Yes. So what we have to do? We have to divide the complete elements into 2 different halves. So let us write. merge sort. Okay, merge sort. So here we can write, yes, one is array, another one is low, and another one is high. Okay, now what we have to do? So if low is equal to high, that means only one element, right? There is no comparison. Okay, there is no comparison. Nothing can be done. So we can return direct elements. Return element. Okay, so only one element means that will be in the sorted order. Else, what we have to do? We have to divide. So recursive call. Again, apply the merge sort. Apply the merge sort. And what we have to divide? So array of elements, and then low to mid, and then again we have to divide merge sort A mid plus 1 to high. So once the division has been completed, then we have to combine. So that we call it as merge. So don't get confused. Merge sort is different, merge is different. Merge function. So here we will write low, high, mid. Okay. So what we are doing? So first we are checking whether it contains a multiple elements or a single element. If it is single element, simply we can return the element. And if it is a multiple elements, then we have to divide the multiple elements into two parts. One is from low to mid and mid plus 1 to high. And once it was completed recursively, then we have to start merging both, all the solutions, right? So we'll write the merge part here. Merge three things, that is low, high, mid. Okay, also we can take array because we need to pass the array. So also we can write array. Four parameters, array of elements, low, mid and high. Now, okay, so what we have to do? So we have to check, so we have to initialize first. Initialize. Let us initialize I is equal to low and j is equal to what we are doing. So we are taking two parts, and here I am writing I and here I am writing j. So, right? So I is a low. J will be the first element of the second array. So which is nothing but mid plus 1. Hope you understood. Right? So j will be the first element of second array. I will be the first element of first array. So automatically I will be low, that is 0, and j will be mid plus 1. And we need to continue this process until the two conditions satisfies. I less than or equal to low and j less than or equal to high. So here, here it is not low, it is mid, because so until I reaches mid and here until j reaches high, because this position is mid and this position is high. So we are keep on comparing each and every element and we are incrementing the I value and j value, and this process should be repeated until I reaches to mid or j reaches to high. So I less than or equal to mid and j less than or equal to high, we have to repeat it. What we are doing, we are comparing this element and this element. So what is the element? So comparisons. Comparison means a condition, right? So if a of I less than a of j, what we are doing? So if a is less than, this element is less than this element, what we are doing? We are copying this element to a new array. Let us consider here a new array. Some b is equal to, okay, so let us take index value 0. B is equal to index value 0 and b is some array of multiple size. Let us take some 10 array. Okay. So what we have to do? So b of I plus plus, So here we have taken B is an array, and let us take the index value as 0. So B of k plus plus is equal to A of I plus plus. So what happens? This is the postfix. Okay, postfix. First it will be copied and then automatically it will be incremented. And you can also write the same thing in this way. B of k is equal to A of I, and you have to increment the I value. So once you copied this element into this one, we have to increment the I value, right? So we have incremented the I value. And simply you can write else what happens? If it is false, that implies A of j is less than A of I. So A of j should be copied here. So this element should be copied here. So B of k is equal to A of j, and j should be incremented. J should be incremented. So j should be incremented to the next. And both the cases we have to increment the k plus plus, because once the element is inserted here, the k should be incremented so that the k points towards here. So k should be incremented, right? So once all this done, then if it reaches to here, what happens? We have to move all the elements of first array to the new array, or all the elements of second array to the new array. So for that we can simply write a loops. So while, simply write it I less than or equal to mid. Okay, I less than or equal to mid. Simply write down B of k is equal to A of I, and simply write one more thing, j is equal to j less than or equal to mid. B of k is equal to A of j. See, this will be happened. Okay, this will be happened. Sorry, here you have to close, and this is outside the loop. Outside the loop. Okay, so what we are doing? We are comparing the elements, and we are selecting the lowest element, and that element will be copied to the first position here, and then we are incrementing the I value. So the same thing happens here. This code is the similar, right? So once I reaches to mid, what happens? So we need to check whether the elements are remaining in the either of the array. So if they are remaining, so we need to copy all the elements to new array. Okay, and here also we need to increment the k value and the I value. So in both the cases, I value and k value will be incremented. So simply we can write it as k plus plus I plus plus. So because of this post increment, first the value will be copied and then the this one will be incremented. Okay, so this is a algorithm or a pseudocode, so whatever it may be. So based upon our explanation on an example, right? So hope you understood this one. Now we'll move on to the time complexity. So what is the time complexity of this merge sort, right? So we'll see what is the time complexity. So what we are doing, so time complexity of 1, if it is one element, that will be 1, right? So T of n is equal to, so first the problem is divided into two parts and we are solving both the parts. So T of n by 2 plus T of n by 2. So two halves, and we are considering both the things because we are solving both the parts. Okay, whereas coming to the binary search, so we are moving on with only one part, right? So that's why we have not included both the parts, right? But here, so we need to solve both the arrays. We are dividing the problem into different parts, and we have to solve all the parts. So we have to consider this one, and plus what we are doing? We are doing n comparisons. So how many elements are there? Then that many comparisons we are doing. So we are comparing each and every element and we are performing the operations. So plus n. So this we can write it as 2t of n by 2 plus n. Okay. Then coming to the relation. So if n is equal to n by 2, right? Then T of n by 2 is equal to 2 into, okay, T of n by 2, right? So 2T of n by 2 divided by 2 plus n plus n. So it will be 4T of n by 4 plus, so what happens here? So this is n by 2, right? So 2 into n by 2, it will be n plus n. So which gives a 4T of n by 4 plus 2n. Okay. So the same thing, right? Plus n means here we are in the place of n we are dividing the n by 2. So once again in the further process, right? So first there are some 6 elements, then 3 elements. Again 3 is divided into 2 parts. Further division, so we can write 4 into 2T of n by 2 divided by 4 plus, okay, n by 4 plus 2n. So it will be 8t n by 8 plus n plus 2n, which will be 8t n by 8 plus 3n. So this will be keeps on moving, right? This will be keeps on going. So that can be written as 2 cube. 8 can be written as 2 cube T of n by 2 cube plus 3n. So this can be written as T of n is equal to 2 power k T of n by 2 power k plus k into n. So this process will be repeated. So what is the stop condition here? So when we are going to stop the division, right? So here I'll write stop condition. So this is the most important, right, while calculating the time complexity. So whenever it will be, so we are keep on dividing the problem and we'll stop when it becomes one element. When it becomes one element. So obviously we can write it as k is equal, n is equal to 2 power k and k is equal to log n base 2. So this is the stop condition. Now you can know, so k value you know and 2 power k value you know. So substitute the same thing here. So 2 power k, which is nothing but n into t of, okay, n into t of n, it's a 2 power k, or simply we can write n by n plus, what is the value of k? Log n. So log n base 2 into n. So this will be n into t of 1 plus n into log n base 2. And this becomes 1. So that will be n plus n log n base 2. And obviously you can see the highest degree, that is n into log n base 2. So the time complexity, the worst case or average case time complexity for the method will be n into log n. That means we have to write by using the asymptotic notation. So big O of n log n. So this is the time complexity for merge sort. This will be the time complexity of merge sort. So this sorting mechanism will follow the divide and conquer method. Divide and conquer. So the name itself indicates. So divide and conquer means first the complex problem is divided into sub-problems and each sub-problem will be implemented. So like that here also the complete large elements will be divided into different partitions and each partition will be applied for sorting technique. So each partition will be implemented by using the recursive methods. Okay. Next, so let us see the procedure first and then we will go with the example. Then first step, Here we have to select the pivot and we have to find the position of the pivot element. So here we will go with the pivot element, right? So first we have to find the position of a pivot. Such that all the elements which are left towards this pivot are less than the pivot element, and whatever the elements which are on right side to this position are greater than a pivot, right? So this position, first we have to find this position, then consider this as one partition, consider this as another partition. So see, this is less than pivot, this is a greater than pivot, don't get confused, okay? This is a less than symbol and a greater than symbol, okay? So less than pivot is one partition, greater than pivot is another partition. So recursively call the same procedure for this partition. Again consider a pivot and find the position of the pivot for this partition, and again divide that into two positions, right? So like this we have to find this quicksort. First, this pivot can be considered as the pivot element can be considered as first element, middle element, last element, right? So we can consider any element as a pivot element, and based upon that pivot element we have to find the position of that particular pivot element, right? For example, if the numbers are 10, 50, 40, 10, 30 and 20, this element can be considered as a pivot, or this element can be considered as a pivot, or this element can be considered as a pivot. So after considering the element as a pivot, we have to find the position of that particular pivot point such that all the elements which are less than pivot should be on the left hand side, and all the elements which are greater than the pivot should be arranged on right hand side. So in such a way we have to find the position of the pivot. First we have to consider the pivot element. What is the pivot element, right? So in our example we will consider this one, first one. So let us consider the first element as a pivot and find the pivot position. See, first consider first element as a pivot. Consider the first element as a pivot. Next, initialize I to low index, J to high index. That means the starting element, J is the last element. Next, we have to repeat the procedure. Repeat the following steps. Until I less than J. So until I less than J, until the condition is true, we have to repeat the following procedure. So first, keep on incrementing I while
A of I is less than or equal to pivot. So unless this condition becomes false, we have to keep on incrementing the I value. Right. Next, similarly, keep on decrementing the j while A of j is greater than pivot. So similarly, from the starting, we have to incrementing the I towards the right, and we have to decrementing the j towards the left. Okay. So while incrementing and decrementing I and j values, we have to check these conditions, whether A of I is less than or equal to pivot, and whether the A of j is greater than pivot. Right. Next. So if this two condition fails, if these two at some condition, this condition, I mean at some point this condition will be failed, so we have to stop incrementing the I. At some element, this condition will be false, so we have to stop decrementing the j. Now check the condition if I is less than j. I is less than j, yes. Then if it is true, then swap the elements A of I, comma A of j. A of I, comma A of j. So we have to swap the elements of I value, the elements which are available in ith index and jth index. Next, if this becomes false, I less than j. So if I is greater than j, the index value of I is greater than j, then also we have to swap A of j element with the pivot. A of j element with the pivot. So this is nothing but, this is nothing but A of low, because here the pivot is the first element, right? Pivot is the first element. So we have to change the swap between the jth element and pivot value. So here j is the position of pivot. So this is very important thing, right? J is the position of a pivot, so that all the elements which are less than pivot are on the left hand side, and all the elements which are greater than the pivot will be on right hand side. So here, after completion of this one, the pivot value will be fixed. The pivot position is fixed, right? Not the pivot value, pivot position will be fixed, right? So we are supposed to find that position of a pivot. Now divide the two partitions. So one is after getting the pivot value, right? So this is one partition and this is another partition. So this is 0 to p minus 1, and here p to high, p plus 1 to high. Okay, p plus 1 to high. Instead of writing 0, we will write a low. Right, low to p minus 1. So this is one partition, this is another partition. So consider this partition, and here also consider repeat the same process. So recursively repeat the same process. Consider this partition as an array of elements. Now consider the pivot, first element as a pivot, and starting I to low index and j to high index. So I will be low, j will be p minus 1, and then repeat the following steps until I less than j. So keep on incrementing I while ia of I is less than or equal to pivot, and then keep on decrementing the j while a of j is greater than pivot, right? Then if I is less than j, the index values of I is less than j, then simply swap the positions of I and j, the elements which are at positions of I and j. then if I is greater than j, the index value of y is greater than the index value of j, then simply swap the low value with the a of j. That means of the value present at the position j. So here a of low means nothing but a pivot value, because in the first step we are considering the first element as a pivot. So here again the pivot, the position j is the position of pivot. So position, when the pivot position is fixed, so that all the elements of which are less than pivot will be on left hand side, and all the elements which are greater than pivot are available in the right hand side. And again do the partitions and again repeat the same process, right? So this is how we will implement, we are going to implement this quicksort, right? So based upon this algorithm, let us solve an example so that your doubts will be clarified. So our aim is to find the position of a pivot, and we will implement the same thing recursively for all the partitions. So once the pivot is fixed, then we have to divide it into partitions, and considering each partition, and we have to repeat the same. Okay. Example. Let us take some elements. Consider these elements. Okay. See, so these are the elements of an array. So this is array elements. These are the indexes. This is the I value. This is the j value. I value, j value. Okay, right. Then consider this as a pivot. Consider this element as a pivot. Now repeat the process. So first step, consider the pivot as a first element. So we have considered this one, and next I is initialized to low and j is initialized to high. So I less than j, that is here 0 less than 5. The condition is 2. So this condition is 2. We have to repeat the process. So what we have to repeat? We have to keep on incrementing I until a of I is less than or equal to pivot. So a of I less than or equal to pivot. See this condition I plus plus. We have to repeat the same process. Okay. So here see first 30 less than or equal to 30. So I plus plus. So that means 1 it will be. Next 20 less than or equal to 30. I plus plus 2. Right. Next 10 less than or equal to 30. I plus plus 3. Index value 3. So 50 less than or equal to 30. So fails. Okay. Fail. Here the fail. Condition fails. Now here at what condition it is failing? I is equal to 3. So I is equal to 3. Right? Condition I is equal to 3 fails. So after completion of this one, I is pointing at here. Okay. Now keep on decrementing the j value. So a of j is greater than pivot if I j minus minus. So repeat this process. So a of j is nothing but a high value, high value 5. So 40 greater than or equal to greater than 30, j minus minus, so it will be 4. Next 60 greater than 30, j minus minus, it's again 3. After decrementing, it will be 3. Next, 50 greater than 30. Again, j minus minus 2. Next, 10 greater than 30 fails. So at where it fails, j is equal to 2. Right? So at some condition, at some element, both the condition will be fails. Now we have to check whether I is less than or j. So what is the, see, if I less than j, then swap a of I element with a of j element, right? Else we have to change swap a of j element with pivot, right? Now let us check the condition here. So I less than j, so 3 less than 2, I less than j, 3 less than 2, which is false, right? So we have to swap a of j. A of j means, see, j is 2, a of 2 comma pivot. What is the pivot? 30, or a of low, okay, a of 0, because here the pivot is a of 0, right? So swapping j position is pivot. So what is the j position? 2. Second position is a pivot element. Second position is the pivot element for the first thing. So after getting this one, see, just swap the positions a of 2 comma a of 0. A of 2 means 10. So 10 will be here, 20, then 30, then 50, 60 and a 40. See, 0, 1, 2, 3, 4 and 5. So second position is a pivot. Second position is a pivot, right? So here if you observe, all the elements which are on the left hand side of the pivot are less than this pivot, 10 and 20. So it may be in a sorted order, or it may not be in a sorted order, right? So whatever the elements which are on the right hand side of the pivot are greater than the pivot elements, right? So this may be in a sorted order and this may not be in a sorted order. So this is the partition 1, this is the partition 2, right? So now we have to consider, so this position is fixed, right? Pivot position is fixed. So we have to take care about the partition 1 and partition 2, excluding this pivot position. So that's why we are writing from 0 to low to p minus 1, and here p plus 1 to high. So we are not considering the pivot position because it's already fixed. So hope you understood this one. So after the first iteration, first recursion, this is the elements. Now let us write these elements, okay? I will write down here. So 10, 20, 30, 50, 60 and 40. Right. So I will erase all these things. So first recursion, this is about the first recursion. Now so this is the pivot element, okay, fixed. So this will be the partition 1 and this will be the partition 2, right? So let us consider these partitions. So 10 and 20, 0th index, first index. So obviously this will be I, this will be j, and also pivot. we know that we are considering the pivot as a first element, so this one. So what we have to check, we have to repeat until I is less than j. Here it is 0 less than 1, condition true. Then keep on incrementing, so a of I is less than or equal to pivot I plus plus. So for this we have to go with this, so 10 less than or equal to 10 I plus plus, that will be 1, and 20 less than or equal to 10, okay, so false. So I is equal to 1, oh sorry, right, I is equal to 1. So I value is changed from here to here, okay. Next, a of j greater than pivot, we have to keep on decrementing the j value. We have to keep on decrementing the j value. So 20 is greater than or equal 20 is greater than 10, j minus minus, right, j minus minus, and the value will be 0 now because initially j is equal to 1, and 10 is greater than 20, which is a false, so j is equal to 0. See, at I is equal to 1 the condition fails, at j is equal to 0 condition fails. Here if you observe I is less than j, then what we have to do, swap a of I comma a of j, else, oh sorry, we can write the condition, okay, I greater than j, then swap a of j comma pivot, right. Pivot, right. So here we can observe here at what positions the condition fails. I is equal to 1 and j is equal to 0. So 1 less than 0, the condition is false. So this will be happened. So swap a of j means 0 comma pivot. Here pivot means again a of low. So that implies so both the j position, both the j value and a pivot are at the same position, so we need not swap anything, right. So already those are in sorted order, that means these are in a sorted order because we need not swap any element, okay, only two elements are there, we need not swap any element. So this will be the pivot position, okay. So here see, j position is a pivot position, isn't it, right? What is the j position? 0. So 0th is a pivot position. If 0th is a pivot position, see, left hand side we are not having any elements, right hand side we are having only one element which is also greater than 10. So it implies this partition is already in sorted order, right. Next, hope you understood. Next we will go with the partition 2. We will go with the partition 2. So this is already in sorted order. Now we will repeat the same process with the partition 2. So 50, 60 and 40. So 0, 1 and 2. So this is the I value, this is the j value. Okay, this is the I value, this is the j value, and this is the pivot, right. So continue the process. So I less than j, that is 0 less than 2. So this condition true. Then a of I less than or equal to pivot I plus plus. So keep on doing all these things. So a of I, that means a 50 less than or equal to 50 I plus plus, that means I becomes 1, initially 0. Next 60 less than or equal to 50 fail at I is equal to 1. At I is equal to 1 it fails. So now I becomes here. Then similarly A of j is greater than pivot j minus minus. So repeat this process. So j value is a 40, 40 greater than 50, 40 greater than 50. Condition false. So at j is equal to 0 position. At j, at j is equal to 2. At j is equal to 2, the condition fails. Okay. Then see, if you observe here, check the condition I greater than j. Here I is 1 greater than 2. I greater than j. It is a false. So swap. I'm extremely sorry. I less than j. So if I is less than j, we have to swap the elements a of I and a of j. If I is greater than j, then we have to swap the elements a of j and pivot. So here the first condition, I is less than j. I value is 1, j value is 2. So I is less than j. So swap a of I comma a of j. So what are the elements we have to swap? Swap the 60 and 40. So the elements will be, after the iteration, the elements will be 50, 40, 60. 50, 40, 60. The positions of I and j are same. Okay. So the index values 0, 1 and 2. And this is the pivot we are considering. Right. So after swapping 60 and 40, we will get this one. Okay. Now again repeat the same process. So a of I is less than or equal to pivot. So I plus plus, consider this one, a of I, that means a 40 less than or equal to 50, I plus plus, which becomes 2. Similarly 60 less than or equal to 50, fail at I is equal to 2. Right? At I is equal to 2, it fails. Now I and j are positioning at the same point. I and j are positioning at the same point. Similarly, a of j is greater than pivot, then simply decrement the j. Repeat the process. So 60 greater than or equal to 50, not equal, greater than 50, j minus minus, which becomes 1. Similarly, 40 greater than 50, which fails at position j is equal to 1. Now j is positioned at 1. Right? Now check the condition. So if I is less than j, then swap a of I comma a of j. Just a minute. Else swap a of j comma pivot. Right. Now here I is 2, j is 1. 2 less than 1, false. So we have to swap, false condition, swap a of j comma pivot, which is nothing but swap a of j means a of 1, 40 comma a of pivot 50, and we know that j is pivot. J is pivot. That means 1 is pivot here. Okay, so here 1 is pivot. So after completion of this, okay, after completion of this, so I will erase this one. Okay. Right. So here j is a pivot. J is pivot. Here what is the value of j? 1. So 1 is a pivot position. 1 is pivot position. So we have to swap. After swapping 40 comma 50, the elements are 40, 50 and 60. The positions 0, 1, 2, the position, this is the pivot position. So left hand side of the pivot is having the values less than pivot, and the right side of the pivot position are having the elements greater than pivot. So here again, this is the one partition, this is the another partition. So here the partition is having only one value, so need not apply the sorting technique. And here also the partition is having only one value. Here also we need not apply the sorting technique. So finally, after completion of all these things, we can simply have (40), (50) and 60. Okay, so this is a procedure we are supposed to apply. So hope you all you understood this one, right? After the first iteration, 2 is a pivot, so that two partitions are there. First partition, again 0 is the pivot. Second partition, 1 is a pivot. 1 means the position 1, index 1. Okay, index 0 and index 1. Right? So hope you understood this one, the quicksort algorithm, how it apply for this, how we are dividing the complete elements into different partitions, and how we are applying the recursive functions. Right? So simple thing. So first we have to consider the pivot element, and first to find out the position of that particular pivot element, and then based upon that particular pivot element we have to divide it into the partitions and recursively apply the same procedure.
Now we'll see the time complexity of this quicksort, and hope you enjoyed the example and the algorithm, the procedure, how we can sort the elements by using this quicksort using divide and conquer. Now we'll see the time complexity. So the time complexity of this particular quicksort is, so we are selecting the pivot element and we are dividing the complete elements into two partitions. Okay, two partitions. So one partition, let it be the pivot element is of middle element, right? So obviously it will be T of n by 2 plus T of n by 2. So worst case, let it be the pivot element is a middle element. So what we are doing, we are dividing the complete elements into two halves. So from 0 to, low to mid minus 1 and mid plus 1 to high, because the middle element will be the pivot. So we need to sort out all the elements of left partition and the right partition. That means pivot, left of the pivot and right of the pivot. So this way. And for everything, for every partition we have to do some n comparisons, because we are applying the sorting up, right? So we require n comparisons, so n. So finally we can write it as 2t n by 2 plus n. So this will be the complexity. Now for the next iteration, so the half partition, again it will be divided into two halves. So then if it is n by 2, then 2t of, apply 2t of n by 2 divided by 2 plus n by 2 plus n. So we are applying only this one, right? So t of n is this one, t of n by 2 is this one. And if it is n by 4, what happens? See, before applying the n by 4, what's the resultant here? So 4t of n by 4 plus n and n, that will be 2n. And if it is n by 4, what happens? And that means again we are dividing the complete elements into two halves. So if it is n by 4, then again it will be, so 4 into 2t of n by 8 plus n by 4 plus 2n. So then what happens here? 8t of n by 8 plus n, okay, plus 2n, that it will be 3n. So this will be the thing, and this will be continued, okay, this will be continued. And what is the stop conditions? Here also the most important, stop condition. From that only we will get some values. So we are dividing the complete elements into halves, and we are repeatedly doing the same thing until we get one element. That means n by 2, n by 3, sorry, n by 4, n by 8, n by 16, and so on, n by 2 power k. And when it will be stopped? Whenever this becomes 1. That means whenever the partition becomes one element. So from this we can write it as n is equal to 2 power k and k is equal to log n. So this is the most important, because from this only we are supposed to calculate this n and substitute the n and k values. So in general we can write it as, so t of n is equal to, so 8, that means 2 power k, okay, or simply we can represent this one 2 power 3 into t of n by 2 power 3 plus 3n. So in the generic we can write this one as 2 power k t of n by 2 power k plus k into n. So we can write the complexity in a generic format like this one, 2 power k, right? Now you can substitute the n value and k value here. So 2 power k, what is it from? n into t of n by n plus k value log n into n. So this becomes n into t of 1 plus n log n. So you can know that if there is only one element, so we need not do all the procedure, the complexity will be 1, because the element itself will be in the sorted order, because we are not having more elements, right? So we are having only one element, so obviously we can say that will be in the sorted order, right? So there is no comparisons. So obviously this becomes 1, so n plus n log n. So in this equation we know the highest degree is n log n. So obviously the time complexity of quicksort, t of n is equal to big O of n log n. So this is the time complexity of the quicksort algorithm, right? So hope you understood. So we are just dividing this one, and this is most important in every time complexity calculation. So from this only we are going to substitute these n and k values. So we are keep on dividing the partitions. So this is a complex problem. So after first iteration we are dividing the problem into half, and this process will be repeated until the partition elements becomes only 1. So from that we got n value and k value, and we are substituting the same in this particular time complexity. So here the name itself indicates this is mainly used for calculating the matrix multiplication. So before this Strassen matrix multiplication, we know that general method how to calculate the matrix multiplication, and then we can also solve this matrix multiplication by using divide and conquer method. And then we will see what are the disadvantages of using this general method and divide and conquer method, and then we'll go with this particular Strassen matrix multiplication. Now we'll see the general method. general method. So which we know that, right? So we'll take n by n order, right? N by n order. So for example, let it be, so A11, A12, A21, A22, and if it is multiplied with B11, B12, B21 and B22, then the result will be C11, C12, C21, C22. So this is the thing we are multiplying. So what is the value of C11? How we will be getting C11? I'll write here C11 is equal to A11 into B11. A11 into B11 plus A12 into B21. A12 into B21. So before going to that, what is the order of this one? 2 into 2. What is the order of this one? 2 into 2. So we know the constraint before calculating the matrix multiplication. What is the constraint? The columns of A should be equal to rows of B. So this is a constraint for any matrix multiplication. If A and B are the two different matrices, and if you want to calculate the multiplication between A and B, then the columns of A should be equal to rows of B. Then only the multiplication is possible. So here we are having a 2 and 2. So obviously both are equal, then definitely the multiplication is possible, and the resultant matrix will be the resultant matrix will be rows of A into columns of B. The resultant matrix will be rows of A into columns of B. So what is the rows of A? This one. Columns of B, this one. So the resultant will be 2 into 2. So this is a general method, we know that, right? Now we can apply this C11. Now C12 is equal to A11 into B12. A11 into B12 plus A12 into B22. A12 into B22. And then the next one, C21 is equal to C21. A21 into B11. A21 into B11 plus A22 into B21. A22 into B21. And then what about the next one? C22 is equal to A21 into B12. A21 into B12 plus A22 into B22. A22 into B22. So whatever the values we are taking, so we need to calculate this matrix with row and column order. So this is the formula we are usually using in the general method, right? So if you go with the logic, so obviously we'll go with the for loop for iterating of rows. So I is equal to I less than n, I plus plus, and then for, and this is for columns. So j is equal to 0, j less than n, and j plus plus. And then the third loop is for multiplication. So for k is equal to 0, k less than n, and k plus plus. And now the logic is C of I comma j. That means this C11, C12, C21, C22 plus is equal to A of I comma k plus, sorry, this is a multiplication, B of k comma j. So this is a logic we are using in a general method for calculating the matrix multiplication. Now coming to the calculation of time complexity, you can see we are having a 3 different for loops, and each for loop is a independent for loop. There is no dependency upon these 3 for loops, right? So this is completely with I, This is completely with J and this is completely with a K. There is no dependency among one with another. So this iterates n times and this iterates n times and this iterates n times. So obviously the time complexity for this one is order of n cube. Order of n cube for general method. So I'll write here. So the time complexity will be order of n cube. Now the same problem can be solved by using divide and conquer method. So coming to the divide and conquer method, the name itself indicates. So first we have to divide the problem into sub-problems and each sub-problem will be get solved recursively, and if possible or if required, all the solutions of those sub-problems will be combined. So that will happen in the divide and conquer method. Now we'll see, and only one constraint for applying this divide and conquer method for calculating this matrix multiplication is the order should be this, it should be a power of 2. Then only the divide and conquer method can be applied. So that is a very important constraint before calculating the matrix multiplication using divide and conquer, right? So for general method it's not required, right? The order can be anything. But coming to the divide and conquer, the order of matrix should be a power of 2. See, I'll tell you. First, make sure the order of matrix are a power of 2. So the next one is divide and conquer method. Divide and conquer method. So one constraint is order should be with a power of 2. That means the order can be either 2 by 2 or 4 by 4 or 8 by 8 or 16 by 16 and so on. So this is 2 power 1, this is 2 power 2, this is 2 power 3, this is 2 power 4. Okay, so like that the order should be only with power of 2. So let us consider this one for our example. Okay, let us consider this one for our example. So I'll take the matrix A11, A12, A13 and A14. Similarly, A21, A22, A23 and A24. A31, A32, A33 and A34. Similarly, A41, A42, A43 and A44. So this is one matrix. This is one matrix. Similarly, there will be another matrix called B. So B11, B12, B13 and B14 and B21, B22, B23, B24 and B31, B32, B33, B34 and B41, B42, B43 and B44. So this is a resultant matrix. I mean second matrix. Now what is the order of this one? This is a 4 by 4 and this is a 4 by 4. So we have to check whether the multiplication is possible because the columns of first matrix should be equal with the rows of second matrix. So here 4 and 4 both are equal. Then the matrix multiplication is possible. And the second one, if the order is in power of 2, then we can apply the divide and conquer. Yes, the order is in power of 2. So 2 square, 2 square, 2 square, 2 square. Then what we have to do? So we have to divide it with a 2. We have to divide it with a 2. So that we'll be getting a lot of 2 by 2 matrices. So simply make it a half. Make an array as a half. So what will be observing? So this is one 2 by 2 matrix. This is another, this is another, this is another. So we are getting a 4 2 by 2 matrices. And here also we are getting 4 different 2 by 2 matrices. So you can represent it as A11, A12, A13, A14. So I'll round it, okay? I'll round it. And similarly, this is a B11, B12, B21, B22. Again, I'll round these things. Okay, so previously we are saying the same thing: A11, B11, A11, A12, B21, B22, B11, B21, B12, and B22. So all these are the values, but here we are saying A11, A12, B11, B12, similarly A13, A14. All these are the matrices, not the values. So for differentiating, I am representing a small letters indicates the values, uppercase letters indicating the matrices. So here we are having 4 different matrices. So you can apply the same formula for calculating this one. So instead of using small a, you can also give a capital A. Okay, you can use a capital A, right? So same, you can apply the same thing. So C11 is equal to capital A11 and into B11 plus A12 into B21. So here the multiplication is in between 2 by 2 matrices. Again we are applying matrices, but here it is a values. Now up to where we have to divide it. For example, if it is 4 by 4, we are dividing into 2. What about if it is 8 by 8? Then it should be divided 2 times. First it will be 4 and then it will be 2. So we have to write down this one in a recursive call. So we are dividing up to where we have to divide, up to whenever the order becomes 2. Whenever the order becomes 2, we can stop dividing, right? So I'll write the formula. So hope you understood. Small letters represents the values, capital letter represents the matrices. So in the multiplication also same thing happens. So C11, so instead of small a, use a capital A. C12, instead of small a, use a capital A. Instead of small b, use a capital B. So same thing will be repeated. Now I'll write the algorithm for this particular divide and conquer method. So what we have to do? So we have to write, for example, I will write it as matrix multiplication, and it takes 3 parameters. So number of parameters, it depends upon your logic. So I am taking a comma b comma the order of this one, because it is a square matrix and also this is a power of 2, so I am giving only n. So the order of matrix will be n by n. So what we are doing, if n is equal to 2, what we have to do? So in this case, we have to write down all these formulas: C11, C12, C21, C22. So we have to write down all the formula, whatever the formula we are writing here. So the same formula will be written here. So if the order is 2 by 2, then it will be the general method, right? So what is the general method? This is the general method we are using, right? So you can write all these things. And if it is else, then what we have to do? So we have to recursively call this one. We have to recursively call this one by dividing the order by 2. So simply what we can do? So we can call the recursive matrix multiplication with what is the values? So A11 comma B11 comma n by 2 plus, okay, and similarly matrix multiplication of A12 comma B21 n by 2. Okay, so this is the formula. See, simply we are, okay, so here these are the values, but these are the matrices. So first we have to calculate this matrix value and then we have to add with the another value. So whatever the things we are writing here, that will be recursively called here. So first we have to calculate the matrix multiplication for 2 matrices A and B. 2 matrices A and B. and then again two matrices A and B. Similarly, the next one, matrix multiplication of A11 comma B12 with n by 2, and again matrix multiplication of A12 comma B22 with n by 2. Similarly, matrix multiplication of A21 comma B11 n by 2 plus matrix multiplication of A22 comma B21 n by 2. Similarly, the last recursive call, matrix multiplication of A21 comma B12 comma n by 2 plus matrix multiplication of A22 comma B22 n by 2. So these are all the different recursive calls. First we are dividing, and we are dividing the matrix until the order reaches to 2 by 2. So if n is equal to 2, then we are applying the same thing here. Okay, we are applying same thing here. Else, okay, if n is not equal to 2, again we are subdividing, again we are dividing the problem with n by 2 times. Okay, so you can see what is the time complexity for this one. What will be the time complexity for this one? So the time complexity for this one will be, count the matrix multiplications, how many multiplications it requires. So you can see this is 1 multiplication, 2, 3, 4, 5, 6, 7 and 8. 8 multiplications are required here. So 8 multiplications for every n by 2 terms. Okay, so we are dividing, okay, and we are solving. Every division we are solving, right? So we are saying it as a 8 into t of n by 2. That is the number of multiplications. Now what about other operators? That is the addition. So 1, 2, 3 and 4. 4 additions. So this is normal value addition. Okay, no problem. Coming to here, so this addition is, so whatever the addition we are writing here, it is in between the matrices. Because here these are the values. Here capital A11, B11 means it's a matrix. And these two are the addition of two matrices. But here the addition of two values. So we have to consider this one. So if for adding of two matrices, what will be the time complexity? So we are using two different for loops. Okay, two different for loops, and one constraint is both the order should be same. So two for loops will be there. Two for loops are independent for loops. So obviously that will be n square. Okay, n square, right? So n square. And how many additions are required? 4 additions are required here. 4 additions are required. So we can simply write it as a 4 addition, right? So that may be varied. So you can give it as a constant like a into n square. A into n square. Okay, so this is for multiplications and this is for additions. This is for additions. Multiplications 8 into t of n by 2 plus a of n square. Now calculate the recurrence relation. So first calculate n by 2. So which will be 8 into t of n by 4 plus a n square by 4. In the place of n, we are giving n by 4. And if it is further divided, we will be writing t of n by 4. So calculate here. So 8 into t of n by 8 plus a into n square by 16. And again, if it is further divided, it will be t of n by 8. Then 8 into t of n by 16 plus a into n square by 64. Right? And this will be keep on going. This will be keep on going. So first let us consider only these things. I am erasing the algorithm, right? So this is the algorithm. Now we are finding the time complexity. So we can use a recurrence relation. So I am substituting this value in this one. So obviously it will become T of n is equal to 8 into, so in the place of this one we have to write all these things. So 8 T of n by 4 plus a into n square by 4 plus a n square. So here it will be written as 8 square T of n by 4 plus 8 into a n square by 4 plus a n square. Now what happens? So this is a T of n. Now you can use T of n by 4, this one in this position. Okay. So substitute this T of n by 4 here. So T of n is equal to 8 square, and here what is this one? 8 T of n by 8 plus a into n square by 16 plus a n square into 8 by 4 plus a n square. And you can elaborate 8 cube T of n by 8 plus 8 square into a n square by 16 plus 8 into a n square by 4 plus a n square. And this can be written as 8 cube T of n by 2 cube plus a n square into, okay, a n square into 1 plus 8 by 4 plus, here it is 8 square by 16, which can be written as 8 by 4 whole square. So 8 by 4 whole square. So this is in the form of 8 power k T of n by 2 power k plus a n square into 8 by 4 power k. 8 by 4 power k. So this is the time complexity after recurrence relation, and this process will be keep on going, and where it will be stopped. So this process will be stopped, that means a division will be stopped when n by 2 power k is equal to 2. Okay, so whenever it becomes n by 2k is equal to 2, so whenever the order becomes 2, we will be stopping. So this becomes n is equal to 2 power k plus 1. So k plus 1 is equal to log n base 2. So k is equal to log n base 2 plus 1, and you can avoid the constant and simply we can say k is equal to log n base 2. And simply you can apply this one here. You can apply this particular thing here itself. So after applying here, so I'll use this one, k is equal to log n base 2. Hope you understood. Let us take T of n is equal to 8 power k, 8 power log n base 2 T of n by 2 power k means n, right? So here we have said n is equal to 2 power k. So 2 power k means n plus a n square 8 by 4 power log n. Okay. Now what we can do? So this can be written as a 2 cube into log n base 2, and this becomes 1. This becomes 1 plus a n square, and you can write it as 8 power log n by 4 power log n, which is a base 2. So which will be n cube. Okay, just refer the logarithmic formulas. So it becomes n cube plus a n square into, and this is also n cube by n square. So this is in the formula. So 2 power log n cube 2. So which will be written as n cube. Okay, this can be written as 2 power log n cube 2 base 2. So if these 2 equal, then it will be n cube. So directly I have taken it as a n cube. So this can be removed, and this will be n cube plus a into n cube, and the order, highest order is P of n is n cube only. So order of n cube. The highest order, we have to consider highest order. So which is order of n cube. See, if you are using the general method, we got the time complexity as order of n cube. And if you are using the divide and conquer, then also we are getting the order of n cube. So there is no difference. So of using general method and the divide and conquer method. So then what we have to do in order to reduce the time complexity. So here also the time complexity will be order of n cube only. Order of n cube only. So that both are equal. Applying the same method is having equal time complexity. That is the order of n cube. So in order to reduce this time complexity of n of order of n cube, we are going to use this Strassen matrix multiplication. Okay, so where we will be having some formulas, and with the help of that formulas, we are going to reduce the time complexity from order of n cube to lower one. Okay, now I'll write the formulas, just relax. So this is the Strassen matrix multiplication. So everything has been reduced, and we are applying these kind of formula for finding the solution, right? So we are taking some 7 values from P1 to P7, and we are applying these formula to find out the C11, C12, C21, C22. So all these things are the resultant matrix. All these things are the resultant matrix. Right? So in order to find out the C11, we have to add P5 plus P4 minus P2 plus P6. So what is a P5 means? Here this is a P5. A11 plus A22 into B11 plus B22. So like that we are taking some 7 variables or 7 formula, and using these 7 formula we are finding out the resultant matrix. So this is the Strassen formula. Okay, this is a Strassen formula. This is Strassen. Okay, now you calculate, the remaining is same. Okay, whatever the information, whatever we have learned, everything is same. So, but instead of using all these kind of things, we are using this one. Okay, so if n is greater than 2, we are dividing it, and we are calling the recursive calls. Everything is same, but what is the difference means, here we are using this formula instead of that one. So because this one is having some 8 multiplications and some 4 or something else additions, right? But here we are having how many multiplications? You can count 1, 2, 3, 4, 5, 6, 7. So one multiplication has been reduced. Total multiplications are only 7 multiplications. Okay, the multiplications are reduced. So here the main complexity is to find the multiplication, not the addition and subtraction. Right? So if you apply the same thing instead of this one, so what will be the time complexity? You can say T of n is equal to, earlier it will be 8 into T of n by 2 because the multiplications. Now it will be 7 into T of n by 2 plus the addition is common, right? If you are performing some addition, the time complexity will be n square, and the number of additions and subtractions will be represented with a constant, so it will be a into n square. So this is the time complexity for Strassen multiplication, not for the divide and conquer and general method. It is for Strassen multiplication. Now again use the same recursive relation. So first let us find n by 2. So it will be 7 T of n by 4 plus a into n square by 4, and similarly use n by 4. So this is also further divided, right? N by 4 is equal to 7 T of n by 8 plus a n square by 16, and this will be keep on moving, n by 4, n by 8, n by 16, n by 32, etc., etc., until it reaches n by 2k. N by 2k reaches to 2, so which is nothing but, so earlier we have calculated k is equal to log n base 2. So till this we are going to divide this one. Now we will apply the same thing for the, instead of t of n by 2. So recurrence relation, amortized analysis, right? So I am erasing this formula, just note down these formulas. So in this Strassen we have to use these formulas instead of that one. Okay, now so here the main we are using, so we are reducing the multiplications, number of multiplications in the Strassen method other than the general and divide and conquer. Obviously the time complexity should be reduced. So previously the time complexity is order of n cube in both general method and divide and conquer. Now we will see what happens. So I am substituting this t n by 2 here. So t of n is equal to 7, and what is this one? 7 into t of n by 4 plus a n square by 4 plus a n square, and this can be written as 7 square t n by 4 plus 7 into a n square by 4 plus a n square. What happens? Now again we can calculate n by 4 here. Okay, recurrence. So t of n is equal to 7 square, and write down all these things in the place of t of n by 4. So 7 into t of n by 8 plus a n square by 16 plus a n square into 7 by 4 plus a n square. Now you can elaborate this one. 7 cube t of n by 2 cube plus 7 square, sorry, a n square 7 square by 16 plus a n square 7 by 4 plus a n square. So this can be written as, so this will be keep on moving, right? So again, if you calculate n by 8, you can replace this n by 8 with the calculated one, right? So it will be replacing everything. So it will be keep on moving until it reaches to this one, n by 2k reaches to here. So I am writing the generalized thing. So 7 power k and t of n by 2 power k plus a n square into, so this will be in the form 1 plus 7 by 4 plus 7 by 4 square, right? And this can be written as t of n is equal to 7 power k t of n by 2k plus a n square and 7 by 4 power k. So this is a generalized thing, and this will be keep on moving until this n by 2 power k reaches to 2. So that becomes k is equal to log n base 2. Log n base 2. So now you can replace this n and k values in this one. You can replace k value here. So t of n is equal to 7 power k is log n. So 7 power log n base 2 t of n by 2 power k. 2 power k is nothing but n. So avoid the constants. Okay, avoid the constants. Plus a into n square 7 by 4 power log n base 2. So what happens here? 7 power log n base 2, and this becomes 1 plus a n square into 7 power log n base 2 divided by 4 power log n base 2. So which can be written as n power log 7 base 2 plus a n square by using the logarithmic formula.
So it becomes n power log 7 base 2, and it will be again n power log 7 base 2 divided by n square. So this becomes 2 square log n base 2, and this 2 becomes here n square, and it becomes n square. So directly I have taken this one, right? So this can be erased, and it will be n power log 7 base 2 plus a into n power log 7 base 2. So you can consider only the highest degree, so you can consider anything. So t power n is equal to order of n power log 7 base 2, okay, so which is nothing but order of n power some 2.81, okay. So log 7 value, once check out what is the log 7 value, that is around 2 point something, which is less than 3, okay, that is important. So now you can see, by using this Strassen matrix multiplication, we are reducing the multiplications, number of multiplications, so that we are also reducing the time complexity. So here it is order of n cube, and by using Strassen it will be order of n power 2.81, so which is less than 3, so automatically some sort of time complexity has been reduced if you use this Strassen matrix multiplication. So now you can check, so consider some 2 by 2 order matrix and use a general method for calculating the matrix multiplication, and also use this Strassen matrix multiplication method, use the formulas to solve and find out the solutions. You need to get the equal solution, the same solution, by using the general method as well as the Strassen. But here the computation time will be less when compared to the general method or the divide and conquer, which is n cube in divide and conquer, which is n power 2.81 or 18, so which is less than 3 in Strassen matrix multiplication method, right? So this is how we can use this Strassen matrix multiplication, which is, we can also say, the example or application for divide and conquer.
Previous sessions we have seen one methodology, that is divide and conquer, where we are going to divide the complete problem into different parts, and recursively we are going to solve each and every problem, and after that integrating all the solutions will give the main solution. And for that we have seen different examples or applications, right? Now we'll say one more concept of this solving a problem, that is a greedy method. So this is a one more methodology in order to solve the problem, right? And this greedy method is mainly used to solve the optimization problems, right? So it's mainly used to solve optimization problems. Now here the question is, what is meant by this optimization? So optimization, that means, so selecting the best solution among multiple alternatives. Okay, so we are having a lot of alternatives, so we need to select the best solution or the worst solution. So for every problem there might be having some constraint or may not be having the constraint. So based upon that constraint we need to select one option from the alternates. So that such type of problems we call it as an optimization. So optimization problem means it's a problem which can have multiple alternates. So usually these multiple solutions will be considered in a subset. Okay, that means a set of solutions. So the procedure or a process which gives a solution or the procedure which gives the better result is known as feasible solution. Feasible solution, right? So a normal solution, whether it may be best or worst or minimal or a maximum, whatever it may be, the solution for a problem is called as a feasible solution. And the collection of all these feasible solutions will be in a subset. Okay, so there will be a set of feasible solutions. Set of feasible solutions. And from these feasible solutions, based upon the constraint, so we can select one solution, and that will be the optimal solution, or we can call it as a best solution. So the best solution among set of feasible solutions is known as optimal solution. Okay, so don't get confused among these two, optimal solution and feasible solution. So any solution can be considered as a feasible solution, and based upon the constraint, selecting one best solution among these feasible solutions is called as an optimal solution. So that's why we call it as an optimization problem. So we need to select the best solution from these feasible solutions, right? So let us take an example, simple example that you can understand, right? So here the real world problem is traveling from city A to city B. Okay, so there is one road, so through streets, okay, through the streets, and there is a one more way, which is a bypass. Okay, so there are two solutions. So we can travel from city A to city B among these two paths. Okay, so the feasible solution is through streets and through bypass. So here you can see feasible solutions are, one is a bypass, so using the bypass, and another one is by using streets. For example, if we use a bypass, let us consider some 15 kilometers, and if you use streets, let us assume that 10 kilometers, the distance, okay, 10 kilometers. Now, which path we need to select? So here, constraint, consider a constraint. Okay, based upon the constraints, we are going to select either bypass or a street. So if you use a bypass, less traffic will be there, less traffic. And if you use streets, obviously there will be a traffic, and also there will be some signals, traffic signals. So if you use a bypass, it may take a less than 1 hour time, and if you use the traffic signals, it may or may not take, so it may take greater than or equal to 1 hour. So if you want to reach the destination within a short period, within a short time, so without any traffic, you can select this one. And if you had any work in between the city, in between the streets, then you need to use this streets. So that means we are having multiple solutions, okay, multiple alternatives. So based upon the constraints, so if you had some work, okay, if you had some work in between city, so we need to go through streets. If you are not having any work and if you want to reach quickly without avoiding the traffic signals, we can choose this bypass. So this type of problems we can call it as an optimization problem, and these optimization problems can be solved by using this greedy method, right? So hope you understood the procedure. Now what are the applications? That means where we are going to use these greedy methods. Few applications, okay, so few applications. Few applications where we are going to use this greedy method. The first one is a selection sort. So in order to arrange the elements in a sorted order using the selection sort mechanism, we'll use this greedy method. And just now we have seen finding shortest path. Finding shortest path. For example, consider a graph. So we are having, so A and B, some 5 and 10 and 6 and 5 and 7. Now see, if you want to reach from A to C, you can see you can reach C through B. So total cost will be 15. So A to C via B, it is 16. A to C directly 6, and A to C via D, it will be 12. So which one will be the shortest? So 6 will be the shortest. So in all these three cases we can reach the destination, but the constraint is minimum shortest path. Okay, so finding the shortest path with a minimum distance, and such type of problems we are going to use this greedy method. And then fractional knapsack, problem, job sequencing, okay, so finding minimal spanning tree, so there are two approaches by using a Kruskal's or Prim's algorithm. So minimum spanning tree. So all these are the few applications where we are going to use this greedy method. So in our further sessions we will see one by one. So how we can apply the greedy method and how we can find the solution for all these applications, right? So let me explain you about one example and I will wind up about this introduction of greedy method, right? So example, for understanding I'll give the example. So I am taking one example which you frequently listen. So that means I am having some 25 rupees, okay, 25 rupees, and I need a change, okay, need change with minimum number of coins, So coins available, so 5 rupees, 2 rupees and 1 rupee. So there are 3 possible coins. So we need to get a change for 25 rupees with the minimum number of coins. So the solution 1 is, see, 5 into 5 rupees. Okay, that means it requires 5 coins. Solution 2, we can take 4 into 5 plus 4 5 is 20 into 2 rupees plus 1 into 1 rupee. So how many coins it requires? 4 plus 2, 6 plus 1. So it requires total 7 coins. And simply we can say solution 3. So 25 into 1 rupee, which requires 25 coins. Similarly, solution 4, we can have 2 into 5 rupees, 10, and 10 into 2 rupees, sorry, again 5. 5 into 2 rupees, so 10, 20, 10 plus 10, 20, and 5 into 1 rupee. So total how many coins? 2 plus 5 plus 1, 5, 12 coins. So there are a lot of possibilities, lot of possibilities. So using 5 coins we can get a change for 25 rupees. Using 4 5 rupees coins and 2 2 rupees coins and 1 rupee coin, still we can get the 25 rupee change for 25 rupees, but it requires 7 coins. And still we can get a 25 1 rupee coins. So to get a 25, so it requires 25 coins. And here, in order to get the 25, we can have a 2 5 rupees coins, 5 2 rupees coins, and 5 1 rupees coins. So obviously we can get the 25 change for 25 with the 12 coins. So that will be keep on moving. These are all the feasible solutions. In all these cases we are getting the solution, right? But what is the constraint here? Minimum number of coins. This is the constraint. Okay. So this one will be the constraint. So we have to satisfy this constraint. So based upon that constraint, we can select this optimal solution among all the feasible solutions. Among all the feasible solutions, we can select the optimal solution. So this is the procedure of finding the solution for optimization problem. Okay, this procedure we call it as a greedy method. So based upon the constraint, getting the best solution or optimal solution. Okay, so if there is no constraint, so anything can be accepted. We can accept anything. Either it may be the best solution or the worst solution. Whatever it may be, we can accept anything. If there is no constraint for a problem. If there is a constraint for a problem, obviously from the multiple alternatives, we have to select the best solution which satisfies the given constraint. Right? So let's stop here. Hope you understood the introduction to this greedy method. So let us move on with the next concepts of applications, explaining the applications using this greedy method from the further sessions. So today we will discuss about an application of a greedy method. So that is job sequencing with deadlines. So we have seen the introductory part of greedy method, so which is mainly used to solve the optimization problems. So optimization problem means having more than one solution and selecting the solution based upon the constraint. So that is called as a greedy method, and one application of applying this greedy method is job sequencing with deadlines. So first let us understand the problem and then we'll move on with the solution, the procedure, how we can solve the problem. So the problem is job sequencing with deadlines. So here you can understand with the name, that is a job sequencing with deadlines. So here we'll be having the first one, jobs, the number of jobs. So we can consider them as a process, number of processes we need to execute. And second one is a profit. So profit means, so which we can profit after completion of the each and every job. Okay, so or we can say it as a cost. okay, the cost. And the third one is deadline. So the name itself indicates for every process or for every job there will be a deadline. So that particular job should be completed within that particular deadline. Okay, so these three are most important in this job sequencing problem. So we need to complete the processes or jobs within the given deadline with a maximum of profit. Okay, so that is our problem. That is our problem. And here we need to remember a few points, most important points. See, so before going for the solution for this job sequencing, the first point we need to remember is only one processor. We are going to execute on only one processor. So one processor will have to execute all the jobs. Okay, then no preemption. So if you are aware about the scheduling algorithms, you might be knowing about this preemption and non-preemption. So preemption means, so if there is any job with the highest priority, then the executed process will be put on hold and the CPU will be given to the highest priority processor. So that will not be done in this job sequencing. That means once the job is assigned to the processor, it have to complete, and that means the remaining jobs have to wait until the job gets completed by the processor. So no preemption. So once a job is given to the processor, so we have to wait until it completes its execution. So no preemption. Okay, so mainly these things, and one more, sorry. So every job takes 1 unit of time to complete. Okay, 1 unit for completion. So every job takes only 1 unit for completion. Okay, so don't get confused about this deadline and this 1 unit. So deadline means the complete time, so upon which the job has to be get completed. Okay, so but every job takes only 1 unit. Now see, these three things are the most important and we have to remember before applying the job sequencing. Only one processor, no preemption, and every job takes 1 unit for completion. Right? Yes. Now we'll see the procedure, or we can call it as an algorithm. So the first step, let us take an example, then we'll move on with the algorithm. So first we'll go with the example so that you will be understanding perfectly. Example. So let us take a number of jobs. Let us consider 5 jobs: J2, J3, J4 and J5. So these are jobs. And the second point is a profit. How much profit we'll get after completion of that particular job. Let us take this as 15, 10, 20, 25 and 5. This is a profit. Okay, this is a profit. And the third one is the most important, that is a deadline. Okay, so deadline. Let us take 2, 1, 3, 2. Okay, let us say randomly I have taken this one, right? So this is a deadline. So we have assumed that only one processor, no preemption, and the last point is every job will take 1 unit for its completion. So let us assume that this is a two units, this is a 1 unit, 3 units, 3 units and 2 units. Now what is the process we have to do? So first we have to find out the maximum deadline, max deadline. So what is the maximum deadline here? So in order to avoid the confusion, let us take it as 3 and let us take it at 1. Okay, right, maximum deadline among all the deadlines, what is the maximum? So the maximum is 3, so 3. Now we have to draw the Gantt chart. Gantt chart means we need to draw this one. See, so this is a Gantt chart: 0, 1, 2 and 3. See, this is 1, this is 1, 2 and 3. So 3 units. You can assume that this is a 3 units, and we need to complete the jobs with the highest, more priority, with more number of priority, right? Now, what do we have to do? The next one, sort all the jobs in a descending order with respect to the profit. So, sort in descending with respect to profit. Here on the end, right? Okay, profit. Now rearrange the jobs based upon the deadlines. First, what is the highest? 25. So J4 will be the first with the 25, and the deadline is 3. What's the next one? 20. So J3 21. So J3 21. Next 15. J1 15 2. J1 15 2. Next, J2 10 1. J2 10 1. Next, J5 5 and 2. So we have arranged the complete jobs in a descending order with respect to the profits. See, for example, let us consider this was not done. Okay, this was not done. So in an order, complete the jobs. So J1 should be completed within a 2 deadline. So let us take here J1 with a profit 15 and J2 with a 1 block, but it doesn't happen here because during the first unit J1 will be completed. So J3 it was also not completed. Next we can go with the J4 with a 25 profit and J5 with a 5 profit. So you can complete the J1, J4, J5, the 3 processes with a profit. So 15 plus 25 plus 5. So which is nothing but 45. Okay, and also we can complete. See, we can complete J1. Next J4. Okay, sorry, already we have done. So we can complete here J2, J3 and J4, right? So first J2 will be taken here, J3 we can complete, J4 we can complete, and the profit will be 10 plus 20 plus 25. Okay, so here we will be having a lot of solutions, and we can't say that this will be the optimal solution. Okay, so there will be a lot of solutions. So we can execute J1, J4, J5, we can execute J2, J3 and J1, we can execute J2, J3, J5, etc, etc, right? So what happens here? So we need to select the optimal solution based upon the constraint. So here what is the constraint? We need to get the maximum profit. Now in order to find out that maximum profit, we are going to see this process, sort in a descending with respect to the profit. So this we have done. Now what we are doing? So first J4, the first process with the highest profit. So The constraint is a profit, highest profit. So based upon the profit, we are arranging the jobs in a descending order. So what is the maximum deadline limit? 3. So we can assign J4 in the last one. J4 with a 25. Okay, hope you understood. So the maximum deadline to complete the job 4 is 3. So we are going to select the third one. That means the last option. Okay, in the third unit. So the profit will be 25. So this completed. Next, J3 with the highest priority. So because this is a descending order. So 20 is the next priority. And this J3 should be completed with a 1 unit. Okay, deadline is 1. So we can't assign J3 here. Because after 1 we can't assign it. Because 1 is the deadline. So J3 will be assigned here. J3 will be assigned here with a 20 profit. Next, J1, 15. That's the third highest profit. And what we are doing? That is 2 is the deadline. So here we can assign the J1. So what is the highest profit? 15. So 15 is the profit. Now the overall profit of completing the 3 jobs J3, J1, J4. What's the profit here? So 20 plus 15 plus 25. So what happens here? So 35 and it will be 60. So 60 is the highest profit in order to complete the jobs. Okay, so this is how we have to solve the job sequencing using the greedy method. So greedy method means we'll get the alternate solutions, and from that alternate solution based upon the constraint we are going to select the best or optimal solution. So here also we can execute J1, J2, J3 or J2, J3, J5 in these 3 slots, or J2, J4 and J5, or J2, J1 and J4. So there will be a lot of options. Okay, we can complete. So let us take J2, J4, J5. So this is one solution. Okay, executing all these, completing all these 3 jobs with a particular profit. What is the profit here? J2 10, J4 25. So 35 and it's a 40. And also you can go with the J2, J1 and J4, J2 10, 15, 25 and 25. It will be 50. So in both the cases we will get the profit, but the constraint is getting the best solution or optimal solution based upon the constraint. Constraint is the highest cost, okay, with a high cost. So for that we have done, so the highest profit, high profit is 60 by executing J3, J1 and J4, 3 jobs. Okay, so this is how we can solve the job sequencing with deadlines problem. Okay, now we'll go with the algorithm. Hope you understood this one. So take a few more jobs. Let us take some 10 jobs and try to solve the problem so that you will be understanding more, right? So now I will write the algorithm and I will wind up. Okay, so algorithm. So step 1. What is step 1? We need to find out the maximum deadline. Find maximum deadline. And step 2. What is step 2? So after finding the maximum deadline, we need to draw the Gantt chart. Draw Gantt chart with maximum deadline. Maximum deadline. So we have drawn. And step 3, after completion of this Gantt chart, we need to sort the jobs according to profits. Sort all jobs with respect to profits. Step 4. What we have to do? So we have to find out the appropriate slot to fix the job. Search empty slot to fix job. Okay, so we having or in a deadline near to its maximum, near to its maximum. So this is the process we are going to do, right, for solving the job sequencing with deadlines. So here the time complexity for this one, time complexity. So first we are going to sort out this one. Okay, only 2 steps. So sorting all the jobs with respect to the profits, which will give the order of n log n. So we can apply any sorting mechanism, quick sort or bubble sort, anything. So I'll go with the quick sort. Okay, because we have seen in our previous sessions by using the divide and conquer. So it will be order of n log n plus what we are doing, searching the empty slot to fix the job in a deadline near to its maximum. Near to its deadline. Okay, right? So how many searches we have to do? So if there are n jobs, we have to search for n slots. Okay, so obviously it will be order of n square. So n jobs, n slots. Okay, m jobs and n slots, or n jobs and n slots, whatever it may be, no problem. So it will be order of n square. Order of n square. So the highest degree, what is the highest degree? This one. So the time complexity, is order of n square. Order of n square for this job sequencing with deadlines, and we have followed the greedy method. So that means finding or getting the feasible solutions, and from that feasible solutions we are selecting the optimal or best solution. So first let us see what is this spanning tree, and then we'll go with the construction of this spanning tree. So a spanning tree is a subgraph. So we all know about the graphs. So graphs are nothing but connected nodes with the edges with the cycles, right? So it is, the spanning tree is a subgraph of a graph with the vertices and edges. So a graph will be having the vertices and edges with the cycles, right? But here the tree means it's a subgraph with no cycles. So here if it is not having any cycles, we call it as a tree, right? Now, so we need to follow a few points or a few rules while constructing this spanning tree. The first one is, so the spanning tree should connect all vertices of a graph, right? So it should contain all the vertices which are available in the graph in the spanning tree. And the second one, if graph is having n vertices, then the spanning tree should have n minus 1 edges, right? So n vertices in the graph, then spanning tree will be having n minus 1 edges. And the third one should not contain any cycles. Should not contain any cycles. So we need to follow these rules while constructing the spanning tree, right? So let us take one example, so graph, and we'll see how to construct the spanning trees. So first we'll consider the graph and then we'll construct the spanning trees from that particular graph. See, so we have to follow all the rules, right? So let us take an example with a 4 nodes. So A, B, C and D. So these are the 4 nodes and this is a connection between all these nodes. So this is a graph. Okay. So edges, vertices and cycles, right? So now we should construct the spanning tree. So what is the first rule? First rule is number of vertices should be equal. Number of vertices must be equal in both the graph and spanning tree. So we have to connect all the edges. We need to connect all the edges. So I am writing all the edges here. Next, so these, if there are 4 vertices, we should connect with 4 minus 1 edges. So I will connect this one. So A to B, A to C and C to D. So this is a construction, right? So you can observe here, here we are having a 4 vertices and the edges are 4 minus 1, that is 3 edges. So this is one spanning tree. And another case, let us see A, B, C, D. So let us consider this one. So this is also a possible spanning tree from this particular graph, right? So because all the edges, all the vertices has been connected and the number of edges are n minus 1, that is 4 minus 1, and there is no cycle, right? And one more possibility. So this is one more possibility, right? So here also all the 4 vertices has been connected with n minus 1 edges, and there is one more possibility here. So this is one more possibility. Here also all the 4 edges, 4 vertices has been connected with 3 edges, because we are having 4 vertices, so the number of edges must be 4 minus 1. So this is the cyclic graph, and this is a acyclic graph. Acyclic graph is nothing but our trees, right? So all these are the spanning trees. Okay, all these are the spanning trees, right? So one graph can have a multiple spanning trees. So here we can have the 4 possibilities, right? And if you consider one more example, like a triangle shape. So this is a graph. So we are having 3 vertices and 3 edges, so that it's a graph. So this can be constructed as, so A to B, B to C, A to C, C to D, right? And A to B and C. So these are all the different possibilities of spanning trees can be constructed from this particular graph, right? So hope you got an idea about this spanning tree. What exactly this spanning tree? Spanning tree is a subgraph from the original graph. So with n vertices and n minus 1 edges, right? So we need to follow the 3 points. One is all the vertices should be connected, and if n vertices are there, n minus 1 edges should be there, and there should be no cycles. So this is all about our spanning tree. Now, what is the minimum spanning tree? Now let us see the concept of minimum spanning tree. So minimum cost spanning tree. So it is called as a minimum cost spanning tree. So let us consider the graph A, B, C and this one. This is a graph, right? This is a graph. So each edge will be having a cost. Each edge will be having a cost. We can also call it as a weight for the particular edge. Let us take here some 5, some 2, some 3. So the cost of an edge A to B is 5. The cost of an edge from B to C is 3. The cost of an edge from A to C is 2. Now construct the possible spanning trees. So the possible spanning trees are A to B, B to C, A to B, A to C, A to C, C to B. So these are all the possible spanning trees, right? All the possible spanning trees. Give the edges here. So 5 and 3. And here 5 and 2. 3 and 2. So now you have to, so you can observe here all the vertices has been connected. Okay, all the vertices has been connected, and here also all the vertices has been connected, and here also all the vertices has been connected. Right. So here you can see there is an edge A to B, B to C. There should not be a cycle, right? So here it is A to B, B to C. So if you add one edge from C to A, so what happens? The starting vertices and the end vertices same. That means it forms a cycle. So we should not connect this one. So that's why we are not connecting, and this is a spanning tree, right? Now cost for this spanning tree is 5 plus 3, 8, because there are two edges with a weight 5 and 3. The cost of this particular spanning tree is 8, and the cost for this one is 7, 5 plus 2. So the cost for this one is 3 plus 2, it's a 5. So you can observe here, for every spanning tree we are finding the cost. So here the cost is 8, cost is 7, cost is 5. Now we need to select the minimum cost spanning tree. So we will select the minimum cost spanning tree. That means the tree with a minimum cost of edges, right? So minimum weighted edges. So here there are two approaches to find the minimum cost spanning tree from a graph. So that is, one is a Prim's algorithm, another one is a Kruskal's algorithm. So in today's session we'll discuss about the Prim's algorithm. So before applying the Prim's algorithm on the graph, make sure that the graph should be weighted, connected and undirected. So unless the graph is weighted, connected or undirected, so we can't apply the Prim's algorithm. So make sure the first point before applying the Prim's algorithm. So the graph should be weighted, connected and undirected. And coming to the steps. So first we need to consider any vertex, because so we know the spanning tree definition. Spanning tree is a subgraph from the graph without any cycles, consisting of all the vertices of a graph. Right? So consider any vertex of the graph. And the second step, find all the edges from the selected vertex to all the new vertices. So find all the edges. So among all the edges, you need to select the least weighted edge. So among all the edges, we need to find the least weighted edge and include it in a tree. So we need to construct a tree for that selected vertex and give in the least weighted edge. And if the least weighted edge forms a cycle, so if you include this least weighted edge into a tree and if it forms a cycle, then simply discard. So if it forms a cycle, then simply discard that one and consider the next least weighted edge. So once you find the least weighted edge, you have to include it in a tree. So after including it in a tree, if it forms a cycle, simply discard that one and consider the next least weighted edge and include it in tree. And the third step, repeat the same step 2 until all the vertices are included in a tree. So once all the vertices are included, automatically that will be the minimum cost spanning tree. Right? So this is how we need to find the minimum cost spanning tree with a Prim's algorithm. So here now we'll see an example and we'll find the minimum cost spanning tree by following all these rules. So let us take an example. So consider one graph. So consider this graph. So let us take some weights. So let us take these weights. Okay, this is a graph. Consider this graph. And we need to find the minimum cost spanning tree for this particular graph. So what we have to do, first consider any vertex. So I will consider A. I will start with A. So this is a A. So I have included this one in the spanning tree. Now consider all the edges from A. So you can see A to B with a cost of 2 and A to C with a cost of 3. Right? A to B with cost 2, A to C with cost 3. So we need to select the least weighted edge because A is having two edges. One is from A to B, one is A to C, A to B, A to C. So consider the least weight. So this is the least among these two. So we need to add this B to the spanning tree. Now the spanning tree will be A followed by B. So with a cost 2. So this is the tree. This is the tree. Now what is the new vertex here? B. So what is the remaining vertex? Consider this one A to C with 3 and consider the edges from B, right? So from B there is a vertex from B to A which is already covered, right? Because this is a undirected. Okay, this is a undirected. So B to A is covered. So we need to consider B to C and B to D. So B to C with a cost of 5 and B to D with a cost of 3, right? B to A, B to C, B to D, right? Now what happens among this one we are having a two edges with a minimum cost 3, so you can select any edge, no problem. So I will select this one B to D. I will select this one B to D. Now the tree will be A, the tree will be A followed by B, B to D. So the edges are 2, 3. Now the spanning tree becomes this one. So in the first step the spanning tree is this one. That means only one vertex. In the second step, so first step, second step, and this one is the third step. Now consider the remaining edges. What are the remaining edges? A to C with a cost of 3. B to C with a cost of 5, right? Now D is added here. Now consider the edges of D. So you can see D to B, which is already done because of undirected, right? So you can simply use this one bidirectional, right? Right. So B to D is completed. Now D to E. So D to E with a cost of 2. And D to F with a cost of 3, right? So the edges of D are D to B, D to E and D to F. So among the D to B is completed, right? Now among these, what is the minimum cost? So this one, least edge, least weighted edge. So consider this one. Now the spanning tree will be A, edge to B, edge to D, and from D to E. So the cost is 2, 3 and 2. Cost is 2, 3 and 2, right? And next, what are the remaining edges? Simply write here A to C with a cost of 3, B to C with a cost of 5 and D to F with a cost of 2. Now E is added. So what are the edges of E? E to D, E to C, E to F. So E to D is completed now. Just discard that one. E to C. So E to C is not there. So we can write the edge E to C with a cost of 4. And E to F with a cost of 5. E to F with a cost of 5. E to F, right? Now among this one is the least weighted edge. Least weighted edge. D to F. So see,
our graph, our tree will be A, B, D, E and F, right? So this is 2, weight 3, this is again 2, now again it's a 2, again it's a 2, right? You can observe here whether all the vertices have been covered or not, A, B, D. So there is no, C is not there, right? So you can continue the process. So what are the remaining edges? A to C with a cost 3, B to C with a cost 5, E to C, D to F is completed. So E to C with a 4, E to F with a 5, right? Next, F, we have reached to F. So the new vertex is F. So write down the vertices of F. So F to D, F to E, right? F to E is completed. So F to D with a cost of 3. Now you can see among all these things, what is the minimum? A to C or F to D, right? F to D is also completed, right? F to D is also completed, so you need not go with this one. And one more thing is F to E. So that's also completed. F to E, we have written F to E here, right? So now among all these things, what is the minimum cost? A to C. So consider A to C and observe whether it is giving the cycle or not, it forms a cycle or not. So if you apply A to C, it doesn't form a cycle. So consider this one. So A to B, D, F, E, C. Right? Now you can give the weightage 2, 3, 2, 2 and 3. So you can observe here A to B with 2, B to D with 3, D to F with 3, D to F with 3. So D to F 3, okay, D to F is 3. So this is D to F with 3 and then D to E is 2 and A to C is 3. So you can observe here all the vertices have been constructed, that means included in the tree. So A, B, C, D, E, F. So here we are having total 6 vertices. So all the 6 vertices have been included. And now you can observe here the remaining edges. What are the remaining edges? So consider B to C with a 5 and E to C with 4 and E to F with a 5. So if you consider B to C, so if you add a B to C, it forms a cycle. So we have to discard this one, right? E to C 4, E to C. If you just connect this edge, again there is a cycle. So A, B, D, E, C, A. So again you need to discard this edge. And E to F, again if you connect this edge E to F, again a cycle forms. So again we need to discard these edges. So we have to discard these edges so that we can have this one. Okay. So hope you got this one. So I think these things are not clear. So I'll write the edges here. E to C with a 4 and E to F with a 5, right? So I think now it's clear. So we have to consider from the single vertex. You can consider any vertex and consider the edges, all the edges from that vertex to new vertices, and consider the least weighted edge. Okay, and continue the process until all the vertices will be connected. So this is the spanning tree, minimum cost spanning tree for the given graph. What is the cost here? So you can observe the cost. I will write here. Cost is equal to, so what is the cost? 3 plus 2 plus 3 plus 3 plus 2. 3, 2, 3, 3, 2. So what is the total cost here? You can observe. So 5, 8, 10, 13. So 13 is the minimum cost for this particular tree. So the cost is 13. The cost is 13 to construct this particular spanning tree. So this is the procedure we need to follow for Prim's algorithm. Okay, so consider a graph, and finally we are getting the minimum cost spanning tree. So we'll get a many spanning trees from this graph. So as we discussed in the previous session, right? So we can get a many spanning trees from this graph, but we need to find out the minimum cost spanning tree. So this is the minimum cost spanning tree obtained from this particular graph. So let us consider this graph, and now we are supposed to find out the minimum cost spanning tree for this particular graph. So just recalling the steps, the first step we can consider any vertex, and the second step we need to find out all the outgoing edges from that vertex to new vertices, and consider the least weighted edge and include it on a tree. And after including the least cost weighted edge on the tree, if it forms a cycle, so we have to discard and we need to go for the next least weighted edge, right? And we need to repeat the same thing until all the vertices are included in a tree. So let's start with this one. So this is a Prim's algorithm. So by using this Prim's algorithm, we are going to find out the minimum cost spanning tree. So first we need to consider any edge, right? So the first step I will go with here. So consider A. Now what are the edges from this A? So edges are like A to D with a 5, and A to F with a 7, and A to B with a 14, and A to C with a 21. So you can see from A we are having a 4 edges: A to B, A to D, A to F, A to B, and A to C. Now the next step, we need to select the minimum cost edge, right? Least weighted edge. So among these, this is the least cost edge, right? So consider this one. So our next one will be A to D. A to D with a cost of 5. A to D with a cost of 5. Now, what are the remaining edges? Simply write down all the edges. So one is A to F with a 7, and A to B with a 14, and A to C with a 21. Now, consider the edges from D, right? Because the new vertex included in our tree, D, so write down the edges from D. So two edges are there. D to A already done. So D to F with 13, D to F with 13, and D to E with 22. D to E with 22, right? So among all these edges, so this is the first step. So among all these edges, what is the minimum cost? So 7, 14, 21, 13, 22. So this is the minimum cost. So consider this one. Okay, consider this one. Right? Now, the graph, the tree becomes A to D with a cost of 5, and from A to F, so the next cost is A to F. So A to F with a cost of 7. So what are the remaining edges? See, after this one, what are the remaining edges? You simply go with this one. So A to B with a 14. Next, A to C with a 21. A to F. So this already happens, right? Sorry, D to F. Okay, D to F.
So D to F with a 13 and D to E with a 22. So now we are having a one more vertex, that is F. So now consider the edges of F. So from F we are having how many edges? So 1, 2, 3, 4 and 5. So among all these things, F to A we have completed. So F to D or D to F. This is a bi-connected, so F to D or D to F both are equal. You can simply leave. F to E with a cost of 15. F to G with a cost of 18. F to B with a cost of 2. So these are the edges from F. So among all these things, consider the least cost weighted edge. So among these, this is the least cost weighted edge, right? Now the tree will be A, D, F, B, right? So this is 5 and this is 7 and this is 2. Now our tree is like this, okay, tree is like this. Now the new vertex added here, and consider all the remaining edges, okay, consider all the remaining edges. So what are the remaining edges here? So all these are the remaining edges. A to B with a 14, next A to C with a 21, and D to F with a 13, and D to E with a 22, F to E with a 15, next F to G with 18, F to B with 2. So our tree consists of a new vertex B. Now consider all the edges from B. So from B we are having only two edges, B to C and B to G and B to C, B to G, B to F and B to A. Now B to A, so this is already covered. B to F already covered, right? So we should not consider this one because we have already done, right? So this is already done, so we should not consider. So B to F, there is no edge. So B to G 19. So B to G with 19 and B to C with 15. B to C with 15. Consider the least. Consider the least among all these things. What is the least one? So this one is the least. D to F is 13. So D to F is 13. So if you consider D to F, so it forms a cycle. You can observe here. It forms a cycle. So we should discard this D to F. We should discard this D to F because if you add this one, we'll get a cycle. So we should not consider this one. Next least. So there are two edges which are having the next least costed edge. So F to E or B to C. In such cases, you can consider any edge. Okay, here we are having two edges with the minimum cost. You can consider any edge. Okay, so I will consider B to C. I will consider B to C. Now the tree will be like this: A, D, F, B. Okay, so this is 5, this is 7 and this is 2. Now we need to consider B to C. What's the B to C here? Yes, B to C with 15. B to C with 15. Now consider all the remaining edges here. So A of B with a 14, right? So you can observe here. Okay, let us write down. No problem. Next, A to C with a 21, D to E with a 22, and F to E with a 15. Next, F to G with a 18, and B to G with a 19. Because we should not consider this one because we have already done the edge from B to C. Now there is a new vertex here included in the tree. Now consider the edges of C. So C to B, there is no edge, right? So C to B, sorry. So already C to B there is an edge, right? So C to A, there is an edge here already covered. C to B already we have constructed in the tree. C to G is 3. C to G is 3. And C to E is 4. C to E is 4. Right? So among 4 edges from C, C to A is already written. C to B already considered in the tree. C to G and C to E. So this is the next one. So we need to select the least cost from this one. So which is C tends to G with a 3. So from C you can construct a G, so which doesn't form the cycle. So now, so I will consider here A with a D with F, B, C and G, right? So the weightages are 5, 7, 2, 15 and the edge is 3 here. Okay, edge is 3. Now we have taken one edge, that is a new vertex G. So what are the remaining edges? See, you can observe here. So A tends to B with a 14 and A tends to C with a 21, D tends to E with a 22, F tends to E with a 15 and F tends to G with 18, B tends to G with 19 and C tends to E with 4. Now the new vertex is G. Now consider from G. So G, we are having 1, 2, 3, 4 and 1, 2, 3 and 4. So first G to F. So is there any edge? There is no edge. So we have to consider G to F. Okay. So let us consider here, right? So G to F with 18. Next, G to B. G to B. There is considered. We have considered, right? G to C. So we have already constructed the tree. So G to E is 2. G to E is 2. So these are the edges. Among all these things, consider the least. So this one is the least, G to E. Now construct the tree with this one. So A, okay, A to B, F, F to B, B to C, C to G, and the last one is G to E. G to E. So the cost, let us write down the cost. It's a 5 and it is 7, it is 2, it is 15, it is 3 and again the last one is 2. Right? So this is the tree and now you can observe all the vertices has been covered. So A, B, C, D, E, F and G. Right? So all the vertices has been covered here. So we can stop here and consider the remaining vertices. So consider this A to B. So we have considered G to E with 2 and we have included the edge. Consider A to B. If you consider A to B, it forms a cycle. So we should discard. A to C. If you consider A to C edge, right? Again, it's a cycle. D to E. So D to E. Again, it forms a cycle. F to E. F to E. Again, it forms a cycle. C to G. Sorry, F to G. F to G. Again, it forms a cycle. B to G. Again, it forms a cycle. So C to E. It forms a cycle. G to F. G to F. Again, it forms a cycle. So all the edges has been covered and all the vertices has been covered here. And now you need to find the minimum cost of this particular tree. So this is the minimum cost spanning tree. So this is a minimum cost spanning tree. So you can see, so we are having all the vertices, okay, we are having all the vertices, and if the graph is having n edges, n vertices, the edges should be n minus 1. So how many vertices are there? 1, 2, 3, 4, 5, 6 and 7. 7 vertices are there. So it should have 7 minus 1, 6 edges. So 1, 2, 3, 4, 5 and 6 edges. So it satisfies the spanning tree, and you can apply, you can see this is the minimum cost spanning tree for this particular graph. And here the minimum cost, I will write here, I will write down here. So the minimum cost is, so how much? 5 plus 7 plus 2 plus 15 plus 3 plus 2. So how much it is? 12, 14, 29, 34. So minimum cost spanning tree, the cost of this particular spanning tree is 34. Right? So hope you understood. First you need to select any vertex and consider all the outgoing edges of that particular vertex to the new vertices, and select the minimum or least weighted edge from the among all the vertices, and if that edge forms a cycle in a tree, discard that edge and consider the next least cost weighted edge, and repeat the same process until all the vertices are included in the tree. So here you can see all the vertices are included in the tree. So we have stopped the procedure and we have checked all the edges. So all the edges, if you consider any one of the edge, it forms a cycle here. So that's why we have to remove all the edges. We need to discard all the edges, right? So this is how we can find the minimum cost spanning tree by using the Prim's algorithm. And we'll see one algorithm to find the minimum cost spanning tree, that is a Kruskal's algorithm. So in the previous sessions, we have seen one algorithm to find the minimum cost spanning tree, that is a Prim's algorithm. So before going to that, let me revise the previous concepts, that is what is a spanning tree. So consider a graph, and a spanning tree is a subgraph derived from that particular graph, so with n vertices and n minus 1 edges, right? And minimum cost spanning tree means the spanning tree with a minimum cost. Okay, every edge will be having a cost. So having a minimum cost to construct the tree is called a minimum cost spanning tree. So in order to find out this minimum cost spanning tree, there are two approaches as we have discussed earlier, that is a Prim's algorithm and Kruskal's algorithm. So in the previous sessions we have seen the Prim's algorithm. Now we will see the Kruskal's algorithm. So here the step 1, the first step means here arrange all the edges in ascending order based on cost. So every edge will be having their own cost. So we need to first arrange all the edges in ascending order based upon the cost, right? Ascending order means lower value to the higher value. So we need to find the minimum cost spanning tree. So that's why we are using this ascending order. And then step 2, consider least cost weighted edge and include in the tree. Include it in tree. So consider one by one and just include that in a tree. And if the edge forms a cycle just ignore and consider next least cost weighted edge. Least cost weighted edge. So every time we'll consider an edge and we have to include that on a tree. So if by adding that edge, if it forms any cycle, so just we have to ignore that edge and consider the next least cost weighted edge, because a tree should not have the cycles, right? So graph can have the cycles, but a tree should not have the cycles. So here we are using this Kruskal's algorithm to find the minimum cost spanning tree, right? And the third step, repeat step 2 until all the vertices are included in a tree. So we know the spanning tree, right? So if the graph is having some n vertices, then the spanning tree should have the n vertices with n minus 1 edges, right? So similarly, we have to repeat the step 2 until all the vertices are included in a tree. So by following these steps, we can find the minimum cost spanning tree by using this Kruskal's algorithm, right? So hope you understood this one, and now we'll see an example and we'll find the minimum cost spanning tree. So let us consider this example, and this is a graph and we need to find the minimum cost spanning tree. So what is the first step? We have to arrange all the edges in an ascending order based upon their cost. So here the least cost among these things are 2. So first let me write all the edges with a 2. So here you can see A to B. A to B is a 2 with a cost 2. So this is a bidirectional, because this is a bidirectional. We can simply consider A to B or B to A. Next, there is one more thing, that is a 2, D to E. Again it is a 2. Next, 3. So we are having A to C. A to C with a 3. And one more, B to D. B to D with the cost 3. And D to F. D to F with the cost 3. Then what about next one? It's a 4. So 4, B to E. B to E with a 4. And C to E with a 4. Next one is a 5. So B to C, 5, and E to F is 5. So you can observe these are the edges arranged in an ascending order, because you can observe the cost, so from lower to higher. Now what is the first step? Consider each and every least costed edge and include it in tree. So first consider A to B. So I will construct the tree here. So A, B with a cost 2. Next, D to E. So D to E. So D to E. So here it is a D. E. So what is this one? D to E, again 2. Next, A to C, 3. A to C, there is no C, so we have to add it. A to C, 3. Next, B to D. B to D. So it doesn't form a cycle, right? B to D. So just include that one. B to D, again it is 3. Next, D to F. So there is no cycle, so I will construct here F. D to F, it is 3. Right? Next, B to E. So if you give the edge here, B to E, it forms a cycle, right? It forms a cycle. So we should not consider this one. So this should be rejected. C to E. C to E. Again, if you form an edge, if you give an edge, again it forms a cycle, right? A, B, D, E, C, A. So we have to reject that. B to C. B to C. Again, if you form an edge, so it forms a cycle. So we have to reject. E to F. E to F. If you consider the edge here, again it forms a cycle. So you have to reject. So you can see in our graph there are 6 vertices. 6 vertices, and our spanning tree consists of 6 vertices. 6 vertices. Right? And here the edges 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. So 3, 6, 7, 8, 9 edges. So there are 9 edges. You can observe here 1, 2, 3, 4 and 5. So 5 edges, which is nothing but vertices minus 1, right? If there are n vertices, there should be n minus 1 edges. So it satisfies. Now you can observe all the vertices are covered, so we can consider this as a minimum cost spanning tree, which can be represented as MST, minimum cost spanning tree. So now what is the cost here? Consider cost here. So cost of this one will be 3 plus 2 plus 3 plus 3 plus 2. So the cost will be 5, 8, 11 and 13. So cost is 13. So the minimum cost we can create or construct the spanning tree is with 13. So you just remember this is the same example we have taken in the Prim's algorithm also. So there also we have constructed the minimum cost spanning tree with a cost of 13. So once just observe the session. So I will post the link in the description so you can follow that one. So that is the procedure of Prim's, and this is the procedure we need to follow for the Kruskal's. So this procedure is Kruskal's algorithm, right? So first we have to arrange all the edges in an ascending order based upon their cost, and then consider each and every edge and construct a tree. And if by adding the edge to the tree, if it forms a cycle, just ignore that and consider the next least cost edge, right? So we have to repeat that one until all the vertices are covered. So here there are 6 vertices. All the 6 vertices have been covered with a cost of 13, right? So hope you understood this one. So this is a Kruskal's algorithm to find the minimum cost spanning tree. Yeah, one more application of greedy method, that is Dijkastra algorithm. So someone will call it as a Dijkastra or Dijkastra. Okay. So today's topic is Dijkastra algorithm. So using greedy method. So we have seen the greedy method. What is a greedy method? So selecting the best or optimal solution from a solution set is called the greedy method. And here the Dijkastra algorithm means finding the shortest path from the source vertex to all the remaining vertex in a graph. So we know that a graph is a connected edges for all the vertices. So for that particular graph, so finding the shortest path from the source node or source vertex to all the remaining vertices. So this is also called as single source shortest path. Single source shortest path. So the main aim is to find shortest path from source vertex to all remaining vertices in a graph. So this graph can be directed or undirected graph, right? So this can be directed graph or undirected. So this algorithm will be suitable for either a directed or undirected. So before going to this one, let's have a small introduction about the graphs. So graphs will be having vertices or vertex and edges. So vertices are represented as a circle and edges are represented with a arrow marks. So this is a directed and this is a undirected. So if you are directing towards some particular vertex, that will be represented with this arrow, and if you are not directing, it will be like this arrow. And widths. So for every edge, so this is a numerical, right? For every edge which connects two vertices will be having some sort of cost, or we call it as a weight. Example, a graph A, B, C. So here we are not using this directed, right? This is an undirected graph, and it becomes directed if the graph is in this way. And here the weight of this particular edge which connects the vertex A and vertex B is represented with a numerical. So this is a numerical. So this is called as a weight. So 5 and 4. So this will be calling as a weights, and this will be calling as a edge, and this will be calling as a vertex, and we can also call it as a nodes, or we can also call it as a hops. Okay, depends upon the subject course. So vertex, node, or hops. So this is a small introduction about this graph. Now the single source shortest path will find, first we have to find out the source node. Let it be, this is a source node. For example, this is a source node. Okay, don't get confused here. I'll write source, right? Source is A. So from A, what is the shortest path for all other vertices? So A to B, A to C. Okay, so that we have to find using this single source shortest path. So where it will be used? So it will be used in order to find the shortest distance in between one place to another place. And also the same thing will be applied in a networking concept for routing a packet. So it will find the shortest path, and through that shortest path the packets will be transferred. So in many applications we will use this Dijkastra algorithm. So Dijkastra or Dijkastra algorithm, right? Whatever it may be. Now we will see what exactly happens in this single source shortest path using this Dijkastra algorithm. I'll explain with a small example so that you will be understanding, right? So I'll take it A, B, C, D. So this is an undirected. So this Dijkastra algorithm can be applicable for both the directed and undirected. I am giving the directed, undirected. So I will give the values 4, 10 and 15, right? So 5 is the weight given for this edge which connects vertex A and B. 15 weighted edge between B and C. 10 weighted edge between D, C and D. 4 weighted edge between A and D. So this is a vertex, this is an edge, this is a weight. Now we need to find, so this is a source. Let us assume this as a source. So we need to find the shortest path from A to B, A to C and A to D. Okay. See, usually A to B there is only one edge, that is a 5, and A to D there is only one edge, it's 4. What about A to C? So A to C can be done through D or through B. If A to C from B, the cost will be 5 plus 15, total 20. And if you use this path, that means through D, it will be 14. So which will be the minimal shortest path? So in order to reach C, A can travel through D, which gives the minimal cost. So here you can see we are having a multiple solutions from these multiple solutions, we are selecting the optimal solution, right? So that's why we call this as an application for a greedy method, right? Now we'll see the procedure. What happens first? Okay, so step one, find out the source node. Find source node. Find the source node. So in this example, let us assume source is A. Source is A. And step 2. Initialize the weight of or the cost of A, that means a source, is 0 and all other nodes cost is infinite. So initialize cost of source is 0 and cost of other nodes or vertices is infinite. So I'll give the weights here itself. Okay, I'll give the weights here. So I'll represent with black, small difference. So 0, and here it will be infinite, and infinite. So this is a cost. Okay, don't confuse. This is a weight and this is a cost. So from source, how much cost it takes to reach the destination. So here A is the source, and if A is the destination, the cost is 0. And if B is a destination, let it be, assume it as infinity, right? So next, step 3. Okay, so find cost of neighbor vertices from source. So what are the neighbor vertices? So B and D. So how we can say that B and D are the neighbors, and why not the C? Because there is a connectivity between A and B and A and D. Okay, so if it is a directed graph, consider the outgoing arrow marks, not the incoming arrow marks. Outgoing arrow marks. So if it is a directed, right? Now the neighbor edge or neighbor vertex will be D, not B, because B is connected to A, but not A is not connected to B, because this is a direction, right? So in the absence of this arrow, that means this is a undirected graph. So we can say A to B and A to D, both are the neighbors. So A is having a neighbors of A to B and A to D. So find out the cost. So there is direct connection. So obviously A to B, the cost is a 5, and A to D, the cost is a 4. Right? Now change the cost. Initially, so next, step 4, change the cost on vertices, or you can see update the cost on vertices. Now you can see initially, so how we can check means the minimum of see what happens here, the cost plus weight of that particular edge, comma, existing cost. So we need to consider any one, minimum of cost plus weight and existing cost. See what happens here, A to B is a 5 and A to D is a 4. So there is a direct connectivity. So we have to go with either 5 or infinity. Okay, so here in this example you can see A to B means 0 plus 5. So here the cost is 0 plus weight is 5 comma infinity. So among this we have to find out the minimum. This is for A to B, and similarly A to D, the minimum of 0 is the cost plus weight, 0 plus 4. 0 plus 4, what is the initial cost? Infinite. So in both arguments we need to consider the minimum. So obviously it will be 5 and obviously it will be 4. Hope you understood now. Okay, now we need to update the cost on vertices. So simply remove this one. So remove this one and update it with D, 4, right? And update this one with 5. Okay. So this is a 4 and this is a 5. Okay, 4 and 5. Now what happens? Right. Next, step 5. What we have to do? Now place the visited node in a set, visited set. For example, I mean here we will write a visited set. So write down the set. So what will be the visited node? A, because we have considered A with the shortest cost, and then okay, so and then we are updating the neighbors. So this node has been visited. So once the node is visited, we need not revisit that node. Okay, so that's why we are placing the visited node here. Now step 6, consider vertex with minimum cost. Now the cost, this is already visited, so we need not consider this one. Consider the cost of B, which is 5, C infinity, D 4. So these 3 are unvisited links, okay, unvisited vertices. So here we can have B with a 5 cost, D with a 4 cost, and C with a infinite. So among these we have to find out the minimum cost as a source. Now we can change. We can select that one. So among this we can simply say D with a cost 4, which is a minimum. Now consider this one as a visited. Okay, because this is the shortest cost among these 3. So now add it here, A and D. Okay, then step 7, update the cost on neighboring vertices. So what are the neighbors? So this has been completed. We are selecting the source as node D. Now we have selected A, and now we are selecting D. What are the neighbors for D? So one is A, there is a direct link to A, right? But A is already visited. So we need not bother about this one. We are having only one node, that is C. So D to C. So what we have to do? Update the cost based upon this one. Minimum of cost plus weight, comma, existing cost. So here you can see existing cost is infinity. So what we have to do? So minimum of cost. What is the cost of D? 4 plus weight 10, comma, infinity. So which one is the minimum? So obviously it will be 14. 14 is the minimum. So update this one with 14. Update this one with 14. Okay. Next, what we have to do? Repeat the same process from step 5. Okay, sorry. Step 6 and 7. Repeat the same process. Step 8. Repeat step 5 and 6. Sorry, 6 and 7. Step 6 and step 7 until all nodes becomes visited. So we have to repeat the same steps. So what is the step 6 after step 7? Consider vertex with the minimum cost as a source. Now consider the source. So these are the visited, right? We need not bother about that. So these are unvisited. Now consider the same 14, C14 and B5. So C14 and B5. Which one is the smaller? So obviously this is the smallest node. Consider this as a visited. And update the, what happens? Update the cost on neighboring vertices. And one point is important, that is no need to go with the visited nodes. So what are the neighbors of B, A and C? A is already visited, so we need not bother about that one. Go with the C. So what is the thing we have to do? A minimum of cost 5 plus 15, comma, 14. So the cost, existing cost is 14, right? So minimum of 5 plus 15, comma, 14. So what happens? This is a 20 and 14. So this is a minimum. Already the cost is minimum. So you need not change the cost. And then repeat the same thing. So add here B, right? And repeat the same thing. Consider a vertex with the minimum cost as source. Only one node is there, that with 14. So consider the same thing and go with the this one, right? So what is the order we have done? Simply go with the order. First we have seen A as a source. From that we have visited the D. From that we have visited the B. From that we have visited the C. Okay, D to C, right? D to C. And this is the minimum cost tree. Minimum cost tree. So this we call it as a tree because this is not closed. Okay, this is a open. So this we call it as a tree. So like this we have to apply the single source shortest path. Okay, so first I'll repeat once and I'll close. So in our next session we'll see one more example, right? So first consider any graph, any directed or undirected graph. So I am taking the undirected graph. So first select the source. So that will be the single source, and our aim is to find shortest path from the same source to all the remaining vertices. So here I am taking A. So we need to find out the shortest path from A to B, A to D and A to C. Now first initialize the cost of source as 0 and other vertices as infinite. So first 0 and other cost is infinite. So find out the minimum cost vertex from all the vertices. So we are having A is a minimum because it is a 0. So consider this one. And now find out the cost for all the neighbors. That also unvisited neighbors. Okay. So find the cost of, here I'll write unvisited neighbors. Unvisited neighbors. Okay. So A neighbors are B and D. So B with a cost 5 and D with a cost 4. And so A is completed because already the neighbors have been got a cost. So A will be considered as a visited. So we need not bother about A. Now we have to update the cost for each and every vertex. Now again the same process repeated. So we need to find the vertex with a minimum cost. So here 4, some here it will be 5 and it is a infinity. So 4 is the minimum cost. So we have to select the D and again repeat the same process. Find out all the unvisited neighbors and find out the cost and repeat the same until all the nodes or all the vertices have been visited. Right? So one thing, so here we are having a 2 paths in order to reach the C from A. AB, BC, AD, DC. That means we can have a multiple solutions, and from that multiple solutions we are taking a constraint as a shortest path based upon the cost of the edges. So that's why we can say this Dijkastra algorithm is an application of a greedy method. So which gives the optimal result among the several solutions. Right? Example for single source shortest path. So we can also call it as Dijkastra algorithm. And example for this Dijkastra algorithm. Example, right? So before going to the example, let us recall the algorithm. Okay, so first we have to select the source node or a source vertex, and we have to give the cost of that particular vertex as 0 and cost of all other vertices with an infinity. That's the first step. Second step, among all the cost or the cost of all vertices, select the minimum cost vertex. Okay, so that will be a visited vertex, right? And from that we have to change or update the cost of neighboring nodes, unvisited neighboring vertices. And we have to repeat the same process until all the vertices becomes visited vertices. So the main aim of this particular algorithm is to find the shortest path from source to all other vertices, not from source to destination, source to all other vertices. Right? Now we'll see an example. So let us take an example: A, B, C, so again I am taking undirected graph. Okay, so I'll give you some weights, random weights. I am giving some random weights. So let us take it as 8. Sorry. Okay, so this is a graph. Okay, so finally we'll get some tree. Okay, so from source, so I'll consider this one as a source. That means A is a source. So first what we have to do, we have to give the cost for every vertex. Okay, so I'll update the cost for A as 0 and all other vertices with infinity. Okay, the cost of all other vertices as infinity. Right? Now we have to find out the minimum. Okay, so the first step, cost of source 0, cost of other vertices infinity. Second step, minimum of all cost. Okay, the vertex, select the vertex with minimum cost. I'll write completely. Select vertex with minimum cost. So what is the minimum cost? A, right? A. So select this one, okay, and now we have to update the cost of adjacent. So let us select A, okay, so let us select A. So what are the adjacents? B and F. So update the cost of B and F. So this is a direct edge, okay, so we can update with a 5, and here it is 7, okay, 5 and 7, all remaining are infinity, and mark this one as a visited node. So A is visited now, because from A we have find out all the cost of adjacent vertices, okay, so we only two neighbors, so we found the cost of these two neighbors, B and F. Now we need to find the cost of, so the second step, we have to repeat the second step. What is the second step? Select the vertex with minimum cost. So I'll update here visited. So A is visited, and next upon all these things 5, 7, infinity, infinity, infinity. So among this one, which one is the highest? Sorry, minimum? 5. So select B. Select B. Now find out the neighbors. Okay, what are the neighbors? One is A, another one is F, another one is C. And you can observe A is already visited. You can see A is already visited, so you need not bother about A. So we need to find the cost of neighbors, unvisited neighbors, F and C. Okay, F and C. So what is the C? Update. So 5 is a cost. Here source is A, right? So the name itself indicates it's a single source shortest path. So we need to find out the shortest path from the same source. From A to B it is 5, and from B to C 5 plus 6 it will be 11. So the path from A to C via B will be the 11, and we have updated it. Now we need to find out the F. Okay, F. So from B to F it will be 5 plus 8. Okay, so don't forget to count the actual cost plus the weight, because here the source is fixed. That means we are finding the path from A itself. So here B to F means A to B and F. So this implies A to B, B to F, A to C, sorry, A to B, B to C. Okay, so A is visited and we are finding the next minimum path. So B to C it was 11, and B to F, what happens? 5 plus 8. Okay, so for this one it will be 5 plus 8, which gives 13. So we need to find the existing cost and the calculated cost, and we need to select the minimum among that one. So here already F is visited with a 7. Okay, there is the shortest path from A, it is 7, and now through B it will be 13. See, A to F is 7, and A to B and to F it will be 13. So among this one, which will be the shortest path? Obviously this will be the shortest path. So we need to select the minimum. Okay, minimum. So we need not update this one. We need not update this one. So we have already done with the neighbors of B. We have already done with the neighbors of B. So we can add this B to the visited set. So this node is visited. Now repeat the same process. Select the vertex with the minimum cost. Select the vertex with the minimum cost. So here where the vertex means unvisited. So here unvisited are F, C, D, E. Among all these one, which is the shortest, I mean minimum cost. Here 7, it is 11, infinity, infinity. So F is the shortest one, I mean minimum cost. So we can select F now. And now find out the adjacent neighbors of F. F, A, B, E. And you can see A and B are in the visited. So simply you can ignore. Okay, we need not revisit that particular vertexes. Okay, only there is a path from F to E. So the cost is 3. But here this implies what is this one? A to F and F to E. So what is a to F? It is 7. The cost plus 3, 10. In order to reach from A to E, the cost will be 10. So this is a 7 and this is 3, which gives 10. Right? So update this cost 10. Okay. So any other neighboring vertex, neighboring edges? No. So obviously we can add this to F. Okay. And this is the visited. F is visited now. Now repeat the same process. Again from the unvisited nodes or unvisited vertices, select the minimum. So which one is having the minimum? E with 10, C with 11 and D with infinity. Obviously E is the minimum. So E, and find out all the adjacent or the edges, neighboring edges. So E to F, E to C, E to D. Okay, E to F, E to C, E to D. Not this implies A to F, F to E. So we can write it here. A to F, F to E, and now E to F or E to C or E to D. So here any vertex in the visited, yes, F is already visited. So you need not worry about this one, F. So we have to find out the cost for E to C and E to D. So E to C, see, E to C. E to C means, see, A to F, F to E, E to C. Similarly, A to F, F to E, E to D. So what is the cost here? So A to F is 7, 7 plus 3, 10. So here we got a 10. So simply we can say 10 plus C, 10. See, E to C it is 10. So total 20. Already the cost of C from A is 11. That means the path or the distance required for A to reach C is 11 through B. And the path from A to C through F and E becomes 20. So which one will be the lowest? So obviously 11 will be the lowest. So we can discard. So we have to select the minimum. Okay. Now coming to this one. E to D. E to D. So already 10 is the cost to reach up to E, and to D it will be 12. So update this with 12. 12. So this will be 10 plus 2, it will be 12. And 12 and existing is infinity. So 12 and infinity, the minimum will be 12. So we are updating here. And what happens? Any other edges? No. So obviously we can select E as a visited. E as a visited. And here it will be E. Again, we are having a 2 more unvisited vertices. That is C and D. Select the minimum cost vertex. So among this C and D, C is the minimum. C is the minimum. So what we have to do? So we need to select C. In order to get C, we are using A to B, B to C. So what are the adjacent? C to B, C to E, C to D. And this comes from B and it comes from A. This implies. So we are just having the path from C to B, C to E and C to D. Select verify whether any vertex are in the visited. So B is visited, so you need not worry about this. E is also visited, you need not worry about this. So we are having only one edge, that is from C to D. So that implies A to B, B to C, C to D. So up to C it is 11 plus C to D it is 4. So which is 15. So from A to reach D, the cost is 15 through C. But through E, it becomes 12. So among these 12 and 15, which is the lowest? 12. So we can discard. So any other edges? No. So simply you can add it to visited. So you can add it to the visited. And now repeat the same process. Consider all the unvisited vertex, and from that unvisited vertex find out the vertex with the minimum cost. So we are having only one unvisited, right? Only one unvisited. So only one, and rest of all are visited. So obviously this will be visited with a 12. So this will also be added in the visited set. So this is the procedure to find out the minimum cost for each and every vertex from the source vertex. So first source is A. So B, C, D, E, F are the different vertices. So we are finding the shortest path to reach all other vertices from the source vertex. Okay. So what is the shortest path? Let us take A to B. That is directly, it is a 5. And A to F, it is directly a 7. So what about C? So A to B, B to C, it is 11. Next, E. A to F, F to E, it becomes 10. Next, A to F, F to E, E to D, it is 12. So this is the cost from A to B, A to F, A to C, A to E, and A to D. So you can apply here. First step, A. So it is a visited, and after that B. Next it becomes a B. Next it is F. Next visited is E. Next visited is C. Next visited is D through E. So this becomes a tree. This is not a graph, because we know that graph is a connected, right? So closed graph, closed loop. So here it is not connected, right? This is a tree, minimum cost tree from the single source. So this is a source. This one will be the source. Okay. So hope you understood this one. So the problem is finding the source node and finding the shortest path from source to all other vertex. Okay, so here I am not talking about the destination. So we are not considering the destination as D and finding the cost to reach the destination. So here the question is finding the shortest path from source to all other nodes. Okay, right? So this is the procedure, and what is the time complexity of this one? What is the time complexity? So one point is finding all the vertices. Okay, so considering all the vertices from A, all the edges. So what we are doing here is, so we are selecting A and all vertices, edges B and F. Next we are getting B and all vertices A, C and F, and we are finding the C with B, E, D and E, and D with C and E, and E is having some C, F and D, and similarly F is having A, B, E. So we are selecting each and every vertex and finding the edges, the cost of all incoming or outgoing edges. Okay, so that implies in order to iterate each and every vertex, it will be n minus 1, and again we have to repeat all the edges. So the maximum edges we can get is n minus 1, right? If n vertices are there, it can have n minus 1, right? So n minus 1 edges. So it will be n square. So the time complexity is order of n square, for this particular Dijkastra. And this is an example application of greedy method, which is used to solve the optimization problems. So here you can observe, in order to reach C, it can go with A, B and C, also A, F, E and C. And in order to reach F, it can directly go with a direct edge, or it can reach till A, B and F through B, right? So for this kind of problem, we are having a multiple solutions. So here, in order to reach F, what we are doing? In order to reach F, A to F is one path, A to B to F is another path. So we are having a multiple paths, and again we can have a multiple A to B, B to C, C to E and E to F. So that's also one path. So that means for finding the cost or reaching this one, so we are getting a lot of paths, multiple paths. But what we are selecting the path with minimum cost. That means the shortest path. So that kind of problems we call it as a greedy method, and this particular algorithm is implemented or solved by using this greedy method. So today we will see one more concept in algorithms, that is knapsack problem using greedy method. So how can we solve the knapsack problem using greedy method? So knapsack problem. So in our previous sessions, we have seen the 0-1 knapsack. So what is the 0-1 knapsack and what that 0 and 1 represents in the knapsack, right? So in that we have seen there will be some weights and corresponding profits, and there will be one container or a sack, okay? So with a capacity, so that we have to carry the products, okay, the weights inserting into this particular sack, so that we have to get the more profit. So here the status of the weight is represented with xi, and that can be either 0 or 1. So 0 implements, so not considering the weight, that means not inserting the weight into the sack, and 1 represent considering. So this is called as a 0-1 knapsack. So the only constraint is we have to get a more profits, okay? By moving the weights into this sack, we must get the more profit, and the result, the status of these weights will be either 0 or 1, either consider or not consider. And this 0-1 knapsack will be used for mainly non-divisible products. Non-divisible products. So non-divisible products means either we have to consider their weight or we may not consider the weight. So some portion of that weight can't be inserted into sack. So example, let us take some mobiles. So we can insert the complete mobile into the sack, but we can't insert a portion of mobile into sack. So that is not divisible, non-divisible. So we cannot divide the complete weight. So we have to consider either complete weight or we should not consider it. And similarly, some television. So we can't divide the television, right? We can't insert some portion of television into the sack, right? So these are all non-divisible products, and for that non-divisible products,
we are using this 0-1 knapsack. But coming to this one, knapsack problem. So this is mainly used for divisible products. Divisible products means the products which we can divide. That means we can consider some portion of the weight to be inserted into the sack. Example. So vegetables. So you can consider the vegetables so that you can give some portion of vegetables into the sack. For example, let it be some 3 kgs of onions over there. So we can accommodate 1 kg of onion into this sack, or 2 kg onion into the sack. That means we can accommodate the portion, not the full, the portion of the weights into the sack. Those products we call it as a divisible products, and this knapsack problem using greedy method will be useful for these kind of divisible products. So here the status xi. So previously the xi gives the status of weight, whether it can be considered or not considered. That too completely. So this can be in between 0 and 1. So 0 means completely not accepting, 1 means full weight is accepted, and in between 0 and 1, that is some portion of the weight is also accepted. Okay, so here the xi will be in between 0 and 1. 0 not accepting, 1 completely accepting. Some portion of the, if some portion of the weight is accepted, then it will be in between 0 and 1. So that is our knapsack problem. So there is a slight difference between 0-1 knapsack and knapsack. If you are saying 0-1 knapsack, there will be no fractional weights. Okay, so if you are talking about the knapsack, it allows the fractional weights. It allows the part of weights. Right? Now, let us check with an example how we can solve this one. Right? So, whatever the thing we have learned in 0-1 knapsacks is completely different. And now, this is mainly for divisible products. Now, we'll take an example. So here, let us consider this example. So it is having some 4 weights. Okay. So let us assume this one as x1, x2, x3 and x4. So there are 4 weights and the corresponding profits. So by moving the 3 weights capacity, we are getting a profit of 15. So by moving 4 weights of capacity, 4 kgs of weight, we are getting some 24 as a profit. Consider this weights in a kgs and profits as a rupees, right? So 6 kg weight, if you move the 6 kg weight, you will be getting the profit as 12 rupees. If you are moving 2 kg weight, you will be getting the profit as 17 rupees. Now we need to carry the weights into the sack from one place to another place. So without beyond going the capacity, with a more number of profits. Now the capacity of sack is 11. Let us assume it. Okay. Now, as I have said that these are the suitable for divisible products. So, for example, let us take 3 kg. If you are moving the 3 kg weight, we are getting a profit of 15. Now, if you want to move 1 kg weight, what will be the profit? Because in this particular knapsack using greedy, we can accommodate some portion of the weights into the sack. So, it is not needed to give complete 3 kg weight into the sack, right? So we can also accommodate some portion of the weights. So first we need to calculate the profit per weight. Okay, so first we need to calculate the profit by weight. So the profit by weight, 15 by 3, it's 5. 24 by 4, 6. 12 by 6, 2, 17 by 2, 8.5. Okay, so this is a profit per weight. Imagine this is a 5 rupees per kg, 6 rupees per kg, 2 rupees per kg, 8.5 rupees per kg. Now the next step, arrange weights and profits in descending order. In descending order with respect to Pi by Wi. So with respect to Pi by Wi, we have to arrange them in descending order. So you can check what is the highest one. So I once again I'll write the X values, weights, profits. Okay. Now among these, which one is the highest profit? 8.5. So 8.5 means 2 and 17. So weight is 2, 17 is the profit, the X value is X4. The next one, 6, 424. So 424, the X value is X2. Next, 15, 315. 3 and 15, the X value is X1. Next, 612. 612, the X value is X3. So after calculating the Pi by Wi, the profit per weight, we need to arrange the weight and profit in descending order with respect to Pi by Wi. So with respect to Pi by Wi, the highest profit is 8.5. So that means weight 2 and profit 17. That should be written first. So we are saying it as a descending order, right? Next 6, 4 and 24. So I am also writing the corresponding X value. Corresponding X value. Now, so initially the weight of capacity, the sack is 11, right? So first insert 2. Insert 2 so that the balance capacity will be 9. Okay, so 2 is completely inserted in the sack, because if you push this 2 into the sack, we are getting more profit. So we can push the complete weight into the sack. So what is the X value? X4. So what is the X4 value? We are completely pushing it into the sack, right? So X4 will be 1. So we are saying that if X value is 1, that indicates that weight is completely pushed into the sack. And if it is 0, not considered, right? And if it is in between 0 and 1, that implies some portion of weight is added. So we are giving the X4. In the next step, what we are doing? So already 2 is there and M is equal to 9, right? Now insert 4. 4. You can check. So 4 can be accommodated in 9 capacity. So what is the remaining? 5. Remaining capacity is 5. So what about the status? X2. So here you can see X2. X2, 1, because we are completely inserting the weight into the sack. Then, so 2 is inserted, 4 is inserted, and M value is 5 now. Okay. Now 3. Yes, 3 can be accommodated in a 5 capacity. So 3 can be included and the remaining sack weight is 2. And what about this value? X value, X1. So we are inserting the complete weight. So X1 is equal to 1. And then, so 2 is there, 4 is there, 3 is there, and again still the capacity is 2. Okay. But if you observe, here we are having the weight 6. So 6 can't be accommodated in 2 capacity. So what we have to do? We have to divide that 6, and from 6 we are inserting 2 weights, 2 kg weight into the sack. So here it will be 0 and I am inserting 2. So X3 value will be not 1, because we are not inserting the complete weight. Okay, and it is also not 0 because we are considering some portion. So what is the portion? We are considering 2 out of 6. 2 kgs out of 6. So X3 will be 2 by 6. X3 will be 2 by 6. Now you can check with the formula sigma xi into wi, which will give the complete capacity of the sack. You can observe x1, what is x1? 1 into, what is the weight? x1 weight 3 plus x2 1 into, what is the x2 weight? 4, okay, plus x3 1 by 3 or 2 by 6. You can directly write it as a 2 by 6, right? So 2 by 6 into x3 6 plus x4 1 into x4 value is 2. Now if you observe, so this will be 3 plus 4 plus 2 plus, what is this one again? 2. So the complete result is 11. So which is the capacity of sack? Which is the capacity of sack? Now what will be the profit? What is the profit? So profit, how much profit we are getting means simply you can calculate sigma xi into pi. Okay, so this will give the profit, how much profit we are getting. So here you can observe x1 means, see x1 here 1 into, what is the profit of x1? 15 plus x2 1 into x2 profit 24 plus x3 2 by 6 means 1 by 3 into, what's the x3 profit is 12 plus x4 1 into x4 value profit is 17. Now you can check, this is 15 plus this is 24 plus this will be 4 plus it will be 17. So total 39 plus 4 43 plus 17 60. So 60 will be the profit if you insert the values. You can see the result x1, x2, x3, x4. So the result is x1 1, consider x1, consider x2, consider 2 by 3 of x3 and consider x4. So this will be the result. So by considering the first weight, second weight, fourth weight and some portion of, sorry, this is 1 by 3 I think. Yeah, 2 by 6 means 1 by 3. Right? So 1/3, right? So by considering this portion, right, the complete weight of x1, complete weight of x2, complete weight of x4 and 1/3 weight of x3 will give you the profit of 60. So this is how we can solve the knapsack problem using greedy method. So here first we have to find out the profit by weight. So per weight how much profit we are getting, and based upon the pi by wi value we have to rearrange all the weights and profits in a descending order. That means highest should become first, and then slowly keep on inserting each and every weight into the sack based upon this changed order, right? So finally if you go with this formula sigma xi pi, so you'll be getting the highest profit, right? So this is how we can solve the knapsack problem, and once again I am repeating, knapsack problem is completely different with a 0-1 knapsack. So 0-1 means it doesn't accept the fractional values, it doesn't accept the portion of weights to be inserted into the sack. But coming to the knapsack, the status of x value, the weight, some portion of the weight can also be accommodated in the sack based upon the capacity remaining in the sack.